말씀 들리시나요? 아, 그래요? 그럼 됐네요. 네, 지금 잘 들리세요? 아,
배터리가 없으면 어떤 현상이 나냐면 봐봐. 자 여러분이 보시는 그 지금부터 제가 뭘 하겠습니다. 방금 나 그러면 배터리부터 주잖아. 무조건 붙여야 돼. 또 없지? 이거 아니잖아. 그지? 그지? 한 25. Is it milk or?
Yes. Mm. They also don't have a low enough power. Yeah.
It's a safe power? Or
Yeah. They use a. actually, but yeah. And the other one is very short. It could be long enough. Whatever you feel. I think it's just long enough. Yeah. If we switch, if you give me, just the. Maybe, yeah. If I know. Okay. Let me just check if this works.
So good morning. Welcome to the Kavli Asian Winter School on Strings, Particles and Cosmology. So let's start. First lecture will be given by Professor Daniel Baumann from Amsterdam and also from Taipei on primordial cosmology. Welcome.
Okay, thank you very much. Yeah, thanks a lot for the invitation. It's really a great pleasure to be back here. So, yeah, when I was asked to give lectures here and asked for a title, I gave this very kind of broad and vague title of Primordial Cosmology. I decided to make it slightly more specific, and I'm going to be talking about cosmological correlations. Okay. As you will see, cosmological correlations are kind of the main observable in cosmology. And in fact, they capture a lot of early universe cosmology that we can access observationally. Just like, they're the analog of scattering amplitudes for particle physics, or cross sections for particle physics. And so we will touch on a lot of aspects of primordial cosmology just by studying kind of the structure and the observations and the theory of cosmological correlations. Okay. So today's lecture, the first lecture here will be on slides, and I apologize for using slides. I really don't like it usually. Let me explain why I do this, and then we can make a plan for the following lectures. So the reason I made slides here is twofold. One, I wasn't exactly sure what the setup was, and whether it would be convenient to use blackboards. And there's some people online, I understand, and for them it might be a better experience to see things on slides. And then second, I gave these lectures a few weeks ago at Imperial College in London, and I wasn't able to cover as much as I would have liked. Okay, I mean that's okay, but slides will allow me to show you a few of the explicit things and long equations, in a slightly more efficient way. But of course, it has the enormous drawback that I'm in danger of losing some of you in the weeds, and so that should not happen. And so if there's any danger of that happen, please shout out, stop me, slow me down. And I'm totally flexible also to switching to the blackboard, and I will probably do that this afternoon anyway. And we might be going back and forth between the board and the slides. Okay, I've prepared slides for everything, and I will put them up on some website, and you can look at those slides also in your own time. But hopefully this is going to be a teaching experience rather than just me, lecturing to you. Okay. So this also means please stop me at any time. Please ask me questions. We have a long slot. It's 80 minutes. I don't want to speak for 80 minutes straight, uninterrupted. That would be horrible. And so, yeah, please don't feel shy to ask anything at any point. Okay, so this first talk here will be kind of low level, I hope, at the level of a colloquium, I would say. Just to set the stage, whoa. I don't know. Thank you. And then the topic is actually rather technical. So if you're worried that there will be too few technical details in this first talk, don't worry, because there's actually a lot of technical subtopics, and the danger is really of having too many technical aspects that not all of you will need to see. Okay, so let me start by just motivating a bit more why we're interested in cosmological correlations. So as I said already, those are the main observables in cosmology. So what we do in cosmology is we measure the distribution of stuff, galaxies, the distribution of matter, the cosmic microwave background radiation. And we first discovered that stuff in the universe isn't distributed randomly. Yeah? At first sight, it looks rather random. In all different directions, you have an equal number of galaxies, dense clumps of matter. But when you look at it more carefully and study statistical correlations between points in space, you will find these points not to be independent. And in fact, you measure things like the power spectrum. This is what I'm showing you here. So as a function of time, you can measure correlations in the density of matter using different traces of that density. So at late times, we measure, for example, the distribution of galaxies, and we can measure its two-point function. And the main shape of the two-point function is this. Okay, I will explain a little bit later where, what generates these kind of shapes. We measure also radiation from the very early universe called the cosmic microwave background. So this is the first light that we receive from when the universe became transparent to light and the first neutral atoms were forming. This creates this interesting spectrum, and we will talk today a little bit about what creates these bumps and wiggles in the power spectrum of the CMB. Okay? Some of you might have seen that explanation before, especially if you took a course in cosmology. I want to spend a bit of detail today in explaining this shape, because it's often underappreciated how amazing it is that we actually see this structure at early times. And so, as you can see, we see these correlations as a function of time. And so it tells us both about the evolution of the universe. So by trying to connect these correlations at different moments in time using a consistent cosmological model, we learn about how the universe was evolving from one stage to the next. But it also tells us about the initial conditions, because you have to put in some initial non-random spectrum in order to create all of the structural correlations that we see at late times. So we do two things. We learn about the early universe. We do primordial cosmology, trying to infer the initial conditions of the hot Big Bang. And we then measure how these correlations evolved in time. Okay? Any questions so far? No? Okay, so just let me give you two prime examples that I mentioned already. So we measure correlations in the temperature of this afterglow of the Big Bang, the cosmic microwave background. It has this particular power spectrum as a function of separation. So here the x-axis is the angular separation of 2 points in the sky. It's statistically isotropic, so any 2 points in the sky you can rotate and you get statistically isotropic correlations around kind of a circle. And so we just measure kind of the correlations as a function of the radius of that circle, randomly moved across the sky, and this is what you're seeing here. So there's an enormous amount of information in this pattern, okay? And we will talk about it quite a bit today. First of all, the position of this first peak here tells you about the large-scale geometry of the universe, the fact that it's spatially flat. It also tells you about the presence of dark energy. The height of that peak tells you about the amount of dark matter in the universe. The relative heights of all these of odd and even peaks tells you the amount of baryons in the universe, and that there was not enough baryonic matter to make up all of the matter in the universe, and we need an extra dark matter. And then finally, the damping tail, the fact that the fluctuations, start with rather constant amplitudes and then they damp on very short scales, is a signature of the presence of free streaming neutrinos. Okay, so we can confirm, for example, that the standard model has 3 neutrino generations with an abundance that's dictated by thermal freeze-out at the weak scale from this pattern of fluctuations. Okay, so we don't just do cosmology; we also do particle physics when we're looking at this pattern of fluctuations. This is really the Mona Lisa of cosmology. Okay, it's the most amazing plot ever generated by cosmologists ever. Okay, it's 1 million data points that have been binned here so that the error bars become small. And then this red curve here has 6 free parameters that basically measure these different physical characteristics that I just described. And with these 6 parameters, we fit these millions of data points, perfectly. Okay. As I said, we then also, these initial fluctuations evolve in time. They then cluster into nonlinear objects, galaxies. And we can measure the distribution of that galaxies and also measure a 2-point correlation function in space. And so here, this is the Fourier power spectrum of that 2-point correlation function. Okay? And it's rather smooth. So it has a characteristic linear in k scaling and then an inverse of k cubed scaling on small scales. Okay? And we understand perfectly why it has these effects. Basically, the reason it has these effects is that the universe goes from being radiation dominated at early times to matter dominated at late times. That happens at a redshift about 3,400. Okay, that's just a little bit before the universe became transparent to light, which happened at a redshift of 1,100. Okay, and that transition from going from radiation dominated to matter domination changed the evolution of fluctuations. And that change in the evolution of fluctuations is reflected in the shape of this power spectrum. So by measuring the position of this peak here, we have another independent measurement of the amount of matter in the universe relative to the amount of radiation. Okay. Okay, so far so good. This is, very simplified. This is what we observe. So we have 2 different snapshots of correlations in the universe as a function of time. Under relatively mild assumptions, we can then trace these correlations back in time, all the way to the origin of the hot Big Bang. Yeah, so to what, some first moment when the universe can be described by a thermal bath of particles. Okay, and of course, because of thermal equilibrium, there's some kind of it's not very important where you define this surface, as long as the universe has established thermal equilibrium. So there's some initial surface that we call the reheating surface or the origin of the hot Big Bang, and we can trace these fluctuations back to that initial surface. Yeah, so this concept is important because that initial surface will be the star of the show. We will have to understand, when we talk about primordial cosmology and we're trying to understand the initial conditions of the hot Big Bang, we're always talking about correlations, fluctuations living on that initial surface. There's some spatial surface that provides a boundary for the hot Big Bang. We know now that that initial surface was not the beginning of the universe. There was some prehistory, and we'd like to infer what this prehistory was by measuring things at late times. But we always do that by tracing the fluctuations back in time to this initial surface and trying to make inferences at that initial surface. Okay? And so we have so far, in fact, learned 2 interesting facts about the initial conditions when we do this process of taking late time fluctuations, tracing them back in time. The first thing we have learned is something I just mentioned, that these fluctuations were not created during the hot Big Bang. In fact, the universe did not begin with the hot Big Bang, but there must have been a period before the hot Big Bang that created the fluctuations. This is relatively recent. I think this was established 20 years ago, 25 years ago. And I think it's an amazing fact. It's one of the number 1 amazing facts that I know, okay? Just as I said, 25 years ago, it would totally have been possible that the universe started with the hot Big Bang and this standard story of the Big Bang. these initial conditions, as I will explain later, could not have been created during the thermal phase of the universe. There was something before, okay? So that's, I think, stunning to know, but we don't know exactly what happened there. We have one clue, namely that these initial fluctuations are scale invariant. And so we're only measuring a snapshot in time, and we find it to be scale invariant. But when we introduce a dynamical theory of the early universe before the hot Big Bang, that scale dependence arises typically from a time translation dependence of the dynamics. So there's a relation between time and space through cosmological evolution. And so we have some hints that this, whatever came before the hot Big Bang, was a phase of near time translation invariance. Okay? So those, I think, are two things that we have learned from observations. So far, there's not very little theory that goes into this. This is pretty agnostic about the type of theories that we usually contemplate. Of course, we will see that inflation is kind of one very natural way of generating this time translation invariant dynamics, but it's not, maybe not the only thing that you can do. And so then finally, we will be interested for a lot of these lectures also in cosmological correlations just for conceptual reasons. Yeah? So there are these grand practical observational motivations for studying them, but as we will see, they also provide to us like a very interesting field theory problem. Quantum field theory in a cosmological evolving space-time is much worse understood than quantum field theory in flat space or in ADS space. And so I've tried to illustrate this here. So here this axis shows our level of understanding in some very vaguely defined sense. And I'm showing you three maximally symmetric spacetimes: de Sitter space, Minkowski space, and ADS space. Okay? And I would claim that, like we understand de Sitter space, which arguably is kind of a good approximation to both the early and the universe, the least of those. Yeah? Meaning when we study perturbative processes, we barely understand them at tree level. Until recently, I would have claimed we actually don't understand the analytic structure of these cosmological correlators, even at tree level. Okay? For scattering amplitudes, we understand tree level perfectly, and we understand many of the loop results also, order by order in perturbation theory. And then in ADS, we have even non-perturbative ways of defining via conformal field theories the correlation functions. So it's a bit embarrassing that the closer we go to the real world, the less we understand. That's not a good state of affairs. So it's, I think, of great conceptual interest to try to understand de Sitter space in quantum field theory. Okay. And in particular, it's as I said, this is very much under development, and it's an opportunity for you guys to to do something very significant. Right? Any questions so far? No? Okay, so this was just kind of very broad motivation. Let me get a bit more specific. Yeah, so the outline of my lectures is going to be the following. I want to spend today saying a bit more about just cosmological correlations, how we measure them, what they teach us, and so forth. That's going to be lecture number 1. Then in the afternoon, I will continue to show you a way of computing those cosmological correlations that maybe is not as familiar to everybody. As we will see, actually, there's 3 ways of calculating cosmological correlations. The standard way of doing that is the in formalism. And so that's maybe, if some of you have studied this before, this is the thing that people would have presumably taught you. There's an alternative way that's called the wave function of the universe, or the wave function approach that's not often taught. And so I want to teach you this wave function approach, because this wave function of the universe has some properties that are slightly nicer than the properties of cosmological correlations, but they're very closely linked to each other, as we will see. And then also the wave function universe provides the seed or the primary object for a new bootstrap approach to try to understand these correlation functions. And so by studying the wave function, we will very naturally be led to ways of actually bootstrapping this wave function rather than calculating it dynamically. And so I don't know how long this will take me, but roughly speaking, I was planning this to be divided between lectures 2 and 3 for the wave function, and then 3 and 4 for the bootstrap. All right? Okay, so then I should say that over the past few months, together with my friend Austin Joyce, we have written quite extensive lecture notes. And I've put a kind of preliminary version of those lecture notes on this website here. In fact, maybe today or tomorrow I will put an update of those lecture notes. This is now already a couple of months old. And so a lot of the details that I will not be able to go through in real time, you can find those, okay? I will try to tell you the essentials that are important for everybody to see, I think, during the lectures, and then those of you who really want to work on this stuff, I encourage to check out these lecture notes, okay? They're very explicit. They really teach you how to calculate these things. They have lots of examples, even solve problems and things like that, okay? Questions? Any questions about the plan? Okay. All right, so let me start with a brief overview of the topic of cosmological correlations. So I've showed you this plot before. This is the power spectrum of the CMB. And I want to spend the next 20 minutes or so describing in a bit more detail the physics of this power spectrum. And I want to highlight a few things that maybe are underappreciated in the mainstream courses on the topic. So actually, first of all, let me give you what I think is a very nice illustration of what this power spectrum actually means visually, okay? So, so one way of visualizing this power spectrum is, so this is as a function of scale, sorry. Here, multiple moments here correspond to just scales when described in spherical harmonics. And so let's imagine now we take the map of the CMB and we coarse grain it. You know, we filter it and only allowing certain scales to come through. Okay, it's just smoothing the map of the CMB. And so that allows you to kind of zoom in to different parts of this power spectrum, and you can see what this map looks like. So for example, if I coarse grain the map of the CMB to very large scales, it would look something like this. Only the largest blobs in the CMB survive. Everything else gets kind of averaged together, okay? So this allows you to kind of focus on the large scale features of the map. And now what I'm going to do is I'm going to step through the power spectrum and show you how the CMB looks like when you filter it on different scales. Is that clear? So this is what it looks like when you just, you know, put on very blurry glasses and you look at the CMB just coarse grained on the largest scales, tens of degrees. This is roughly what Kobe saw, the Kobe satellite that first measured these fluctuations. Actually, this is more like what Kobe saw. So now I'm going to step through. I'm going to look at finer and finer details of the CMB, and I'm going to show you how it changes, and at the same time, we're going to look at this power spectrum. Okay? So here we're zooming. It's a nearly scale invariant out here. So the strength of these blobs, you know, the intensity of the blobs doesn't really change visually. Okay? Just the size of the blobs changes as I'm stepping through. But we are approaching the first peak. So if you look closely, you should not, you know, in the next step or the one after that, you should see that these peaks are getting more intense as I'm zooming into this. Maybe it's hard to see, but maybe if I go back and forth. So this is the peak of the power spectrum. Yeah, if I tell you, maybe you believe it, but of course, the power spectrum is giving you a quantitative sense of measuring the strength of the fluctuations as a function of scale. And so visually, when we coarse grain, we should see that there's a peak here, that it becomes stronger, and then as I'm stepping through it, the fluctuations get washed out, and you have this damping feature where the intensity goes down. Okay. So maybe not showing so well. You know, if I'm uploading the slides, you can try to look at it on your computer. I think it's a little bit clearer on the computer. Okay. Any questions about this? Okay. This is just to show you visually what the power spectrum means. But now we want to discuss actually what created these features. Okay, I made a big deal about us seeing kind of the power going up and down, the intensity of these spots becoming strong and weaker. So let's discuss what created these features. So the cartoon picture of the cosmic microwave background is the following, that at very early times, you have a plasma of free particles, photons and baryons, and the baryons are mostly protons and electrons. This is before nucleosynthesis, where the light elements have formed. Actually, it doesn't really have to be, even because by number density, kind of most of the atoms in the universe are also hydrogen. And so you form a little bit of helium and lithium as the universe goes through nucleosynthesis, but doesn't change the picture very much. So we have mostly protons and electrons. But they're free particles, so the photons are very strongly scattering between the protons and the electrons. Okay? Actually, Thomson scattering scales inversely with the mass of the particle, so most of the strongest scattering is with the electrons. But then the electrons and the protons are strongly connected by the Coulomb force. So essentially, you can view the entire baryonic matter as one fluid, and then the photons as another fluid, and they're strongly interacting because the photons and electrons are scattering with each other. Okay? And so it's a strongly coupled single fluid made out of baryons and photons. Okay? In addition, you have dark matter that is decoupled from those particles and just provides a gravitational potential well for these fluctuations, a driving force for making the fluctuations collapse. So the picture is the following. You have a kind of gravitational potential well due to the dark matter. You have baryons that give mass or weight to the fluid. And then you have photons that produce pressure. Because what happens when you try to have a hot gas and you compress it, it heats up, it creates more pressure. And so there's a photon pressure that tries to push the fluctuations apart, while the dark matter is trying to compress the fluctuations. And so what you naturally get is you get oscillations in this primordial fluid driven by the dark matter fluctuations and the photon pressure. Okay? So this is very much the same as sound waves of air in this room. Yeah? So I'm creating a driving force by speaking of these sound waves. They then propagate through the room as density waves. And it's the temperature of the gas that provides the restoring force, just like the temperature of the photons that provides the restoring force of this plasma. Okay? So you have these sound waves in the early universe. Okay? Is that picture clear? And so, of course, when we have these waves, they're small amplitude waves. So it's it's natural, as always, to decompose those small amplitude waves into Fourier components. And then in linear theory, the different Fourier modes will evolve independently. So we can describe them one at a time. So that's what I'm doing here. So there's a density fluctuation in the density of the photons relative to the mean background density. So there's a fractional density fluctuation in the photons. And there's two different, there's waves of different amplitudes A and B. With a sine or a cosine dependence. Okay? And then when we look at the CMB, we're evaluating these density fluctuations in the photons essentially at a fixed moment in time, because we see these photons when they stream to us from the moment when the universe becomes transparent to light. And of course, fluctuations in the density are directly related to fluctuations in the temperature, by a factor of 4, in fact. Does anybody know what this factor of 4 comes from? So the fractional density of photons is exactly 4 times the fractional change in the temperature of the photons. Any idea where this 4 comes from? Yeah. Sorry? Curiously, it's related to space-time dimension, I think. So in different dimensions, this would not be 4. But yeah. Sorry? Can you say it louder? Space-time volume? Oh, Stefan Boltzmann. Yeah, exactly. So also just by dimensional analysis at high temperatures, the only dimensional quantity is temperature. And then as he was saying, in 4 dimensions, energy density has mass dimension 4. So it scales as temperature to the 4th. And so if I then just Taylor expand fluctuations around the mean, the factor of 4 gets pulled down. And so the fractional change in the temperature of the gas as a function of spatial position is related by a factor of 4 to the fractional change in the density. Okay? Yeah. And he's right, of course. If the number of space-time dimensions had changed, then the mass dimension of density would be different, and this wouldn't be 4 anymore. Okay? Yeah. So in that sense, we have proven that the universe is 4-dimensional in space-time at some at those times. Okay? Okay, and these amplitudes here are stochastic. Yeah, so there's some random process in the early universe that set up these fluctuations, and so these wave amplitudes have random variables, and in particular they have 0 mean. Yeah, and that's just by definition even, because we're defining these fluctuations relative to a background homogeneous universe, and so. Statistically, as I'm changing position and average over all positions, the 1-point function of those fluctuations has to vanish, okay? And that's just a reflection then of the fact that these 2 amplitudes, A and B, are stochastic variables with 0 mean. And by the way, this is also why we actually don't see visually a wave pattern in the sky, okay? Because we don't have a non-zero 1-point function. So we don't see just clearly waves propagating because they just washed out when we take spatial averages. Yeah. So in order to see this wave-like pattern, we have to look at the map statistically, not just looking at kind of one-point statistics, but higher point statistics. And the first statistics that we looked at, of course, is the two-point function. So then we take the two-point function of temperature fluctuations, now in Fourier space, so this is the power spectrum of those fluctuations. If you have these two modes, one sine and one cosine, that just means that the waves have random phases, and square the sine and the cosine solution, you get three terms. So you get a cosine squared multiplied by the power spectrum of the amplitude of the cosine wave. You get a sine squared solution multiplied by the power spectrum of the b, the amplitude of the cosine, the sine solution, and you get a cross term multiplied by the cross correlation between coefficient A and coefficient B. Okay. Now, if these sound waves were created by some random source, so if there was something jiggling in the early universe during the hot Big Bang, for example, yeah, that means that the cross correlation between those two waves has to vanish, and the autocorrelation of the amplitudes has to be equal. That's just what randomness means in the statistical sense. So there's just a single power spectrum that dictates the cosine and the sine solution, or or these Fourier modes have random phases as a function of wave number. And that then means that this two-point function becomes, so this middle term here will vanish, and you add up these two cosine squared and sine squared with equal amplitude, and by the magic of trigonometry of cos squared plus sine squared equals 1, this will just give us the power spectrum of the initial fluctuations. But that initial power spectrum we assume to be just scale invariant, yeah, or has some function of k, but no function of kind of, yeah, the whole sine and cosine feature that we had, we were amazed by due to the sound waves in the early universe has disappeared. Okay? So the question then is, where are these oscillations that we imprinted in the fluctuations? Okay? And so this is just a reflection of the fact that these initial fluctuations could not have been a random source in the hot Big Bang. Yeah? There must have been something more correlated, more systematic going on, and I'm going to show you now what that looked like. Okay? But first of all, can I check whether this argument is okay? All right. Okay, so as I said, in order to explain why we're seeing these oscillating features in the power spectrum, we have to assume that these sound phases do not have random phases. Okay. So for example, imagine that these fluctuations were created by a pure cosine solution and have no admixture of a sine solution. Okay, so that picks out a specific phase for all of the wave numbers. So and what's important is that this is the same cosine solution independent of k. Yeah. So when we have Fourier modes, of course, we're separating the signal into different wavelengths, different wave numbers, and the point is that each of these wavelengths has the same initial phase. Okay, so that you get a cosine. If they had random phases, we would get an equal number of sine and cosine contributions. And so what we're seeing in the sky is that that's not the case. We have to have some more structured result. If it was purely cosine and we square the cosine, of course, now we do get cosine squared by itself with no sine squared. And when we're evaluating that as a fixed moment in time, this becomes an oscillating function as a function of k. And then when we project it onto the sky, this is oscillating in multiple moment L. Okay? And that's what we're seeing when we're looking at the sky. We're seeing these sound waves with the very peculiar property that the amplitude of the sound waves was not generated by some random jiggling force in the hot Big Bang, but by something that somehow was setting up the initial phases of these waves to be all equal for every wavelength of the fluctuation. Okay? And so the question is, what created these coherent phases in the primordial sound waves? Okay? Okay, so my claim is that this phase coherence was created because the fluctuations were created before the hot Big Bang. It's these oscillations and the fact that they're coming from these initial conditions with coherent phases that tell us that the universe had an age before the hot Big Bang. So let me explain to you a little bit why. So if we go back in time, then all the fluctuations have wavelengths that are bigger than the Hubble horizon, the Hubble scale in the early universe. Okay, and that's just because physical wavelengths scale as 1 power of the scale factor of the universe, while the Hubble scale, for example, during a radiation-dominated universe, scales as the inverse Hubble scale, which is the Hubble radius, scales as 2 powers of the scale factor. And so there has to be a crossover where the physical wavelength of fluctuations was greater than the Hubble radius, or the causality scale in the hot Big Bang at early times. And so then it's not hard to show that even if we don't know exactly what the evolution equations were for the photon baryon fluid at those very early times, although we kind of know it, on very large scales, just by causality, you get two modes. You get one constant frozen fluctuation, and you get a second decaying fluctuation. Okay? There's various ways of deriving this, but it's mostly just because once you're outside of the Hubble radius, there's no, by causality, kind of gravity cannot kind of change the fluctuations, and so you just have some constant growing mode and then a decaying fluctuation. And so if the fluctuations were created long before the hot Big Bang, then eventually you would always get dominated by this constant growing mode. So sorry, it's called the growing mode just because it doesn't decay. So there's, second order equations always have these two solutions that are growing and decaying. Sometimes the growing mode is not a true growing mode. Sometimes it's even decaying, but it's decaying more slowly than the actual decaying mode. Okay. So we call this the growing mode. And so only this growing mode survives. Because if I have a long period of evolution, the scale factor gets bigger and bigger. This decaying mode gets smaller and smaller if they start roughly with equal amplitudes at some moment. Unless you exponentially enhance by some mechanism this decaying mode, it's going to be gone, if you just wait long enough. And if it's gone, then the simple constant growing mode eventually has to be matched on to these sound waves. And it will match on to the cosine solution, not the sine solution, because the cosine solution is the one that has zero velocity at the moment when the fluctuations come inside of the Hubble radius. Okay? And so the matching condition between this constant growing mode and the oscillating waves on small scales will tell you that they all have coherent phases. Okay? So this is a bit schematic. You can make this more formal, but essentially this is what's going on. Okay? I should emphasize this does not yet tell you that this was inflation. It just tells you that there was a long period before the hot Big Bang where these two solutions on large scales that you always get, reduced to just a single constant solution, and that a constant solution gives you a cosine at late times. All right? I think this is super duper important. Okay? This is not often explained when people motivate inflation, for example, as kind of a mechanism to generate the initial conditions, just because it takes a little bit of time. So in popular talks, people will not have the time to explain this to you. There's one really nice article by Scott Doddleson that I encourage you to find on the web that explains this in quite a bit of detail. He makes this the entire point of his talk or lecture or something like that. And so there he will even give you a bit more details. Yeah? Sorry? Say again?
Is this the only way to explain the phase covariance?
Well, it's always hard to prove uniqueness. Okay, but so far somehow I've used very little input. Yeah, so I've used kind of that the initial universe, the early universe was described by an FRW homogeneous and isotropic universe and things like that. So if you break all of that, maybe there's some island of theory space where you can do something else. So I never want to say it's impossible to do anything, but within the framework that I was somehow sketching out, I think it's almost a proof. In fact, one should also say that this phase coherence is on scales that are larger, is set up on scales larger than the Hubble radius. So by causality, this cannot have happened in the hot Big Bang. Okay, and so there just had to have been some time before the hot Big Bang. And so that's actually the message I want to commute at this point. Yeah, we haven't yet become more specific than that, but I think it's remarkable that we have learned that fact. That's kind of a new cosmological feature as of 20 years ago, that then there has to be something extra. I don't want to yet say that this is inflation. We're going to talk about the evidence for inflation in a moment. But it is, to me, evidence, very strong evidence that the hot Big Bang was not the beginning. Okay? Indeed. So actually, at this point, I would say that this suggests two options. Yeah. So you have to create some history before the hot Big Bang, and there's actually, roughly speaking, in this FRW context, there's two ways of doing that. One is to have very rapid expansion, okay, and that turns out extends. In the technical sense, it extends conformal time. Physical time actually never changes, but it's the conformal time that becomes negative during inflation. And so you can actually go past the origin of the hot Big Bang in conformal time. We will see this in equations in a moment, okay? So that's one option. You just have very rapid expansion, and that changes the relationship between physical time and conformal time. And it's the conformal time that's relevant for the propagation of light and causal processes. And so if we can manage to have more conformal time than we thought for the same amount of physical time, we solve the problem, okay? So that's one way of doing it. And the second way of doing it is to have a long period of slow contraction. And so that also, as it turns out, achieves the fact that it decouples physical and conformal time in that sense. Okay, but then the universe has, of course, the universe is not contracting right now, so it somehow has to connect to an expanding universe eventually. And so there's this uncertain phase of where the universe goes to very high density and then bounces. It becomes an expanding hot Big Bang universe. And so because of this uncertainty and the fact that we don't have good control over what happens at the bounce, I'm going to be mostly focusing on this first scenario here. Okay. But there's, of course, a lot of activity also trying to understand, trying to put ingredients. It turns out that in classical physics, it's hard to have this bounce. It violates the null energy condition. So if you have a bouncing universe, the sign of the Hubble rate, the change of the Hubble rate has to change, of course, and that violates, turns out, the null energy condition. So you need some null energy violating phase of the universe. In classical physics, this seems hard to do, but in quantum physics, you can maybe do that, and so on. It's a hard problem. Okay? So I'm going to focus on the first option. Also because there's actually additional evidence for the first option that I want to now show you. And so the evidence for the first option, I would say that's quite compelling, is the fact that these primordial fluctuations were approximately scale invariant. Okay, so I said this before, but when you take the fluctuations and the CMB, you trace them back in time using the known fluid equations that are kind of sketched with the harmonic oscillator. Yeah. Then you see that this pattern here, you find that this pattern here is consistent with a perfectly scale invariant power spectrum of the initial gravitational metric fluctuations, for example. The Newtonian potential at early times was nearly scale invariant. And this is an observational plot of that feature. So what you're seeing here is on the on the x-axis, you see the deviation from perfect scale invariance. There's a strange way that we will see in a moment that this is parameterized by the deviation from a number 1. So perfect scale invariance corresponds to this primordial tilt of the spectrum of ns equals to 1. So this green line here would correspond to a perfectly scale invariant spectrum. And we see that it's close to that at the order of the percent level, but it's not exactly scale invariant. Okay? And we will talk about this slight breaking of scale invariance later. But for now, I just want to highlight that this is very close. It could have been order 1 different from scale invariance. That's not the case. It's very close to a percent level scale invariant. And in fact, later we will see that inflation will demand that it's not exactly scale invariant, because that would also be a disaster. If the universe was exactly scale invariant, time translation invariant, then it wouldn't be evolving. And so it would be time translation invariant forever. So there needs to be a breaking of time translation invariant, of course, that makes it cosmology and that makes it an evolving universe. And that's what inflation essentially does. It is the symmetry breaking phenomenon that takes something like the zeta space, which is time translation invariant, has no cosmology, and makes it an evolving space-time with a slight evolution in time. But always close to this zeta evolution, which controls a lot of its features. Okay. Yeah, and actually, so this y-axis here is just the amplitude of gravitational tensor fluctuations that just allows me to make this a 2-dimensional plot. It's not so important for this discussion at this point. So this suggests that the fluctuations were created in a phase of approximate time translation invariance, which we often call inflation if it's an expanding universe. Okay. Any more questions? Okay. So one way of defining inflation is therefore a phase in the early universe where the expansion rate was nearly constant. So the expansion rate is defined as follows. So we have the scale factor, which describes kind of the physical relationship between co-moving and physical distances in space. As the universe evolves, that is a monotonically increasing function of time, a of t. And then we can calculate the fractional rate of change of the scale of the universe. Okay, and that gives us the Hubble rate, and it could possibly be a function of time. And so inflation tells us that it was a function of time, but it was very nearly constant. Yeah, so the expansion rate of the universe being nearly constant. And it's the only physical scale if it is a constant, then h is the only physical scale in the early universe. Okay, so everything is therefore scale invariant. Therefore, yeah, there's nothing that picks out scale if h was a constant. And then because h is during inflation going to be slowly evolving in time, there will be a slight breaking of that time translation invariance or the scale invariance of the fluctuations. Okay. For the time being, we're going to work in an approximation where this Hubble rate is really nearly constant. If that's the case, then we can integrate this expression and we get an exponential scale factor. So we get exponential expansion of space. Okay, and that's of course what we always hear about inflation being. And the geometry of the background geometry of the universe will be nearly de Sitter space. It's exactly de Sitter space if this expansion rate h is a constant. But of course, as I said, inflation needs to end, so there has to be some time dependence, and we usually parameterize it by the rate of change of the Hubble scale as a function of time, normalized with respect to itself, so it's dimensionless. And so we get this what's called the slow roll parameter epsilon as this h dot over h squared dependence. Okay, and that has to be much less than 1 in order to stay close to the scale invariant solution. So what you hear most of the time is that this is generated by a field that's rolling down a potential very slowly, and the potential has a flat region, and in that flat region there's a one-to-one correspondence between the shape of this potential being nearly constant and acting like a cosmologically constant in the Einstein equation, and the expansion rate of the universe being nearly constant. Okay, h squared is proportional to the density squared in the Einstein equations. So if the potential is constant, the density of the field is constant, then h is also nearly constant. Okay. But I want to highlight that this is not the only way of getting a time-independent Hubble rate. And so we want to think of inflation in a slightly broader context, where there's some mechanism, some quantum field that generates nearly constant energy density and nearly constant Hubble rate. Okay, that might be a weakly coupled field, but it might be something else, some more strongly coupled phase. Yeah, at this point, it's not so essential. Okay. Actually, is there a clock here? I'm somehow losing track of time. Oh, can you tell me how much time did I use, sir? Sorry? Okay. Yeah, I'm going rather slow, but okay. Let's see how far we get in this, and then we continue in the afternoon. Okay, so I want to actually describe inflation now in kind of the broadest possible sense that I kind of know of. Not assuming a fundamental scalar field and a potential, but just in a level of what it does to the background expansion, namely that it breaks this time translation symmetry. Okay, so I think the one nice way of thinking about inflation is as this symmetry breaking phenomenon. Okay, there was a phase in the early universe that was close to de Sitter space, and that phase got broken by some order parameter. Okay. And so, of course, whenever you have symmetry breaking, you should also expect to get a Goldstone mode that describes that symmetry breaking. And then by Goldstone's theorem, that Goldstone mode is a scalar. Okay? So there's one preferred scalar mode that I'm going to call pi here that describes the breaking of time translations in the early universe. Okay? And it's this Goldstone mode pi that I want to use as a way of seeding the initial fluctuations in the universe. Okay? Of course, we are always operating in a gravitational theory, so there's a second degree of freedom, which is the graviton that's always present. So in my mind, the minimal scenario of inflation as a symmetry breaking phenomenon has these two different fluctuation modes. The Goldstone mode of spontaneously broken time translations, okay? And in the standard slow roll inflation, this would come as fluctuations of a fundamental field, but it doesn't have to be. Whatever created the background h of t will always give rise to a single scalar fluctuating degree of freedom, okay, pi. And then there's the graviton, okay? Those two modes you will always have. In more complicated scenarios, you might have more things, okay? But let's just stick on the things that we know have to exist and see how far we get with just those fluctuations. In fact, of course, where I have fluctuations in cosmology are gauge, or in gravity are gauge dependent. And so we can go to the so-called co-moving gauge, where there's no fluctuations in the matter sector, so I'm actually removing this field pi. I'm looking at time slices where whatever order parameter created the breaking of time translations in the matter sector got removed. Okay, and then it gets pure. It's completely moved to the metric. So we sometimes say this is eaten by the metric, this Goldstone mode. It's sometimes also called the inverse Higgs effect, yeah? Where you can go to a gauge where there's no fluctuations in the matter, yeah? And all of the fluctuations were just purely intrinsic to the metric. And so now the metric has two fluctuations. It has an isotropic fluctuations in the spatial part, you know, which creates a stretching and squeezing of space that's kind of isotropic. And it has an anisotropic, transverse traceless component, which is the graviton. Yeah? So from that, in that particular gauge, it's also very clear that there's two fluctuations that you can have of the spatial metric. An isotropic breathing of the metric, which is this, and then it becomes, the name for it is the curvature perturbation zeta, and an anisotropic graviton fluctuation. And this curvature perturbation zeta is just linearly related to the initial Goldstone fluctuations in an arbitrary gauge. Yeah, or in any gauge that's not the co-moving one, okay? So in the following, we will think of zeta and pi as being equivalent, okay? We can describe fluctuations in one gauge where they look like Goldstone modes of the matter sector, or we can go to the specific gauge where there are no fluctuations in the matter sector and all the fluctuations are in the metric. And then we call it the co-moving curvature perturbation, okay? Is that clear? Okay. So a lot of you who have studied cosmology and cosmological perturbation theory, I'm sure will have seen this zeta, okay? Okay, and I will switch back and forth between pi and zeta, yeah? And you can always just think of them as being related by a constant rescaling, which is given by the Hubble parameter. So now let's go back to pi. Because it's a Goldstone mode, the action of this field is highly constrained by the nonlinearly realized symmetry that's still present. Yeah, it's spontaneous symmetry breaking, and spontaneous symmetry breaking means there's still structure in the effective Lagrangian of the fluctuations. Yeah, there's coefficients that are nonlinearly related that, in the absence of spontaneous symmetry breaking, you know, would be independent, but are now getting linked to each other. And so that's precisely also what happens here. So there's a free part of the action, which is just the kinetic term of the field with some overall normalization. That's the symmetry breaking parameter of the theory. Notice that this is proportional to h dot. So in the zeta space, this would vanish. And it makes sense. In the zeta space, you have no symmetry breaking. There's no Goldstone mode. And this kinetic term here becomes degenerate, okay, with zero coefficient. And so you can also see this if you just go back here, take the fluctuations of the inflaton field, defined as such. Yeah, it's just a shift in time of the inflaton field minus its background value. Expand in powers of this shift in time pi. You would get this leading term. And in that case, this coefficient here would just be the background speed of the field, phi dot squared. Okay? So there's something proportional to the speed of the field. The speed of the field is kind of the symmetry breaking scale of the theory. And so the free theory is just that. Okay? So if you were to take this standard slow roll Lagrangian and expand it out, you would get first such a term. And then at leading order and slow roll, actually, you would get no interactions for slow roll inflation. But more generally, this Goldstone field can have interactions. In fact, an infinite power of interactions set by some scale. But as you also see here, these interaction terms come as a linear combination of field fluctuations with different powers, which is precisely an origin of this nonlinearly realized symmetry that I mentioned. Yeah? So in particular, if you were to take this kinetic term here, expand it in fluctuations, you get a linear term that looks like this, and you get a quadratic term that looks like this, and the two are not independent because they came from the same operator, which was just the kinetic energy of the field, the underlying fundamental field. Okay? But there is a more general way of rationalizing that this has to happen. You don't have to assume that there was a field phi to begin with. Okay? And in particular, if you're not close to the slow roll attractor, then these fluctuations can have a large sound speed. So notice here actually that the leading term starts at n equals 2, which is, so you take this operation here and square it. You get phi dot squared, which will change the kinetic term of the field, which is generating for you a non-trivial sound speed of the fluctuations. Because it changes the phi dot squared coefficient, but it doesn't change the grad phi squared. So there's a breaking of time and space derivatives, which is characterized by a sound speed of the fluctuations, which is not the speed of light. Okay, so that can happen now because we have broken time translations and therefore we have broken Lorentz symmetry in the process, and so the fluctuations do not have to evolve with the speed of light anymore. There can be a non-trivial new parameter, which is the speed of sound. All right. Okay, we will get back to the speed of sound later, okay? But for now, you can just have in the back of your mind that there's this effective Lagrangian for the field, and we can work with this effective Lagrangian. And at first, we're just going to work with the free theory anyway. Okay.
저기 우리 지금 상황이 그래서 처음 6명 나왔고 2명 디클라인 했고 그러니까 제가 듣기로 김성준이라는 친구는
Okay.
얘기가 있었죠. 아 그게 보내신 게 얼마 안 됐구나 사실은 친구는. 아 온다고 왔어요? 아 방금.
Okay, I'll continue and speak over the person.
우리한테 사실은 일요일까지 얘기를 해줬어요. 토요일까지 얘기를 해줘야 되는 건데.
I don't even know where it comes from.
보내? 전
Okay. Yeah. So, but the basic picture is that quantum fluctuations in this Goldstone mode will produce the initial conditions and the density fluctuations in the early universe. And so I just want to sketch for you, because if you have not seen this calculation before, it's a sin. Okay, and and it's an extremely important calculation that shows you how the primordial fluctuations were created in this phase of inflation in quantum field theory. I'm just going to sketch for you what this calculation looks like. It's extremely simple. And so let's actually derive these initial conditions. So we're going to start from the quadratic action of this Goldstone mode. Okay. If you like to think about slow roll inflation, you could just start from the kinetic term of the inflaton field, and everything would work out the same. You just have some test scalar and a quasi-de Sitter background, and we're just going to calculate the 2-point function of this test scalar in a quasi-de Sitter background. I've transformed here to conformal time that I'm calling tau to distinguish it from t, which is the physical time. And I'm going to denote time derivatives with respect to tau by a prime, while time derivatives with respect to physical time are over dots. Okay, so I hope to keep this convention throughout. So then we have previously seen that in physical time, inflation was an exponential function of time. Yeah, the scale factor was an exponential of time. In conformal time, it becomes this inverse power law. Okay, if you have never seen this before, you should prove this to yourself. Okay, and so the Sitter space in this conformal time coordinate has this dependence on time. Okay, and so we're going to use that in here. Okay, there's a measure factor that comes from the square root of minus g in the action. When we evaluate this in the Sitter space, there will be 1 over tau squared that appears up front. And then there's a constant parameter here. So the only time dependence in the action is the 1 over tau squared. It's the 1 over tau squared, in fact, that gives us scale invariance. Okay, if this was a different function of tau, then we would not get scale invariance. So the only dependence on time came from the measure, came from the scale factor. No physical quantity in the universe actually dependent on time. Okay. Now it's convenient to actually redefine the field and define the so-called canonically normalized field. So let's take this time dependence and factor it and take it out by defining this new variable that is just proportional to the scale factor times a constant times the Goldstone mode pi. All right. What this does is that it removes the a squared in front of the kinetic term, and that's why we call it canonically normalized. So what you see here is that there's a kinetic term for the field, there's a gradient squared for the field, there's a minus sign between them. So the free part of the field, this first part of the field, is just like a scalar field in Minkowski space. There's now no measure anymore. So this is just like the integration over volume, space-time volume in Minkowski. And so this part of the action is just what you would get for free field in Minkowski. Yeah? There's just one new term, the time dependence of the evolution tells you that there's a mass term for the field now. Although you started with a massless field, the Goldstone here, when you redefine to go to canonical normalization, you generate the mass for the field. A double prime, so it's a second derivative of the scale factor divided by the scale factor, which gives you 1 over conformal time squared as a coefficient here. Okay? So of course, given the action, you can calculate the equation of motion, and in Fourier space, the equation of motion would be this one. So it's an acceleration plus a k squared, which comes from the gradient squared, the Laplacian. This is what you would get. So if you dropped this term here, this is what you would get in Minkowski space. Okay? Just a simple harmonic oscillator for every Fourier mode k. And now the fact that we're living in de Sitter space adds this extra mass to the field as a function of time. So it's a harmonic oscillator with a time-dependent mass. Okay? So the problem we're trying to solve when we calculate quantum fluctuations in the early universe is just the problem of what do quantum fluctuations of a harmonic oscillator with a time-dependent mass do. Okay? So before this can actually be solved fully analytically and so on. Yeah. The path integral measure. Let's see, actually. So I'm now going to involve this, calculate this in just canonical quantization. Okay, there's no path integral measure at this point. Okay. In the afternoon, in fact, we might have time to rederive it using the wave function of the universe, where we actually are going to calculate this using a path integral. And then maybe you can voice your concern there and see whether, yeah, we will get the same answer. So I suspect there's nothing going on there. But maybe we can pinpoint precisely where you're worried something might be going on. Okay. Here, I'm literally going to do the thing that you would do in ordinary quantum field theory, the first course you take, where you just canonically quantize fields in momentum space. And the only subtlety is that now there's a time dependence in the coupling or in the mass, and so we have to carefully treat that as a function of time, and things will change, and we have to worry about the vacuum state of the theory a bit. Okay? So as I said, this equation actually can be solved, has an explicit solution, so we could just solve it and then calculate the two-point function and be done. But let's just get some intuition by taking limits of the solution, okay? So the first limit we can take is we can go to very early times or short distances. What this means is that we take this combination k times tau with a minus sign and make it very big. I should have said that conformal time during inflation ranges from minus infinity at early times to 0 at the infinite future. Okay? So this conformal time is actually always negative. And then in the hot Big Bang, this conformal time is always positive from 0 to some finite value. And so that's how inflation solves the problem that we had at the beginning, that it extends this conformal time to negative values, and then it attaches it at 0 to the hot Big Bang. But since we're now talking about inflation and the phase before the hot Big Bang, this conformal time is negative, and it gets larger and larger at earlier times. Okay, so going to early times means making this combination here, this dimensionless ratio, large and negative. Large because I put the minus sign here. At any given fixed moment in time, you can also think of this as going to very short distance scales or large wave numbers. Okay, so that's an equivalent way of stating the limit. Okay, so either you take fixed wave number and you just go back in time, and so then that wave comes deep inside of the horizon at that early time, or at a fixed moment in time you look at a wave number that has very short wavelength, so that it's also inside of the horizon. So in that limit, you can see that this k-squared term will dominate over this time-dependent mass. And if we drop the time-dependent mass, it just reduces the equation of a simple harmonic oscillator. Okay? So it just reduces to flat space quantum field theory, and we can solve this theory the way we would just in Minkowski space. Okay? So that's at early times, and we know that the solutions of this harmonic oscillator are the following. So e to the plus or minus ik tau, with an overall scaling that goes as 1 over the square root of 2k. That's why you shouldn't use slides. Okay. Okay, then the second limit, the opposite limit is to go to very late times, where this combination minus k tau goes to 0. Okay, that's approaching the end of inflation, which is defined at tau equals 0. Or at a fixed moment in time, this just means that the wave number becomes very small, and so this is a mode that is stretched outside of the horizon. So then the opposite happens, that this gradient term is small, and we're dominated completely by this time-dependent mass, and you just get power law solutions of time, conformal time, yeah? So now there's a growing mode that decays in time. Sorry, no. It actually grows, sorry, because tau goes from negative in large value to 0, and it's an inverse of tau. So this is an honest-to-God growing mode. It gets larger and larger with time, while this one is decaying, yeah? If I took the solution and I go back to the initial Goldstone mode, then this growing mode corresponds precisely to the constant growing mode that I claimed has to be there in order to explain phase coherence. Yeah. So having 1 over tau here for the growing mode is precisely what I need in order to get a pure constant for the physical Goldstone mode or the density fluctuations in the late universe. Okay. Okay, this is actually what I'm saying here, is that if you go back to the field pi or to zeta, you have to divide by the scale factor. Remember, the scale factor was 1 over tau, so inverse of the scale factor is just tau. Tau times tau to the minus 1 is just constant. Okay. Okay, any questions about these limits? Yeah, so there's 2 limits, very early times or very late times, but there's also a full solution that connects the early time limit to the late time limit, which is this one. This is just the most general solution to the equation of motion. It has 2 solutions with two free integration constants, C1 and C2. We call this solution the positive frequency solutions because it's e to the plus ik tau. And we call this solution the negative frequency solution, e to the minus ik tau. And we will see that the inflationary initial conditions, the vacuum state of the harmonic oscillator is the one with purely positive frequency. So I'm going to argue in the next slide that the ground state solution of this harmonic oscillator, which we define at very early times, is the one where C2 is 0. Okay. Okay. Yeah, maybe I can give you a warning when I have 10 minutes left or so. Okay, thanks. Okay, so then we can just go through now that we have the mode functions, we know how the field classically evolves. It's straightforward to quantize it, and I'm just going to rush through it quickly because I'm sure you have seen this before, and you can just read through it in the slides later or ask me if any of this is not completely familiar. So you start with the classical quadratic action. You define a conjugate momentum of the field, which is just the kinetic energy of the field in this case, because it was canonically normalized. Okay. We then take these classical fields, U and P. We promote them to quantum operators by putting hats on them. Okay. We then impose these commutation relations between a field and its conjugate momentum at a fixed moment in time. And because of locality in space, this commutator has to be proportional to a delta function in space. Okay. So, only coincident points, have this non-zero commutator, and any 2 points that are separated in space are commutating variables. Okay, this is what this commutator is telling us. Then we define a mode expansion of the field operator. So we split this operator into non-Hermitian, so-called creation and annihilation operators that you've all seen before, and mode functions that are a function of time that satisfy this classical equation of motion that I showed you earlier, and for which we have a solution. Okay, and then there's a intrinsic normalization of these mode functions that is set by the fact that these annihilation and creation operators have unit magnitude in Fourier space. Yeah. So by demanding this and demanding that it also satisfies the canonical commutation relation, I'm putting one constraint on the so-called Wronskian of the field. Yeah. There's a combination of the time derivative of the field and its value. That Wronskian of the field now has some fixed norm, just in order to normalize the creation and annihilation operators correctly. Okay. So this is literally just following a nose of your standard textbook in quantum field theory. You define the vacuum state and also the way that you all know about. And so now then there's just this question about, we had these 2 solutions with 2 independent constants, C1 and C2. How do we pick the physical solution that we think corresponds to the ground state of this harmonic oscillator at early times? And so there's an exercise that's useful to do is just to calculate the Hamiltonian of that theory in this predefined vacuum state and minimize that expectation value of the Hamiltonian. Okay, so you calculate the Hamiltonian in the ground state. It will depend on these 2 parameters, C1 and C2. And you can show that unless you set C2 equals to 0, this expectation value will be not a minimum. Okay? So in order to get a minimum of the expectation value of the Hamiltonian in the ground state, you need to pick one of the solutions and not the other one. Okay, and we call that the positive frequency solution. Any amount of negative frequency that I add to this solution will just raise the energy of the harmonic oscillator in the ground state at early times. So if I'm demanding that these fluctuations start their life in the ground state of the harmonic oscillator in flat space, which is the limit that I'm taking when I'm going to early time, I'm picking out a unique solution, which is called the Bunch-Davis vacuum or the Bunch-Davis mode function. Okay. Okay, but now everything is specified, and I can just calculate the two-point function. So if I calculate the two-point function of this operator in Fourier space, yes? How was A defined? AT. AK, yeah. So AK was defined when I was defining this mode expansion. So there's a mode that I've written in position space, but I'm doing a Fourier transform. So this, everything in brackets here, is the field operator has a function of tau and a function of k, vector k. Okay? Coordinate dependent. Yeah, the whole field is coordinate dependent. So now we're doing this in a fixed gauge. Yeah. So yeah, this calculation is done in a fixed gauge. That's a good question. And so. Yeah, I think for the free theory that coordinate dependence, because we're defining the vacuum relative to the homogeneous background, which is kind of picked out by this preferred slicing, time slicing introduced by inflation. Yeah, and so there's a unique de Sitter invariant vacuum, which is the Monch-Davis vacuum. You could have non-de Sitter invariant vacua. Sometimes they're called alpha vacua, which are one parameter deformations around the de Sitter invariant vacua. They have issues. They're not ground states of the Hamiltonian at those early times and so on. But it's a good question. Let me think about it a bit more. Yeah, I think we're implicitly using a fixed gauge here. But I think if you do gauge transformations, it will just maybe affect kind of higher order interactions or so. I don't think it affects the free theory result. Okay, thanks. Yes? Yes. Well, it's always what we do in semi-classical. I mean, we always do quantum field theory on a fixed classical background. This is the best we can do. Yeah. Of course, strictly speaking, yeah, the background is also quantum, and we need quantum gravity to this, and all of that stuff. Okay. But to the degree that Hawking radiation is a well-defined calculation around the Schwarzschild background, this is the analog. This is exactly the same. It's the Hawking radiation calculation for a de Sitter background. And so I agree with you, at a conceptual level, you could worry that we're doing this split into a kind of a classical background and small quantum fluctuations. As long as the fluctuations are small, I think that's okay. There are extreme regimes of inflation, like eternal inflation, where the quantum fluctuations will start to compete with the classical rolling of the field and be large, and the fluctuations become order one. In that regime, I would sympathize with you even more that probably that calculation cannot be trusted. Yeah. But yeah, in the sense that we can do any QFT in curved spacetimes, we always are doing it in such a split of having a fixed classical background and quantum fluctuations that are weakly coupled and small, living on that classical background. There was another question, yeah. Okay. To keep the inflaton light? Yeah. Actually, I think it's this Goldstone symmetry. So the reason the inflaton is light here, the inflaton fluctuations are precisely massless in the limit where the symmetry is restored. So it's technically natural to have a light Goldstone mode. So that's in practice, and thanks for the question. Yeah, I think that's precisely what makes this language so nice. So for the inflaton, in fact, you have to work hard. For the background, you have to work hard to keep the fundamental scalar light. And you need to impose an extra global symmetry, and then quantum gravity doesn't allow you to have global symmetries that are exact and all that kind of story, and becomes very subtle. Okay. Here we have separated the problem. We assumed there was some process, some underlying condensate that gave us h of t as a function of time with a small variation of time. How that is generated is an important problem for the microscopic origin of that theory. But once you have something like this, there are Goldstone fluctuations that are nearly massless. Okay? So in some sense, okay, it's a chicken and egg problem. You still need to explain what generated the nearly time translation invariant expansion. Once you achieve that, the Goldstone modes are guaranteed to be massless. Okay? But yeah. Yeah. Yes. Uh, Yeah, I would say the minimal scenario is where you don't have these additional fluctuations. You just have the Goldstone mode, and you try to see how far you get like that. In fact, one other nice feature of the Goldstone mode is that it generates so-called adiabatic fluctuations. So adiabatic means, and it's maybe easiest to explain here. So imagine you take some background field, which I've called phi, but it could also just be some density, some order parameter. It doesn't have to be a fundamental field or anything. And you take, and it's at 0th order, this field here is homogeneous. And now you generate fluctuations by just taking the time coordinate of that field and shifting locally that time coordinate of the field by some by spatially dependent variable pi. That generates for you a fluctuation in the original order parameter, so delta phi, of a very specific type. It's not the most general fluctuation that you could get in phi. It's what we call adiabatic fluctuations, yeah, where there's just and it seems to be the case that, and then this adiabatic fluctuation mode gets transferred to all the other fluctuations in the universe. For example, the baryons, the photons, the dark matter. They are all synchronized. The fluctuations in space are coherent between the dark matter, the baryons, and the photons, because they all came from this common pi source. They were all generated in the same way, that there was some clock that shifted their waves. So that's something very special, but we have seen this in the sky. So the fluctuations that we see in the sky have this adiabatic nature, that all the different matter fluctuations are synchronized in space. Yeah? If you have additional fields that fluctuate, that is not the case anymore in general. Additional light field will create so-called isocurvature fluctuations, and then we have to work a little bit harder to remove those isocurvature fluctuations. So it creates trouble for you. Okay, it's not actually very hard to remove them because thermal equilibrium, for example, does it for you. So it's not. I wouldn't say that this is a kind of a showstopper for, but it is a nuisance. And yeah, I think a nice feature of the Goldstone mode is that it automatically creates for you adiabaticity. Okay. Okay, where were we? Yeah. So sorry, I was here, and maybe I can stop on the next slide. So I was here calculating the power spectrum. It's now very easy. You just substitute the mode expansion of the field. The annihilation operator annihilates the vacuum to the right. The creation operator annihilates the vacuum to the left. So then you're just left with two terms. This term here in the first bracket, and this term here in the second bracket. You use the commutator for the A operators, and you find that the power spectrum is just proportional to a delta function, first of all. That's just the translation in space invariance of the background, and the square of the mode function, okay? And that square of the mode function we then just call the power spectrum, P of K, okay? So given that I know precisely what this mode function is, I can just square its absolute value, and that tells me what the initial power spectrum is, okay? And so when you do that and you rescale by a factor of a squared to get back to the power spectrum for zeta, this is what you get, okay? If you then go to late times, the time dependence disappears completely, as it had to be because of time translation invariance of the background. And so you get something that has a coefficient that's constant in time, and it scales with the Hubble parameter and the breaking of the symmetry epsilon, okay? So actually, and then 1 over k cubed for the momentum dependence, yeah? Right? So this 1 over k cubed is precisely what we want to get for the power spectrum if we want to have scale invariant fluctuations in space. So maybe as an exercise for you, if you take the Fourier transform of this power spectrum, this becomes a log of spatial separation in position space. And it's this log that really is reflective of an underlying scaling symmetry in space, okay? So in Fourier space, we actually really want to get 1 over k cubed. Any deviation from 1 over k cubed is a non-scale invariant spectrum. And so this is telling us scale invariant. Sometimes this is described by the fact that people define an alternative power spectrum where they take the power spectrum we just calculated and they multiply it by k cubed. Then you get something which at first, at leading order is just independent of any value of k, okay? And then with a small breaking of time translations, you get this spectral tilt ns minus 1, okay? maybe my last comment before I stop, if you look at the amplitude of these fluctuations, they have two important factors. One factor is just h squared over m Planck squared, okay? That's related to the zeta temperature, or the inverse of h would just be the Hubble radius during inflation, or in the zeta space, in units of the Planck scale, okay? And in fact, if I had kept h bars explicit, it would also have been proportional to an h bar to show you that this is a quantum two-point function. And then there's a 1 over epsilon, which is, as I said, the parameter that breaks the symmetry. So if I'm taking the limit of going to exact de Sitter space, yeah, epsilon would go to 0, and this entire power spectrum blows up. Yeah? Which makes sense because this is the power spectrum for zeta, and zeta becomes pure gauge in de Sitter space. And a signature of the fact that something became pure gauge is that, on the one hand, we saw that the coefficient of the Goldstone action went to 0, which then shows up in the power spectrum as a divergence of the power spectrum. So zeta as a variable just becomes ill-defined. The zeta space has no such gravitational fluctuations. And when we break the symmetry, we have this order parameter that shows up in the power spectrum. Okay, so maybe actually here I have a summary slide which wasn't planned, but but works well here. So here I've just summarized the entire story that we told today. And yeah, I can take questions for this, and then maybe we stop here. Thanks. Yeah. What determines the breaking scale? Yes. Actually, in the next lecture, I'm just 2 or 3 slides away from that, actually explaining that. Maybe if the person can hold on, I can just say something quick, and then we will actually see it in 2 or 3 slides. So for slow roll inflation, what determines the breaking scale is the speed of the field rolling, phi dot. If you don't have a fundamental field, what determines the breaking is m Planck squared h dot. It's the coefficient in front of the kinetic term of the Goldstone field. Okay? But we will see it in 2 or 3 slides in the afternoon. Other questions? Maybe I can, sorry. Yeah, yeah, let me then take the opportunity to just mention 1 or 2 things on this summary, because yeah, if you haven't studied this very much, I think 1 good exercise for yourself is to try and explain features of this diagram here. So for example, what I'm trying to illustrate here is that, so there's as a function of time, I'm looking at different scales, okay? And I've drawn in 3 different colors, 3 different wavelengths of fluctuations, yeah? And scale goes up, so red is the longest wavelength fluctuation. So in the initial power spectrum, this is to the left because it's inverse of wave number. And blue is the shortest wavelength fluctuation. And then in gray, I've shown you the evolution of the Hubble scale, or, yeah, the physical horizon scale, in the late universe, or the Hubble parameter during inflation. And so what you see here is that during inflation, inverse of h is nearly constant, because the universe is nearly de Sitter space. And then as the universe reheats and the hot Big Bang starts, which is this phase, the inverse of the Hubble rate increases by some function of time, some power law of time. Okay? And these physical scales here, they evolve with the scale linearly with the scale factor, always. Okay? So what this means is that if you have very short wavelength fluctuations, they will cross the so-called horizon, or Hubble radius, during inflation, and then re-enter at late times, just because by the nature of the shape of these curves. Okay? So there are super horizon fluctuations here. There are sub-horizon microscopic fluctuations here. They become classical out here, and then they remain classical when they come back inside of the horizon at late times. And then they get imprinted into, so they evolve as sound waves out here, and they get imprinted in the cosmic microwave background at a specific moment in time. And you can then also, there's a 1-to-1 mapping between these points in the initial power spectrum and the points in the CMB power spectrum, which I've also indicated here by colors. And you can see that the larger scale modes exit the horizon during inflation first, as you can see, as a function of time. First red, then orange, then blue. But then blue enters the horizon first, and the large scales enters last. as you can see from the entering points over here. So there's a lot of detailed information in this figure, which I encourage you to try and understand. Okay, let's stop here. Yeah. Yeah. No, I think it's a very subtle question which people have looked at. I'm just not expert enough to, or I need to remind myself what the precise answer is. So one answer is that in cosmological perturbation theory, all these gauge issues are only relevant outside of the horizon. So outside of the Hubble radius, out here, yeah, it's indeed very subtle and gauge dependent. For example, there's even just the matter fluctuations evolve differently whether you're in Newtonian gauge or in co-moving gauge. Yeah, in one gauge they're frozen, and the other gauge they're not, and so on. So outside of the horizon, there are all these subtleties. These subtleties about gauges all go away when you go to short scales. So when it comes back inside of the horizon, then gauge artifacts are small. And if you wanted to be really sure, you then ultimately just relate to some gauge invariant observable. Yeah. And so I've not been detailed enough to kind of track these gauge issues, but you could either define gauge invariant observables throughout, and then you can prove that on short scales, even if you were to pick a specific gauge, those gauge dependent observables approach the gauge invariant answers on small scales. I think that's, and then, okay, there's some math behind this, but the physical feature is that on short scales, everybody agrees. And on large scales, these subtleties are there. But we're never seeing those. So it's a fortunate coincidence that, well, it's not a coincidence, it must be like that, that the gauge dependence is only in the things that we can't see. So super horizon modes we cannot actually observe, and there's an ambiguity in how we define these super horizon fluctuations, yeah? But then as soon as these fluctuations come back inside the horizon and we can start to observe them, we all start to agree. Yeah? And it's a physical feature that observables are well defined. Yeah. Okay.
계시는데 한번 말씀드려 볼까요? 아, 여기서 직접요? 그러면은 Hello. Yeah, thank you. Thank you for the introduction, and then thank you for the invitation to speak here. I'll be talking about the quantum entanglement in the context of many-body quantum systems. And then in particular, I will focus on the multipartite entanglement, and then I think it's a bit complicated subject, even in a few-body quantum systems context. But there's some interesting new directions emerging in this context. I try to mention some of these recent developments. And since I'm a condensed matter physicist, and then I think the audience is quite broad and mixed. So I may be speaking mainly in the language of condensed matter physicists. So if you don't understand terminologies or some notions, maybe it's just best you to ask. But before moving on to the multi-party or multipartite entanglement, I just want to say some very quick introduction to just a quantum entanglement and many-body systems. So let me try to write quantum entanglement. Oh. Okay, I hope it's okay. So quantum entanglement and the many-body physics, or I think depending on in which community you are in, people may be interested in let's say understanding many-body physics from the context of quantum entanglement, or maybe people are just interested in coming from maybe the quantum information background, maybe interested in applying quantum entanglement or quantum information theoretic thinking to quantum many-body systems. But either way, this type of way to consider or discuss many-body systems becoming increasingly popular and important in recent years of many-body quantum systems. There are various aspects for this. One aspect is that quantum entanglement may be a kind of useful concept to understand or to characterize quantum many-body systems. So it maybe plays a role of a order parameter, or not in the conventional sense, because we have a order parameter for defined from the local correlation functions to detect symmetry breaking phases. But as the quantum many-body physics developed, we are discovering more interesting phases or states in quantum many-body systems where order parameters may not be enough to characterize very intricate quantum many-body wave functions, or in worst cases, there's no local correlation functions we can use to describe these phases. But even in such context, quantum entanglement may be a useful concept, or even qualitatively useful concept to characterize quantum many-body wave functions. I will touch upon the examples where I discuss something called topological phases of matter, where this type of thinking is particularly useful. Another way the quantum entanglement may be useful to understand the aspect of many-body quantum system is that it may be a nice way to organize the degrees of freedom relevant to describe quantum many-body systems. Microscopically, you may have a well-defined like a spans which describe your quantum systems at shortest length scale, ultraviolet scales. But in many-body systems, it is often the case that if you go to the long wavelengths, relevant degrees of freedoms are very different from these fundamental degrees of freedom. And then we may be able to, if we understand the quantum entanglement of many-body wave functions, we may be able to find a very efficient description of quantum many-body systems. And this type of thinking is useful, for example, in numerics. Because it is known that simulating quantum many-body system is exponentially hard on classical computers. So we have to use some trick, or we need some insights to have a exponentially complicated quantum many-body wave functions if we just use classical computers. So, for example, tensor network has been a very useful way to organize the quantum entanglement and degrees of freedom in many-body quantum systems to describe, to have an efficient description of quantum many-body systems. Also, thinking along this line, meaning if we have a if we try to develop a very efficient way of describing quantum degrees of freedom, it is also closely tied to the concept of renormalization group. So this is, let's say, more conventional language to speak, maybe not just quantum, but many-body systems in general. But in recent years, we are finding a way to understand a renormalization group idea using the language of quantum informations. For example, quantum information quantities, such as entanglement entropy or some combination of entanglement entropy, they obey certain inequality, for example, strong subadditivity. And then in simplest cases, we can just use the strong subadditivity to show the monotonicity of renormalization group flow, and so on and so forth. So anyway, it is useful to understand quantum degrees of freedom across the scales, for example. And then, not least, it is also widely discussed in the context of holography. So to understand the mechanism of holographic dualities, quantum entanglement may be a useful concept. I think there's a slogan which is to say that a quantum spacetime may emerge from the quantum entanglement of many-body systems. Okay. So let's speak about the simplest state, which has quantum entanglement. So it is the this type of state for 2 spin 1/2 degrees of freedom. So this is not really many-body quantum systems yet, but it's a composite quantum systems of the simplest kind, a 2-dimensional Hilbert space. So this is the we call it the Bell pair, or maybe EPR pair, and then this is the subject of Nobel Prize last year, and then this is the simplest kind of state which embodies the non-local correlations, which we call the quantum entanglement. Okay, and the real challenge is really that we scale up this type of quantum entanglement idea to system with many degrees of freedom. Here it's just 2 spins, but in quantum many-body systems, we may have a system consisting of many such spins. So it can be arranged in the 1-dimensional lattice, or it can be they can live in higher dimensional lattices. But in simplest cases, it can be defined on the 1-dimensional lattice, and then we have a spins, quantum mechanical degrees of freedom at each site, and then they may interact with each other, and then they may produce interactions, may produce very intricate quantum ground state. Okay, so then as we speak about many-body quantum systems, it is more difficult. It starts to be more difficult to understand the quantum entanglement. It's easy to say, we have a quantum entanglement. But we want to be more quantitative. So then under this simple state, Bell pair, although it's not a fully-fledged many-body quantum state, Bell pair, in fact, is very useful to understand quantum entanglement, even in many-body physics context. For example, we can consider a state, one-dimensional quantum systems whose ground state basically consists of many Bell pairs. So let me draw one such picture. So at each side, so in this example, I had the spin 1/2 degrees of freedom at each side. But instead, let's consider a systems where we have a 2 spin 1/2 degrees of freedom at each side. So at each side, we have a 2 spins. Let's say spin left. Maybe I write this way: spin left, and then spin right. And then we have an array of such spins, okay? And then, in principle, we could have many different quantum ground state for such systems, but a interesting kind of state was discovered by Haldane, and then also by Affleck, Kennedy, Lipstasaki, AKLT. They consider a quantum state which consists of basically many Bell pairs. And then, as it turns out, this is the one of the simplest example of quantum spin liquid in 1D. And then this was another topic, a Nobel Prize topic, I don't know, 6 years or 7 years back. So this state is a translationally invariant. And since each Bell pair is a SU2 symmetric, it doesn't break spin rotation symmetry. So this is a state which is, symmetric, totally symmetric in terms of spin, in terms of spatial structure. And then we say this type of state liquid. Since it's a spin system, we call it spin liquid. But anyway, this is a particular example where quantum many-body system can be built out of a simple constituent, which is a Bell pair. And then, we could reasonably say that we understand quantum entanglement of Bell pair, but we just use this knowledge to build quantum many-body system of this kind, okay? We also understand this state obeys something we call the area law. So we can ask the quantum entanglement between a cluster of spins, a group of spins living on the left to this cut I just introduced here. Let's call it, this is region A. And then there's the complement of A, which we call region B. And then we can ask what is the entanglement between these two groups of spins. And then it is common to define a entanglement entropy by first tracing out the degrees of freedom for region B. So we define a reduced density matrix rho A, starting from the, let's say, some ground state or state. And then we can define a entanglement entropy by this way. And then it is common to discuss the scaling of entanglement entropy for subsystems as we change the size of the subsystem. And in this case, this is proportional to oops, we are here. In many cases, in particular in this case, SA, entanglement entropy for the subsystem, is proportional to the area of region A. And in this one example, it's just a endpoint, since it's a one-dimensional system. So in this case, it's just depends on the number of endpoints A. In this case, maybe 1 or 2. And this can be understood simply from the property of this Bell pair. So when we introduce this something we usually call entangling boundary between these two regions A and B, we basically cut one Bell pair. This entangling boundary cuts through this one Bell pair. I'm using actually this bond notation to represent one Bell pair. And then each Bell pair has an entanglement entropy of log 2. So in this case, if we cut here, or maybe if we cut here too, then we get the contribution of log 2, each coming from the boundary. So this is the simplest example of area law. Okay? And then thinking along this way, we may be interested in states in higher dimensions, for example, 2 dimensions, maybe 3 dimensions, and so on and so forth. And in higher dimensions, stories are a little bit more complicated. In principle, one may consider something like a square lattice for 2 dimensions. And then we can think about having these Bell pairs. They may form some particular pattern. And then we may be able to write down such a corresponding many-body wave functions. So this type of thinking was popular in the early days of high-TC superconductors and also quantum spin liquid. And then based on this type of idea, Anderson introduced the notion of resonating valence bond. It is the it's not a very precise formulation, but this is the first example where people thought about possible quantum spin liquid state in 2 dimensions. Okay. And then we can also understand something like area law in higher dimensions. In higher dimensions, we may define the area, which may be looking like this. In this case, as we cut through each Bell pair, once again, each Bell pair contributes to the finite amount of entanglement entropy. So once again, we may be able to understand the area law by assuming that at least locally there's the something like a Bell pairs, or maybe qubit version of Bell pairs which are locally present, and as we cut through these Bell pairs by the entangling boundary, we may be able to get the area. Okay, so in 2 dimensions, it's a bit, what I said is a bit hand waving, but nevertheless, I'm here just emphasizing the importance of Bell type correlations. Okay, and then one more thing I want to say is the context in the context of non-equilibrium physics. Equilibrium. So for all states I discussed were static. Maybe it can be a ground state of some local Hamiltonian. But nowadays, people are also interested in time dependence or non-equilibrium processes in quantum many-body systems, in cold atoms or more or some quantum simulators. And then we may be interested in discussing the time dependence of entanglement entropy. So for example, popular setup is to start from ground state of some, let's say, the way I'm drawing it, it's a 1-dimensional quantum system. So I start from particular Hamiltonian, H0, but then let's say at time t equal to 0, I change my Hamiltonian to something else, and then I can induce the time dependence or some non-equilibrium process. So my wave function, starting from a let's say ground state of H0, then it undergoes a time evolution induced by a different Hamiltonian. So I get time dependence. So it may be looking like this. And then one may be interested in how entanglement entropy changes. Let's say if you focus on the subregion A, how does entanglement entropy associated to region A changes as a function of time, okay? So this type of experiment has been done, and it is useful to distinguish different kinds of dynamics, integrable or many-body localizing, or some so forth. But you know, it's generically it's a very hard question how quantum systems or quantum wave function changes as a function of time in many-body in many-body setting. It's a very hard time. Had a problem, but there's something some effective description called the quasi-particle picture. where time dependence can be simply described by the free propagation of pair pairs. So the idea is that we start from some quantum state, let's say psi, but then we basically excite. We make some excitations by changing Hamiltonian from H0 to H1. But then the basic picture within this quasi-particle picture is that we basically create many pairs, many pair pairs, and then they propagate in time. In relativistic systems, they just propagate at the speed of light. And then in order to understand the quantum entanglement, let's say, between two regions, region A and region B, basically we just count the number of pair pairs shared by these two regions. You know, this pair pair, for example, this pair pair at some time t may be shared by these two regions A and B, and we just count the number of pair pairs. Okay, maybe it's a bit subtle in quantum field theory because it's, you know, it's continuum systems, but nevertheless we can roughly understand the time dependence of entanglement entropy, or maybe mutual information by following this quasi-particle picture. Okay, but once again, this is another example where a concept of pair pair is just extremely useful, where we can basically use the entanglement structure of 2 spin 1/2 degrees of freedom, and then somehow that appears in various different contexts, in the many body context, or maybe in this case it's even, you know, it's many body system, but we were basically assuming a free propagation of pair pairs. So then we just consider some systems can be understood. For some systems, dynamics can be understood by considering the non-interacting pair pairs. This is not always true, and that's why I'm interested in discussing something beyond pair pairs. But this is just to introduce that pair pairs have been very useful to gain some insight in many body quantum systems. Okay, so by the way, I think if you have any questions, maybe you can stop me. And then I guess so far it's just so broad and so hand wavy. So maybe no questions in some sense. But yeah, but if you have any questions, just let me know. Okay, so my interest today is about the multi-party entanglement, multipartite entanglement. And then once again, like pair pair, we first look at the few body systems, and then we may be able to ask what happens if we consider the many body systems. But first we start from maybe systems with 3 spin 1/2 degrees of freedom, S1, S2, S3. And then we can ask what is the quantum entanglement for systems of these 3 spin 1/2 degrees of freedom. So this problem has been studied. And then people realize that there are basically 2 classes of state we can write down. So one is called GHG state. One of the Nobel laureate is here. And then the other is something called W state. Sorry, I have to erase. So down, up, up. Yeah, this type of state. So yeah, obviously we can write down a pair pair between first and second spin, and then, you know, third spin can be just, you know, just a simple tensor product with the third state in the third spin. Or we could do the same thing for the pair pair for 2-3 and pair pair for 3-1. But these are not new state. These are the state we already know from the example of 2 spin 1/2 systems. But here we are asking what is a fundamentally new state if we have a systems of 3 spin 1/2 degrees of freedom. And these are basically the new state, GHG state, and the W state. So this was, for example, discussed by Dar and the Vidal, and then Sirac in 2000. And then they are interested in basically classifying different classes of state realized in spin 3 spin 1/2 degrees of freedom. Technically speaking, they are interested in a certain set of operations you can do. That's called a stochastic LOCC, a stochastic local operation, classical communication. But anyway, this is a set of, we first define set of local operations. That's, that's some physical operation you could do for systems of 3 spin 1/2 degrees of freedom. And then you can ask, under this set of operations, which states can be transformed into to different state. And then under this, so then you can sort of form equivalence classes under the set of these operations. And then essentially they prove that there are two distinct three-party entangled state, that is GHZ and the W state. Okay, so that's a quantum information theoretic context. So these are new states which emerge once we have a 3 degrees of freedom, not just for the case of Bell correlations or Bell pair, we had the 2 degrees of freedom, but now we have a 3 degrees of freedom, and then these are fundamentally new states, and they are distinct. Okay, one difference between these GHZ and the W states is that GHZ state has a kind of genuine tripartite correlation. If you trace out one of these 3 spins, then the rest is just an unentangled state. Okay. Whereas for W state, it's a three-party entangled state, but there's also the correlation between 2 spins as well. Okay, there's some difference between these states. And then, this is nice quantum information theory result. And then we sort of understand a quantum entanglement of 3 spins. And then this line of research, although I'm not super familiar with, but there it sort of continues. If you have a systems of 4 spins, 5 spins, can we classify all possible quantum entanglement? And then, as far as I understand, this type of story gets complicated as you increase the number of spins. But nevertheless, I will stick with this 3 spin case. And then the kind of question I want to ask is that, like the Bell pair, Bell pair played fundamental role to understand the many-body physics. Okay, I mean, let's say even many-body physics. It's a two-body quantum state, but it was useful to develop many insight into many-body quantum systems. But is there anything we are missing by doing this? So that is really the question. And if we are missing something like this, maybe we are missing something like this multi-party correlations, which appears only when we have a doesn't appear for 2 spin 1/2, but if we have a 3 spin 1/2, new pattern of entanglement emerge. So one could imagine something like this happens even for the many-body quantum context here. Yeah. So the question is, is there multi-partite entanglement in many-body systems or many-body problems? So that's basically the motivation for questions I'm interested in. And then one may be interested in characterizing multipartite entanglement. So how do we characterize? And then maybe there's a interesting physical insight we can gain from this. Yes, question?
Yeah, there is a question in the online.
Yeah.
Is every tripartite entanglement GHZ or W states on the SLOCC for any spin chains, like a spin 1 and spin 3 path?
You mean the, yeah, Q did, right. Good question. That actually, I don't know. I may have looked at this before. But yeah, of course, if you change the local Hilbert space dimensions, story is a bit different, yes. But I think this has been also discussed, yes. I think this paper I'm quoting is, I think this is for specific for spin 1 half. But yeah. Other questions? Okay. So yeah, so I think we don't have a full answer to this question, but we are accumulating some result along this thinking. So here's my outline. Yeah, so I will first discuss some particular quantum entanglement measure or quantum entanglement quantity called reflected entropy that was introduced in the context of holography, but in last few years, I think just in the broad many-body quantum physics context, people started to investigate this quantity reflected entropy. So I will introduce what it is. And then I will discuss quantum many-body systems first in 0D. 0D simply means few-body systems. And then 1D. And then I will discuss 2D systems, in particular topological systems. Okay. And then the next thing I may say something about is the non-equilibrium problem in 1D, like quantum quench, and then we ask how multi-party entanglement changes as a function of time and so on and so forth. So this is my rough outline, and then yeah, I'm not sure how much time I take for each topic, but hopefully I can cover all topics. Okay. Okay. So yeah. So as we discussed, we need some way to characterize multi-party entanglement, and then in particular we may want to have a particular quantity which we can calculate, and then we can say we can learn something from this quantity. So for the few body quantum systems, like a 3-spin 1/2, I think from the quantum information theory perspective, people use various quantities to classify or characterize a quantum entanglement. But unfortunately, not all such quantities are useful, or at least, useful for my perspective, from the perspective of quantum many-body or maybe condensed matter physics perspectives. So we are interested in something which we can compute and define even for many-body quantum systems. So reflected entropy is one such a quantity. So this was introduced by Data and Faulkner in the context of holography. I can say perhaps a few words about connection with holography. But so for now, it's just some quantum information theory quantity, and it is defined as follows. So we are interested in tensor product Hilbert space, let's say HA tensor HB. And then for the multi-party entanglement, I have more Hilbert spaces. Here is just 2, but I first focus on 2, and then I will describe how we use this for multi-party entanglement. But to state a definition of reflected entropy, I just need 2 Hilbert spaces, HA tensor HB. Okay, and then I have some generic quantum state, which may be in the mixed state. So let's call it rho AB. It's a mixed quantum state. So it can be, maybe written in this way. It's a density matrix, but it can be expanded in terms of a some state psi. Psi is a member of HA tensor HB. So we sum over pi. So this is on HA tensor HB, and then pi. As you sum, you get 1. That's a density matrix. So the reflected entropy is defined as follows. So we first enlarge the Hilbert space. So instead of just considering HA tensor HB, I consider a copy of A, which I call A bar. And then I also consider a copy of B, which you call a B bar. So we consider a bigger Hilbert space. But HA and HA bar, they are completely isomorphic to each other. And similarly, HB and HB are completely isomorphic to each other. They're basically just a copy. But then in this enlarged Hilbert space, I can write down a state, which is called purification of rho. And it's defined as follows. It is defined by flipping this bra to ket. So this is now a state in AB. Psi I, the second psi I is the state in A bar B bar. Okay, but sometimes it's convenient to take the complex conjugation, but that is not important. So let me just not write it here. So we just flip this bra to ket, and then to put the square root here. So I have a pi square root. And the purpose of introducing this state is that once we trace out the newly introduced degrees of freedom, so A bar, B bar, then we recover rho AB. Okay, so this process is called purification, because I started from the mixed state, but I write down the pure state. The price I had to pay was that I have to introduce more degrees of freedom. So the total Hilbert space is now bigger. Okay, let me draw a diagram. So it has this type of structure. I started from the Hilbert space A tensor B, but I introduced a bigger Hilbert space. And then I have these 4 Hilbert spaces now. Okay, the purification is useful concept, and then it appears in many places in quantum information theory textbook. But this is a particular purification, such that in that I wrote down my state in the Hilbert space, which is twice as big as the original Hilbert space. For the purpose of just writing pure quantum state, you don't have to have HA bar and HB, which are the same, which are the copy of HA and HB. We can introduce a smaller Hilbert spaces, and then we may be able to still write this purification partner of rho AB. But here we don't be clever about this choice. We just have an exact copy of HA and HB, and then you just write down pure state, and this is always possible. So this is called canonical purification for that reason. Canonical. And then once we purify, we finally define a reflected entropy. I call it RAB. So this is defined as a von Neumann entropy of rho A bar. So if I trace out A bar and B bar here, we go back to the original density matrix rho AB. But instead of doing this, I now trace out B and B bar here. And once I trace out B and B bar here, I get density matrix defined on A and A bar. So that is something I'm calling here, rho A bar. Trace over B bar. And then we just consider von Neumann entropy of this rho AA bar. So this is called reflected entropy. Okay. This was introduced by Dutt and Faulkner in the context of holographic duality, and then one of the motivation for them was that they are interested in the holographic dual of something called entanglement wedge. Entanglement wedge. For example, entanglement SA for the reduced density matrix rho A for the quantum ground state of field series, like conformal field series. It has some geometric description using holographic duality as a geodesic or minimal area surface. But there's a different geometrical object in holography. For example, if you consider this is my 1D space. I'm not drawing time. And then I may be interested in a quantum entanglement between these two regions. And then we start drawing minimal area surfaces for geodesic in this picture. But then this region here is called entanglement wedge, and then we may be interested in this cross section of entanglement wedge. That is this dotted straight line in this case. So Dutt and Faulkner was interested in the holographic dual of this cross section, entanglement wedge cross section, and then they found out basically that reflected entropy is given by the 2 times entanglement wedge cross section. I should say minimal, but anyway, cross section of this entanglement wedge in unit of 4 times G Newton. Okay, so that was the. I think it's kind of interesting entanglement quantity because it was invented purely in the context of holographic duality, but now we just started to use a reflected entropy beyond the holographic context to study many-body quantum physics. So maybe it's a contribution from a holographic community to quantum information theory in some sense. Anyway, so I will be interested in this reflected entropy, not necessarily in the holographic context, but just broadly in the quantum many-body systems. And for my purpose, since I'm interested in a multi-party entanglement, I may have a space regions, let's say A and B and C, and then to make use of reflected entropy, I first trace out one of these regions. Let's say I trace out region C first. Even though I could start from a pure state psi supported on ABC, and then I may be interested in a multi-party entanglement in this state. But then to make use of reflected entropy, I first trace out region C. Then we get mixed quantum state on AB. And then for the mixed quantum state AB, we can compute, we can define the reflected entropy. And then idea is that we may be, by looking at the behavior of this reflected entropy for rho AB, we may be able to learn something about the multi-party entanglement of this pure state psi ABC. Okay? Any question for the, yeah. Yeah. Yeah, so EW is this cross section. Yeah, this region, yeah. Yeah, sorry, I didn't say that, yeah. Or maybe people say EW is this region, and then we are interested in cross section. I guess common notation is that EW is a cross section of this entanglement wedge region. But anyway, here it's EW is just the length of this cross section. Question? Yeah. Yes. Yeah, this is particularly associated to canonical purification. Yes, and then yeah, so there's similar quantities called a entanglement of purifications, which does not require a canonical purification. But that's more difficult to compute, and that's interesting on its own right. But I think I will mostly focus on the reflected entropy for the simplicity of calculations. Yeah. Yes. So this comes, I think, I forgot precisely, but this too comes from the fact that, naturally comes from the fact that, you double the Hilbert space. Yeah, so this too is necessary here to make a holographic dictionary, and then that's basically coming for the way we construct it, doubling. Yeah. This is a result. Yeah, this is a result. Yeah. So this is defined just using a quantum many-body physics language. EW is also defined just by using geometry, but then this factor 2 is important. And if you consider different quantities, there may be some, so for example, there's also the holographic dictionary between other entanglement quantity called entanglement negativity, and it's also related to entanglement wedge cross section, but then you get the different coefficient. So yeah, coefficient is kind of carefully put here to make, maybe I should say this is a result. This is not a part of the definition, yes. Other questions?
When you say cross section,
yeah.
so especially when the length of A and the B or area is different.
That's right.
So where do we, how do we
so we have to find the minimum. Yeah. So it depends on the size of A and B, but we are looking for minimal. Another question? There may be quantum corrections. Yes. So I don't know the answer to this question, but of course, the most naive thing to expect is that this is the leading order in 1/G Newton. Yes. Operational. Good question. So I'm not sure. In some sense, so just to make sure, in some sense, so I think what he's asking is there like interpretation of this quantity in terms of operations we can do. That I'm also not sure. This can be interpreted as a conditional mutual information between A bar and B, and then perhaps we can convert this into like a number of qubits shared between A bar and B. But it's conditional ones. I'm not completely sure. But roughly speaking, that may give some interpretation. Yeah. Yes.
Yeah, there is a question from the online. Dr. Mori. He asked, if I remember correctly, reflected entropy is equal to or larger than mutual information, counting total correlation.
Yes.
Then why do you focus on the reflected entropy, although it cannot be a proper entanglement measure?
Yeah. So. Right, so we call this reflected entropy a entanglement quantity because actually it's not entanglement measure. Entanglement measure has a kind of more strict definition such that it has to be, for example, it has to be monotone, meaning entanglement, something you cannot create by local operations. And then reflected entropy is known not to be entanglement measure. So I don't have a very good answer for this. I think it may be useful to consider more proper entanglement measures, but usually they are more difficult to calculate. In the market, in addition to reflected entropy, sometimes people discuss entanglement or purification, and also entanglement negativity, and perhaps few other quantities. These are marginally computable, but for example, entanglement negativity is entanglement measure, so that's good. But on the other hand, it doesn't have it doesn't show particularly universal behaviors. For example, in the context I'm discussing. So yeah, I don't have a clear answer. I will focus today or in these lectures reflect entropy mostly. I myself studied actually other quantities as well. And then that's interesting, but usually it's just more difficult to compute, for example. Yeah, this is not a perfect answer, but it's a kind of developing field. Okay. Other questions? Yeah, I mean, if you are interested in, for example, negativity, I'm happy to talk about negativity as well, but I will focus on reflected entropy mostly. Okay. Are there other questions? Sorry? Yeah, so yeah, that's right. So, depending on the configuration, this can be disconnected like this, and then cross-section is just 0. And then you can also check that reflected entropy is also 0. Yeah. Right. Okay, so I think it's also related to the previous question, but it's also useful to define reflected entropy minus mutual information, and you can show that this is bounded below by 0, and then usually this quantity is called H. There's some peculiar name for this. Sometimes this quantity H is called Markov gap. But anyway, motivation to consider this combination is that R is always bigger than mutual information. This is a mutual information. So it's good to consider this difference, and the difference is called Markov gap. Okay. So yeah, I may be just interchangeably saying reflected entropy and the Markov gap. So in holography, we are going to discuss conformal field theory just in few slides from now. So it's proportional to C. Yeah, but there's no sub-region dependence. That's important. Okay. Other questions? Okay. So I may be proceeding slowly, but I hope it's okay. So now I want to say something about this use of reflected entropy in multi-party entanglement. But first, I will focus on 0D case, and then, as we discussed, for example, we can consider a two tripartite state, GHZ and W, and then from this classification work, they are not. We cannot go from GHZ to W just by using this stochastic LOCC operations and vice versa. But but can we use reflected entropy to distinguish them? So if you compute this Markov gap for GHZ, it's 0, whereas if you consider W state, it's non-zero. It's something like something of order log 2. I forgot precise number. I think it's roughly log 2, like 1.49 log 2 for the reflected entropy part, and then like roughly 0.49. I hope this is not a typo, but anyway, this is the reflected entropy. It's non-zero, and then this is the mutual information, and then the difference is non-zero. So from the reflected entropy point of view, GHZ and the W states are distinct because GHZ state has a vanishing reflected entropy, but W state has a order 1 non-zero reflected entropy or Markov gap. So this was first pointed out by Chris Akers and Russ. And then their work is a kind of a motivation for the coming works in 1D and 2D, but they discussed this 0D case, and in fact they actually discussed a random tensor network state. Yes, that's a condensed matter notation. So 0 means no space, but time. So this is the 0D result, but this was done by Akers and Russ, but I just want to say they did more. They just didn't just look at 0D case. They study actually random tensor network model of holography, and then they basically found that there's a mismatch between, in terms of reflected entropy, the reflected entropy you expect from holography, right? That is a holographic formula I presented. But there's also tensor network models of holography. So typically you just consider some graph. Yeah, I'm just drawing random graph. And then at each vertex, you place some tensor, usually drawn by box. You place some tensor. And then these some vertices, they are assigned with some tensor. But there are also some vertices, like these vertices, where nothing is assigned. So they define these dangling vertices, they correspond to boundary in the context of holography. But these bulk vertices, they are assigned to some tensor. So then we can write down some state corresponding to this tensor network. So this type of tensor network have been discussed as a toy model of holography. And then it reproduces the holographic entanglement entropy formula, for example. But they pointed out, Akers and Russ pointed out that the simple kind of random tensor network, it's called stabilizer random tensor network. These are particular kinds of random tensor network where they have a particularly simple entanglement structure. So here these tensors at the vertices, you can think about choosing them randomly, but in this stabilizer random tensor network, these tensors are particularly simpler ones. They are stabilizers. There are some common eigenstate of some power matrices and so on and so forth. But anyway, details are not so important. So they consider the stabilizer random tensor network, and in this random tensor network, as it turns out, if you consider a partitioning of boundary Hilbert space, let's say A, B, and C, and so on and so forth, up to some unitaries, this state turns out to have a very simple description: Bell pair between region AB, Bell pair between B and C, Bell pairs between C and A, and there's some numbers. It's not just a single Bell pairs, but this stabilizer random tensor network states, it turns out, has a very nice simple structure that was discussed by Nozemi and Walter, such that this state, if you rearrange up to some unitaries, these states basically consist of a Bell pairs between A and B, B and C, C and A, and the ABC, small ABC represents number of Bell pairs shared by these regions. And then there is also GHZ state, which is shared by all these three regions, A, B, C, D. And then, as it turns out, ABC, they scale extensively with n in the large n limit, but D is always order 1. So you know, in the large n limit, we may forget about this small part of the wave function. So then this psi is just roughly speaking, it's like a product of Bell pairs AB between AB and BC and CA. But this does not agree with what we see in holography, where we have a finite entanglement wedge cross section, which means a reflected entropy equation. Yeah, sorry. Yeah, so this is actually just a motivation, so I don't really prepared for this, but let's think about random tensor network states. So I hope this notation is okay. I draw some network of tensors, and it defines some quantum state. Yeah, so it depends on your construction. Yeah, so you may want to consider more regular graph. I'm just drawing random graph. So yeah, so I mean, okay. Yeah, so first we draw some random graph. Yeah, some random graph, but then there's also, so graph consists of vertices and edges. And then we kind of separate vertices into two groups: bulk vertices and boundary vertices. So then some vertices, let's say I'm now using circles. So these are my boundary vertices. And then there are also bulk vertices, like these vertices, like these black dots. And then for these bulk vertices, I assign some tensors. So then I draw now boxes, each represent tensors. Right, so here obvious choices, many choices we can make, like a dimension of yeah, so the structure of the graph, dimension associated to each vertex, and so on and so forth. So there are many choices, but there's a particular ones where we can discuss holographic duality if we take some sort of large n limit. So then we put many these boxes, and then this defines some state. Okay. So Akers and Russ, they are interested in, I think one way to state what they did is that they are interested in computing reflected entropy. RAB for this random tensor network. So I have a boundary Hilbert space like this white dot, but then I tripartition these boundary vertices into three groups, like a group A, group B, and then group C. Okay, so then we may be interested in computing reflected entropy by first tracing out, let's say, region C, and then we may be interested in computing reflected entropy for row AB. Okay, but then there's a so yeah, in principle this can be very complicated calculation, but for the particularly nicely chosen tensors, that's where this stabilizer condition comes in. If this tensor network is something called stabilizer random tensor network, this psi has a very simple form. So up to some unitary transformations, you can basically write down explicit form of this psi ABC, which is a product of Bell pairs between, yeah, maybe I can use colors. Yeah, A and B. So we first write down a certain many Bell pairs connecting A and B, and similarly many Bell pairs connecting B and C, and many Bell pairs connecting A and B, and then yeah, up to some small correction which may connect all these three regions like GHZ state. But then that's it. That was what was shown by what does Nozemi and Walter discuss this structure. So I think from my perspective, this is like a how to say, very nice examples where I can sort of clearly visualize the pattern of quantum entanglement in many body quantum states. So this is like my dream case. But in the other cases I'm going to discuss, we don't have such a simple formula. But anyway, this is a context where Akers and Russ computed reflected entropy. And then they found out basically that since these are just coming from Bell pairs between A, B, and B and C, A, B, and B, C, and C, A, you don't get reflected entropy, which means you don't get any entanglement wedge in the language of holography. So this is kind of showing that a stabilizer network, although it reproduces the RT formula, it doesn't really reproduce full holography. Okay, so this is the kind of way a context of Akers and Russ. Okay, so I have a something like 10, 15 more minutes, I guess. Yes, okay. All right, so anyway, I think Akers and Russ, for my purpose, most important point is this 0D result. We can distinguish, we can detect triparty entanglement, and in particular, we can distinguish GHZ state and the W state. Okay? Okay, are there questions? Other questions? Yeah. Yeah, that's a very good question. I'm not sure if I have a good insight for this, in fact, and then yeah, that's a very good question. I don't know in this context, but in 1D case, I think it's more understood. So let me now discuss actually 1D case. Actually, maybe it was understood in the context of random stabilizer tensor network, but I personally I don't have any insight for this. So now let's consider 1D. This is the oops, 1D. So now I have a something like a spin system on one-dimensional lattice, spin up and down or something like this, quantum spin systems. And then we can discuss what is the behavior of refracted entropy. I think I actually want to consider periodic boundary condition. So I draw a circle like this. So I have a chain with periodic boundary condition, and then I tripartition this chain into 3 regions, A, B, and C. And then we can compute, or we can discuss the refracted entropy for or AB, for example, by tracing out this region C. So what is the behavior of refracted entropy, or maybe Markov gap? Okay, but we can also we also need to specify what kind of states we discuss, and then roughly speaking, we can discuss 2 kinds of states: gapped state. It means a ground state of some gapped Hamiltonian, like you can consider transverse field Ising model, and then you can go away from the critical point. Or we can also consider a critical ground state, which is the ground state of a gapless critical Hamiltonian. In particular, we can consider a critical points described by conformal field theory, for example. But I think in principle we can have more choices. But these are two kind of canonical cases. So we can discuss the behavior of the refracted entropy for these gapped states and the critical ground state. And this problem was studied by Zhou, Shiba, Soejima, Mon, and Zaratel. And then they found out the following thing. So first of all, for the gapped ground state, H is 0. That's the result number 1. And then they actually also proved that H is 0 if and only if the ground state is, the state in question is gapped. And then they also found that H is C over 3 log 2, where C is the central charge of the conformal field theory describing this critical point. Okay, so these are, roughly speaking, these are two main results by them. Okay, so now I have 2 things to describe here. So gapped states and critical states. So I guess before the break, perhaps I can just discuss gapped state, and then critical state I can perhaps describe in the next lecture. For the gapped state, they proceeded as follows. So they first consider something called the sum of triangle state. So it has the following form. So if you consider a 3 Hilbert spaces, HA, HB, HC. So I just use these circles to describe 3 Hilbert spaces. But then you can form some sort of simple state, which I describe this as a triangle. So this is the simple state, which may be looking like this: HR, BL, BR, CL, CR, AR. Meaning AR is the some degrees of freedom in the Hilbert space A, HR, and then there's the remaining degrees of freedom AL, and similarly HB also have a some degrees of freedom BR and BL, and the HC also has some degrees of freedom CR and CL. Okay, and then you can write down this a very simple state of this kind. And then for this type of state, H is simply 0. But we can also consider a slightly more complicated state where we can consider a sum of such state. So I can put some index here. Yeah, so these are tensor products, yes. And then I consider linear superposition, and there's some coefficient. So yeah, the first state is called triangle state. H is 0, and then second state is called sum of triangle state for obvious reason. And then for the sum of triangle states, H is also 0. That is something they can prove. Okay. So yeah, H is 0 for this three-party setting. H is 0 if and only if state psi is a sum of triangle state. So this is the first statement they established. And then to make a connection with a question, yes. Yes, exactly. Yeah. So this is the, if you wish, generalization of GHD state. Yeah. Yeah. So how do we prove this? Yeah. So that's actually I'm not sure. I refer to this paper, Zhou et al. They kind of well, it's a finite dimensional problem, and somehow they can prove it. Yeah. Yeah, it's non-trivial. Yeah, I didn't say it's a trivial, but this is the first statement they can establish. And then in the second step, they can use the matrix product state representation. So this is statement A. And then they consider the matrix product state representation of quantum state. That is another example of a tensor network state. So, but since it's a 1D quantum systems, tensor tensor network you consider is something very simple. So we have a array of tensors. They are connected by these tensors or matrices, and then these are like a boundary bonds, boundary degrees of freedom in the previous random tensor network discussion. So physical degrees of freedom, they are living here in these dangling bonds, but others are fully contracted. So this is the particular tensor network commonly used to discuss 1D, in particular the 1D gapped state. So 1D gapped state, we can use this matrix product states description of quantum state. And then you can sort of define a coarse-grained, not coarse-grained, but you can sort of blocking. Yeah, okay, so maybe let me stick back. So then we also consider a region ABC in this language. So some bonds are representing Hilbert space degrees of freedom in A, B, and C, and so on and so forth. And then they can sort of then block, they can sort of define real space renormalization group procedure where they combine some of these tensors, such that we produce the a kind of coarse-grained description of the initial ground state. So the second step is basically that by using this matrix product state representation and then blocking or coarse graining these tensors, we eventually actually go to this type of sum of triangle state description of quantum states if your state is gapped. Or short range entangled. Okay, so this is the two statements they made in their paper. Okay, yeah, I guess this may be I think I will take a question for this, and then maybe the critical point maybe I can discuss a little bit, but it may not end in 5 minutes or so. So maybe it's good to discuss maybe for the next lecture. But is there any question for this gapped states result? Yeah. So gapped ground state, yeah. So yeah, that means I have a quantum Hamiltonian, like a transverse field Ising model. But if J is H, yeah, spectrum is it's critical chain. But I simply means I go away from the critical points, then we get the excitation gap. So if J is H CFT, that means Ising CFT. If J is not equal to H, spectrum is gapped. Okay. Are there other questions? Yes, question? Yes. Right, so here this is the time-independent problem. Yes, but we could do time-dependent problems as well. Yeah, that is perhaps, yeah, so time dependence I may be able to discuss something like a third lecture or something like that.
There is a question in the online, Dr. Mori. In MPS, the boundary conditions, theoretical or open, matters to reduce the system into the product of triangle states. So basically, boundary condition is important in this state.
That's a good question. So yeah, periodic boundary condition is known to be slightly more complicated than the open boundary condition when we use this type of as a numerical tool. In this argument, I don't think boundary condition affect much. But I have to look into the detail of this blocking structure. Yeah. Yes. Yes, that's true. That's true. Yeah. So, but this is true. Yeah. So, yeah. So, in the limit where NA, NB, NCN, where yeah. So NA, NB, NC, they can be all different. So then they can have a different number of sites. But we take the limit where NA, NB, these ratios are fixed, but we take N very large. And then the claim is that this result does not depend on NA, NB, and NC. So that is a statement. Yeah. So that's also a priori not clear why it does not depend on. Right. Yeah, so the second one derivation I will present in the next lecture. But yeah, it sounds a bit non-trivial, I agree, yes. Is there any holographic Yes, there is. So that this is done by Hayden and Jonathan Source, and then Onka Parika. There's a paper. Actually, that is a paper where they introduce this terminology Markov gap. So there's the holographic picture, and then but that's yeah. But for example, one may ask, how does this log 2 comes up? That's yeah. I cannot. I don't remember, but there's a paper on this. Sadly, yes.
All right. Is there more question? If not, let's thank Professor Liu for very motivating lecture.
Yeah, thank you very much.
There will be a one announcement from organizers, about video lunch. Okay, so um, so in fact there are two complications about getting lunch from the IBS cafeteria. Oh yeah, good. Thank you. So yeah, two complications about getting lunch from the IBS cafeteria. One is that we have just have a limited number of seats available, so perhaps we can't all at a time sit together. And the other complication is that in order to enter into the IBS main building, in which we have a cafeteria, you need to deposit your ID card to get the entrance card. And the solution is this. So we are about 120 here, I think. So we split into three groups, each of size around 40, and each led by a member of IBS. So the first group will be led by myself. By the way, my name is Seungju Lee. And the second and the third groups will be led by other members. Mio Park, where are you? Oh yeah, Mio Park over there, and Junsei Tokuda over there. So yeah, Junsei will lead the second group and Mio the third group. So we will proceed like this, and the first group will leave now, and the second maybe in about 10 minutes, and the third in about 20 minutes from now. So yeah, so hands up please if you are so very hungry to join the first group. Yeah, okay, good. Okay, more is fine. Yeah, more, a bit more. Yeah, we can accommodate more, please. Yeah, more. Yeah, okay. Yeah, even more is fine. So okay, so these people will for sure be in group one, and a bit more will be fine. So you can follow me, and then yeah, we can just spontaneously form the second and third groups. A few more information. So you will receive the meal coupons upon exiting the lecture hall. So you need the coupons to get lunch. And the lunch will be in a buffet style. And for the vegetarians, I guess there will be some vegetarians here. The non-veggie menus will be marked as such. At least that's how I'm told, and we will find out. And some tables have a transparent partition for the pandemic reason, but not all. So you can go for the right table for you. And lastly, if you miss the groups, that's still fine. You just have your IDs and meal coupons, and you can still enter into the building and get the lunch. So yeah, that's it. Yeah. Then first group, please follow me.
하나, 둘, 셋. 하나, 둘, 셋.
Uh, uh,
You use Blackboard? Are you using Blackboard also?
no, Blackboard no.
No. Okay. Then I think you can just.
Yeah, just can stay here. Yeah.
All right, welcome back everyone. So let's start our afternoon session. So the afternoon speaker will be Marcus Marinho, and he's going to tell us about introduction to resurgence in quantum physics.
Okay, thank you very much. Thanks to the organizers for the invitation. I'm very happy to be in Korea for the first time. So I'm going to talk about resurgence, and let me first give you some indications about the material. I think it was already told to you that you can actually find notes, LaTeX notes for my course in my web page. So you go here, and you go to my web page, you will see a section on lecture notes, and the lecture notes for this course are just the first set of lecture notes that you will find there. It's called Introduction to Resurgence in Quantum Theory. And in these lecture notes, you will also find lots of workout examples that I will also use as exercise for this course, okay? So the topic of the course is resurgence, and some of you are familiar with this, some of you are not. So let me just tell you a little bit what is resurgence about and why we are interested in giving a course on this. Well, resurgence is about perturbation theories, perturbative series. So every time you have a problem in physics and mathematics involving perturbative series, resurgence, in a sense, is the best way to deal with it. So it's, in a sense, it's a general theory to work with perturbative series in quantum theory, but also in classical theory in mathematics. And these are perturbative series which are factorially divergent. So let me explain you why this is important. So let me give you an example that we will actually revisit in the course of these talks, which is an example from elementary quantum mechanics. And it's an example that maybe in your course on quantum mechanics you actually look at, which is a Hamiltonian, which is, a Hamiltonian, which is the harmonic oscillator Hamiltonian, and then you add a perturbation with a quartic term and with a coupling constant G. So this is a coupling constant. And you know that this part of the Hamiltonian is exactly solvable, but you would like to find an approximation for different quantities that you want to calculate as power series in this coupling constant. So this is, of course, something that you might have done. And imagine that, for example, you want to calculate the energy of the ground state for this system. So here 0 refers to the ground state. So the first thing you will get is the ground state of the harmonic oscillator, which in this unit is 1/2. And then you will get a power series in G, and you can calculate many of the coefficients of this power series. So formally, you will get a series in this coupling constant of this form. And this is probably an exercise that you have done at some point. You might have actually calculated the first few coefficients of this series, and this is supposed to be an approximation. This is supposed to be an approximation for the actual ground state energy when the coupling constant is small. Now, you would like to use this power series in order to do calculations. For example, you would actually like to see what is the kind of approximation you can get from the ground state energy. But then the first thing you should realize when you do this kind of calculations is that this series does not converge. Actually, the radius of convergence of this series is 0. It's strictly 0, okay? So the question you have to ask yourself is, what can I do when a series which has 0 radius of convergence? And the reason that this series doesn't converge is because the coefficients grow factorially, okay? So this situation is actually not special to this example. So this behavior in which the coefficients grow factorially is actually the generic behavior. This is the generic behavior for perturbative series in quantum theory. And this involves, this includes, of course, quantum field theory. So one very important aspect of this is that, when you study quantum field theory, you spend a lot of time in learning renormalized perturbation theory. And in renormalized perturbation theory, at the end of the day, you produce asymptotic series in the coupling constant for your systems, but these series do not converge, have zero radius of convergence. So all the work you have done in renormalized perturbation theory in order to produce a perturbative series cannot be completed if you don't know what to do with this final object, which is a divergent series. So it's not obvious at all how to go from this divergent series to a prediction of this series for a physical observable, because the series has zero radius of convergence. So the theory of resurgence, in a sense, is a collection of ideas and methods to deal with this. Okay? So resurgence has, in a sense, two aspects. The first aspect is to make sense of this perturbative series. And in order to do that, there are various techniques. And one of these techniques that I'm going to explain in these lectures is going to be Borel resummation. Okay? Borel resummation is a technique in which you can actually produce numbers out of this series. Okay? Now, the second thing, actually, what should I do now in order to get another page here? Sorry, yes. Oh, like this. Okay, very good. So the second thing is to actually find underlying structures in perturbation theory. So what we're going to see is that actually this type of series have additional information on non-perturbative sectors. So this is actually quite surprising, because we are starting here with the perturbative series of the theory. How is it possible that we can see some sort of non-perturbative physics out of perturbation theory? But actually, this is what the name resurgence means. Resurgence means that the non-perturbative effects of the theory can actually resurge, can reappear in the perturbative series. And this is something that we're also going to discuss in detail in this course. And I'm going to try to teach you practical methods in which you can see the emergence of non-perturbative sectors in perturbation theory. So one of the lessons of this course, and I can already tell it to you now, is that perturbative series are much more than just a collection of numbers. They give you windows into the non-perturbative sectors of the theory, and this could involve sectors like instantons, more complicated sectors called renormalons in quantum field theory, and so on. Okay? So eventually, and this is a kind of much more long-reach goal of resurgence, is to see at which extent you can reconstruct the exact theory just using ingredients from perturbation theory. Okay? So which extent one can use perturbation theory to reconstruct the full theory. And this is a goal which might not be reachable. We know that in some cases this can be done, but there might be other examples in which this cannot be done. But the kind of ambition of the theory is to be able to reconstruct as much as possible from the exact theory just using the ingredients of perturbation theory. Okay? So you see that in resurgence there are parts which are quite technical, in the sense that we are going to learn how to extract information from perturbative series and how to read something in order to get predictions. Because if you use, for example, in quantum field theory, just standard renormalized perturbation theory, you will get divergent series, and unless you do something to this series, you are not going to be able to extract predictions from them. So, in a sense, these techniques of resummation that are in resurgence are crucial, are in a sense the last step you have to do in order to extract predictions from a quantum theory. Without these techniques, it's hard to actually extract predictions from the normalized perturbation theory. But this is, in a sense, a more technical part. Then there is a more mathematical part in which you try to extract from perturbative series windows into the non-perturbative sectors, and eventually you want to reconstruct the whole theory just out of perturbative series, when it can be done. And in some cases, it cannot be done, but in trying to do this, you learn many interesting things about your quantum theory. Okay? So in a sense, we are going to start with perturbation theory, and we are going to try to see how much we can extract from it. Okay? So this applies to many, many different systems, from elementary quantum mechanics to quantum field theory, quantum many-body systems, and so on. So the program of the lectures is I'm going to start with resurgent technology, some kind of basic ideas and techniques of the theory of resurgence that one needs to use in solving the problem. So this is going to be a more mathematical part. But I'm going to try to give you lots of examples and lots of applications so you don't get bored. Then I'm going to illustrate these techniques in quantum mechanics, because quantum mechanics is a success story for the theory of resurgence in many senses. So we're going to actually look at examples in which you can show this technique, in motion. And then, if time permits, let's see how much we can do of resurgence in quantum field theory, which is a much more complicated story. So I'm going to give you some examples, if time permits, where the techniques of resurgence work very well. And I want to mention here that there are also applications of resurgence in string theory. In a sense, resurgence works better in string theory than in quantum field theory. And let me also mention that the theory of resurgence is an old story. Many of the things that we are hearing in this school are very recent developments. The theory of resurgence actually goes back to the 70s and the 80s. So it's a theory that was constructed by many people, but in particular, there were many physicists involved, like Edouard Bressan, Jean Saint-Just, André Boros, Giorgio Parisi, who won the Nobel Prize, Toft, another Nobel Prize, did many important contributions to resurgence in the late 70s and 80s. So this theory was actually constructed, in a sense, was developed in the kind of gold times of quantum field theory in order to understand the perturbation theories that quantum field theories were constructed at the time. And in a sense, there has been a new resurgence of interest in the theory of resurgence in last years. And in a sense, what has happened in the last years is that people have realized how to apply the technology of resurgence to theories like string theory, where this was not developed before, and also to interesting problems in mathematical physics, in complex Chern-Simons theory, relations to BPS states in string theory, and so on. So recently there have been many applications of this theory which looks a little bit like applied mathematics into pure mathematics. So, but these developments I'm not going to cover here. I want to really try to give you the basics of the story. Okay? Okay. Are there any questions? Yes?
You said that the factorial growth in this conservative series is generic in quantum theory.
Yes.
Can you be more specific about which aspects of quantum theory puts its factorial growth?
So when I mean generic, I mean that most of the perturbative series that you have studied in your life are of this type. So this includes stationary perturbation theory in quantum mechanics, WKB method in quantum mechanics, the perturbative series that you compute in quantum field theory, in the coupling constant, all these theories are factorially divergent.
So for instance, is it important that the Hilbert space is infinite dimensional?
Uh,
If I think of 2 by 2, two-dimensional Hilbert space, I can easily think of a Hamiltonian, which is whose gravity expansion is finite.
I wouldn't think about this in terms of Hilbert space. If you think in terms of, for example, Feynman diagrams, okay, like, because perturbation theory is attached, perturbation theory is in a sense is an artifact that you have invented, So, the way we conceptualize this artifact is in terms of Feynman diagrams. The reason why this series diverge factorially, there are many reasons, but one of the reasons why they diverge factorially is because the number of Feynman diagrams that you compute at each order is actually grows, the number of Feynman diagrams grows itself factorially, okay? So you will have a series, will have n factorial Feynman diagrams at each order, and unless there are cancellations, these diagrams will give you an n factorial dependence, okay? So it's really it's the combinatorial character of perturbation theory that leads you to this growth, okay? Now, there are other sources of growth, and I'm going to mention this, but this is in a sense, the main reason. But you have to, one very important thing here is that perturbation theory is an artifact that we have invented. Nature doesn't work with perturbation theory. It's us humans who work with perturbation theory. So n factorial, it's not so clear what is intrinsic to this n factorial growth. What is going to be important is that from this factorial growth, we are going to be able to find information which is not really perturbative in nature, okay? So, but the exact answer of say, a ground state energy doesn't know about perturbation theory or Feynman diagrams. It's just a number. It's just the way you think about this number that is important here, okay? Okay, so let me then start. Oops. Sorry? Yes. No, that's true. But you have a 2G factorial growth actually in perturbation theory, but this is due to the volume of moduli space. You see, that's the source for the growth. Okay, is you have to integrate over the moduli space of genus G Riemann surface, and this will have a 2G factorial growth actually. So in a sense, actually, perturbation theory in string theory grows faster because it has a 2G factorial growth and not an n factorial growth. But the techniques of resurgence can be easily applied to string theory. Now, in string theory, it's actually quite important, these ideas, because in perturbation, in string theory, you often don't have anything but the perturbative series. I mean, you don't have a non-perturbative definition of string theory. String theory, as it's defined, is just a collection of perturbative series. The standard definition is as a collection of perturbative series. And then, the theory of resurgence is actually very important in order to see how non-perturbative effects can be deduced from this. And let me mention, since you are asking that, the first evidence for deep brains was actually found in this way. So people realized that string perturbation theory grows like 2G factorial, and this meant that there should be non-perturbative effects of e to the minus 1 over GS, and these were later interpreted as deep brains, but the first appearance was, in a sense, as this kind of non-perturbative effects deduced from the growth of perturbation theory. So in string theory, actually, this method is quite important because it actually leads to an insight on the theory that you wouldn't have otherwise, okay? But I'm not going to talk about string theory in these lectures, okay? Okay, so let's start with elementary resurgent technology. So I'm going to start with kind of very basic things. So our starting point are then formal perturbative series that I'm going to write in this way. So I'm going to be, Z here is going to be my coupling. You can think about the coupling, or it's just a complex variable. And I'm going to assume then that these ANs are numbers that grow like n factorial, and maybe they will have a subleading growth of the type a to the minus n. Okay, so this is as I said, this is the typical growth of coefficients in the theory. Okay. Now, what do you do with such a series? Now, such a series, as I said, has serial radius of convergence, so they cannot give you a reliable expression for an observable. But what we usually do with this series is to find asymptotic approximation. So given a function f of z, we can actually, so this is an actual function, and phi of z gives an asymptotic representation, an asymptotic expansion. So the meaning of an asymptotic expansions are actually very different from convergent series. So what it means that you have an asymptotic expansion? How does it usually work? Now, asymptotic expansions are very tricky because of the following. Imagine that you want to find an approximation to this function f of z starting from this asymptotic approximation. Now, usually, if you have a convergent series, you know that the more terms that you add, the better is going to be your approximation for your function. Now, when you have an asymptotic expansion, this is not going to be the case in general. So what happens is the following. You know that you cannot sum all the terms of this series of phi z. You cannot sum it for any value of z because this series has zero radius of convergence. So you cannot really sum all of them. So the best thing you can do is to consider partial sums of this series. And let me denote it like this. And then in these partial sums, you just cut your asymptotic expansion to a given order n. Okay? So imagine now that you want to know how these partial sums reproduce, how well these partial sums reproduce the function that you want to calculate. So let's assume that you take f of z, the function that you want to calculate, and you consider these partial sums, and then you represent this quantity as a function of n. So you represent this quantity as a function of n. You start here with n equal 1, n equal 2, n equal 3, and so on. So what is the typical behavior that you are going to find? Well, the typical behavior is that for a given z, so here z is fixed, you are going to find that this thing, as you increase the number, decreases, but at some point, it doesn't decrease anymore. On the contrary, it starts to actually, instead of decreasing, it starts to increase again. So you find that the sequence of partial sums do not give you some systematic approximation to your quantity. There is a minimum value for which this approximation works very well. These partial sums work very well, so there is a minimum, there is a value of n star for which the difference between the real function and your approximations reaches a minimum, and then it starts increasing again. So this means that if you want to use an asymptotic expansion to calculate a function, you cannot include all terms. You can only include a finite number of terms up to a given integer number n. And this procedure in which you cut the series at n equal to n star is called, this procedure is called optimal truncation.
There is a question online.
Yes.
The question is how the divergence and the resummation insurgence address are in n in a second. Due to the number of completions that occur at each order in the perturbed expansion, and question is it then correct to say that the resummation you perform in this case are in a sense that orthogonal to the RD analysis? Here
Is
I mean the Wilson RD and the not renormalized one, which is already tied to perturbation theory.
What is the question? If this is orthogonal to what?
Divergences and resummation resurgence address are those due to the number of contributions that occur at each order in the automatic expansion.
I mean, maybe when we talk about resummation more concretely, we can address these more kind of questions. As I said, there are many reasons for the divergence of this series. One is the number of Feynman diagrams, but there are other reasons where this series can diverge factorially. Like one reason I just mentioned is in string theory is the factorial growth of the moduli space and so on. But when we get to resummation, you know, we will, I mean, maybe I can get this question again or, okay. So the important point here, yes? What? F is just a function. I'm just supposing that you have a function, you have an actual function, and you have an asymptotic approximation to it, okay? And the question is, if this series gives you an asymptotic approximation, what's the actual meaning of this? If you have a function given by a convergent series, I could just here write an equal sign in the region of convergence of this series. But if you have an asymptotic expansion, you know, I'm trying to explain what's the actual meaning that a formal power series gives you as an asymptotic expansion to a function. F is a function for which you have an asymptotic expansion, and the thing is what is the actual meaning of that. I will actually give you an example right now, okay, immediately, okay? Yes? No, there is, you know, usually I will actually now explain you how you can get this n factorial. No, there is a point in which, you know, this series actually starts increasing. Sorry? Because you know that at the end it has to sum to infinity. So at the end this series is going to go to infinity. Eventually, this series has 0 radius of convergence. So this means that if you sum all the terms of the series, you will get infinity for sure. So at some point, when n grows, you know, phi z goes to infinity, okay? So this thing goes to infinity as n goes to infinity, okay? So it cannot oscillate, it has to go to infinity, okay? It can oscillate while going to infinity, okay? But it has to go to infinity eventually, okay? Okay, so actually, you can actually guess the number of the number n. Find the value of n, approximate the approximate value of n by just minimizing. So you minimize an. Sorry. So you minimize the terms in this series. So you look at this formal series, and you look at what is the term that gives you the smaller contribution, okay? And if you do this exercise, you will see that n is actually done in my notes, so you can think about this as an exercise. And the answer is very easy. You will see that n is essentially a over z, okay? So remember that I assume that an grows like n factorial a to the minus n. So it's an elementary calculation that the terms in this series are minimized for this value of n star. And notice that the smaller, the greater is the bigger z, the bigger the value of your coupling constant, if you want, the smaller is n. So this means that if z is very small, n star, the truncation can be done quite far. You can take many terms in this series. But if z starts growing, at some point, n star grows smaller and smaller, and at some point, you don't really get any good approximation to your function. And even taking 1 or 2 terms of your asymptotic expansion can be is not really even a good approximation. So at some point, you know, if z is sufficiently large, you know, this thing completely breaks down, okay? And that's why this expansion is an asymptotic expansion. The approximation gets worse and worse the smaller is z, okay? Sorry, the bigger is z, yes? Sorry? What? So why we can truncate? I mean, we have to truncate. We cannot take the whole thing, yeah. Yeah, the question is, oh, I mean, actually, I assume in here that this phi of z is an asymptotic expansion of this function. So this means that you know, this means actually that the error that you make when you truncate is going to decrease with z. Okay, that's the definition of asymptotic expansion. Okay, so this means that if z is sufficiently small, this approximation is going to be good. Okay, but you always have to truncate at some point. Okay. So the reason why this gives an approximation which is good for a small z is because of the definition of asymptotic expansion. So no, I assume that phi z is an asymptotic approximation. Is an asymptotic approximation to f. Okay. Which means that fz minus fn of z divided by zn goes to 0 as z goes to 0. Okay? So this is what guarantees that this approximation is actually makes sense. But it's very important here that this approximation is only really good when z goes to 0. For finite z, you have to truncate, and this truncation can be very, very bad. Okay? So actually, another very important thing is that since you truncate, you will always get an error. You see here in my previous plot here, you see that there is, even when you do this approximation, there is always an error in the kind of in the approximation you are making to this function. You see, when you have a convergent series, you can make the error as small as you want. But when you have an asymptotic expansion, you always have an error that you cannot get smaller. And this is independent of how many terms you have in your series. You see? Here, I can give you all the coefficients of the series. If z is sufficiently large, I'm going to have to truncate the series, and then I will always make an error. And then, with the same argument, once you have this value of n start, you can always actually see that fz minus fn optimal, so this is the optimal value that you can obtain here, are going to be of exponential order. So are going to be of this order here. So this means that when you use asymptotic expansions, you will never get the exact result that you want to get, and you are going to make an error which is exponentially small in your coupling. Okay? And this is the source of what we will call later non-perturbative corrections. This is non-analytic in Z, because it goes like e to the minus 1 over z, okay? And this is actually what you would call a non-perturbative effect. So optimal truncation, which is actually what most people do when you are given if I give you, for example, the series for the ground state energy of the quartic oscillator, which is this example that I gave you at the very beginning, and you try to use this series to calculate the ground state energy, you will typically do this kind of optimal truncation. But you will never get the exact result. You will always get an exponentially small error, okay? So, and as I said, I emphasize that this error, you make it independent of the number of terms you have computed in the series. So this is actually very bad, because you see many of our colleagues in quantum field theory are spending a lot of time in computing higher loop corrections in perturbative series. But if this perturbative series is asymptotic, no matter how many loop corrections you calculate, you're always going to make an error. And you see, and this is very different from convergent series. You have a convergent series, you know that the more terms you have in the series, the better is going to be your approximation to the result. But when you have an asymptotic expansion, this is not true. You work for nothing, because you compute more and more terms, but you still make an error if the value of the coupling constant is sufficiently large. And this is what makes necessary to actually introduce additional technology to improve this state of affairs. Okay? Very good. So actually, in order to kind of make this more concrete, let me give you an example. So this is an example exercise in order to make these things a little bit clearer. So let me give you an example which is actually a toy model for quantum field theory. So I'm going to introduce a function of a coupling G which is given by this integral here. So this is an integral over R, and then I get e to the minus s of z. So this, you see, this looks very much like a path integral in quantum theory. And sz, you can think about this as an action, is z squared over 2 plus g z4 over 4. So this is, if you want, is lambda phi 4 theory in 0 dimensions. So this is like a toy model for the path integral of a lambda phi 4 theory. So, yes?
In this resurgence of the quantum field theory, is it important whether it's Lorentzian or Euclidean?
It can be important because sometimes you have to make analytic continuations in the final variable. So it can be important in some applications of quantum field theory, absolutely. Because sometimes you have to move in the complex plane in order to go from Minkowski to Euclidean, and this means that you will have to change direction. As we will see here, changing direction in the complex plane of your coupling constant or your variable might have very important effects. Yes.
When you say resurgence in quantum field theory, is it Euclidean or Lorentzian or?
Usually I mean in Euclidean calculations in quantum field theory, yes. But in many of the examples I will discuss in detail, this is not so important. But yeah, in principle in Euclidean quantum field theory. So if I'm going to discuss, for example, ground state energies and things like this, even in quantum field theory. So this is going to be mostly Euclidean quantum field theory. Okay. So we can discuss, if you want, more subtle issues of how you go to Minkowski and so on. Can discuss in private if you want. Okay, so this is like a toy model of lambda phi 4 theory, and of course this g is a well-defined function. It's a well-defined function of g as long as the real part of g is positive. Okay, the real part of g is positive. Here you have like a e to the minus g z to the 4. So this integral will be absolutely convergent. So this is really a well-defined function of g for these quantities. Now, of course, what we would like to have is an asymptotic expansion of this integral if g is very small. And the way you do this is the standard thing in quantum field theory. So you just keep the Gaussian part, right? And then you expand the exponent, right? And then you integrate term by term. This is the analog of perturbation theory in doing this integral. And if you do this, you are going to get a series. Let me write it like this. So here I didn't put an equal symbol because this is not going to be an equality. What I'm going to obtain here is an asymptotic series, and this asymptotic series is of this form, and these coefficients can be computed. So this is what I put as an exercise for you, can be computed completely explicitly. They are given by minus 4 to the minus k, 4k minus 1 double factorial, divided by k factorial. Okay? And it's very easy to see that these coefficients actually grow like minus k to the 4 to the k times k factorial. Okay? So this is a typical example in which you have an asymptotic approximation to an exact function by an asymptotic series, okay, whose coefficients grow factorial. And as I said, this is lambda phi 4 in 0 dimensions, and this is actually what is going to happen for quantum mechanics with a quartic potential or for a quantum field theory with a quartic potential. You will have also this type of behavior, okay?
In this asymptotic series, you also include negative g also.
No, right now I'm thinking about this asymptotic series as a formal object, okay? I'm not telling you what you should do for g negative. That's a different question. Now, actually, my original function is not defined for negative g, so I should do some sort of analytic continuation or something like that. Okay. Let's assume that you are working in this domain, but then g is very small. So this should be an asymptotic expansion for this. So one thing you can do, for example, as an exercise here, and this is actually, you can see it in my notes, you can actually compare zg minus the partial sums here, and for example here I gave the value g equal 0.02, and then you see that the optimal truncation here happens when n star is equal to 12, more or less. So you can actually do the calculation. You can calculate these differences explicitly, and then you will see that the optimal truncation here occurs at this point, and you will have a non-trivial difference between these two functions. Okay? So this is an example in which you can play with and actually check these statements I made. Okay? So I have to say that optimal truncation is what many people, the only technique that many people use to do these calculations, and in a sense what we would like to do is to improve the situation. And the first question you would like to ask is the following, and this is a very practical question. Is there any way in which I could actually get a result from this perturbative series in which knowing more and more coefficients actually would help me to reduce the error? Okay, that's a kind of very practical question, and many people working in quantum field theory ask this type of questions. Now, what I'm going to explain you now is a technique which allows you to do this in many situations, which is the technique of Borel resummation. And in order to do that, I have to introduce some additional things, but the goal now is to go beyond this optimal truncation that we see that it has many limitations and try to improve the situation here. Okay? So first, I'm going to define a very important object, which is the Borel transform. And also for those of you who like mathematics, the Borel transform is very interesting because, as we will see, it's going to take us from this world of formal divergent series to the world of analytic functions. And this is actually very good because analytic functions, working with analytic functions, we have a lot of complex analysis that we can exploit, and this will change radically the situation. Okay? Very good. So let's go back then to our general formal series. So here, again, I'm going to assume that this goes like this, goes n factorial, then it has some sort of subleading exponential growth. Okay? Now, the Borel transform is defined in a very simple way. Now, what is bothering you here is, of course, the factorial growth. The factorial growth is what is spoiling this series, right? So let's just remove it. So you just take the same coefficients, you divide them by n factorial, and then you introduce an additional variable psi of n. Okay? So this is called the Borel transform of phi. And a very important property is that this function is analytic at the origin. So you see, we started live with a formal power series, and now we have a function which is much better. It's an analytic function of the origin, so it means that this function phi of z will have a non-trivial radius, non-zero radius of convergence around the origin in this z plane, and then you will find maybe singularities somewhere as you reach the border of the domain of convergence. Okay? But this is actually, it's very trivial, but we have gone from the world of formal power series to the world of analytic functions. Okay? So let me give you a very simple example, almost a trivial example. So suppose that I take the most obvious divergent series, just k factorial divided by z to the k. It's clearly a series whose coefficients grow factorially. What is the Borel transform of this function? Well, we just remove the factorials, right? So we get z to the, sorry, it was not z, it was zeta, is zeta to the k. And we know that this function sums to this. So in this case, we have a function whose radius, the Borel transform of this divergent series has a radius of convergence of 1, and will have a singularity, a single singularity, which is a pole at z equal 1, at zeta equal 1. Okay? Now, there are more interesting examples that you can work out. So, for example, as an exercise you can do, and it's solved in the notes, you can take a slightly more general factorial series, which is gamma k plus b divided by gamma b a to the minus k, z to the k. And it's very easy to show that the Borel transform of this is actually 1 minus zeta over a divided to minus b. Okay? So here I'm assuming that b is between 0 and 1. So you see that here, you see have something very similar. So this function, this Borel transform, has a singularity at zeta equal a, which is a branch cut singularity. Okay? And in particular, if you take the limit when b goes to 1, you will get a logarithmic singularity. So you see that now we have factorial divergence series, and through this Borel transform, you get analytic functions. And these analytic functions will have singularities. And these singularities will reflect in some way the properties of the original factorial series. Okay? Now, what is, in a sense, one of the most beautiful aspects of resurgence is the following. What we should do now is to look at what happens to these functions near the singularities. When you have an analytic function with a singularity, it's very interesting to know what is the local behavior of this function near the singularities. And what we're going to find is that near these singularities, there will be hidden formal power series. And these formal power series are going to tell us about, very often, about additional sectors of the theory. Okay? And this is, in a sense, one of the basic ideas of resurgence. We are going to we have constructed analytic functions, and we are going to zoom, in a sense, near these singularities to see what is there. Okay? And looking at these singularities, we will find more information. In a sense, these singularities, these are singularities of the Borel transform. But these singularities, you see, to see a singularity here, we have to have a lot of coefficients in my original series. So in a sense, these singularities are telling us about the factorial divergence series, the perturbative series that we started with, but when you look at higher orders in the expansion. So in a sense, as we will see, these singularities are related to the large order behavior of perturbation theory. And this large order behavior of perturbation theory will have information about additional sectors of your theory. Okay? And we will see actually a very beautiful example of in quantum mechanics probably tomorrow. Yes? Yeah. N factorial square is very easy. We have, for example, it's a very simple example, which is the WKB expansion. The WKB expansion. The WKB expansion grows like 2n factorial, which is like n factorial square, or string theory. Now, the way you do this, actually, in the case of WKB or string theory, essentially, well, first of all, you can generalize what I have done here by introducing generalized Borel transforms in which you divide by 2n factorial instead of n factorial. Okay, so this can be accommodated in the theory. But actually what happens very often is that the coefficients grow by, like, for example, in WKB, that we will, I guess I will talk a little bit about WKB this week. In WKB, the coefficients grow like 2n factorial, and actually what you can do when the coefficients grow like 2n factorial is like construct a series out of this in which you only have even powers, so that the coefficients grow like 2n factorial. So a series with 2n factorial behavior is like a series with n factorial behavior in which all the terms vanish. So you can also adapt these formulas to this type of series. Okay? So in principle, you can do this. Okay? But yes, there are generalizations. Also, you can do a generalized Borel transform in which you take into account this. Okay? Yes. I mean, this is kind of, yeah, I mean, I don't know what to say. I mean, these are just singularities of complex functions. You see, they can be, you can have poles, you can have branch cuts. You know, usually logarithmic singularities. I mean, this is, in a sense, much more elementary. We're just trying to, we are going to find some sort of singular behavior for this series, and the question is how bad is this singular behavior? Typically, essentially, branch cut and logarithmic singularities are already cover all the cases that you can find in realistic applications. Okay, so I'm going to actually restrict to this. Okay, now of course, now in order to make progress, we have to do actually be able to restrict ourselves to a set of functions which are nice. So the nice functions, so you see in each branch of mathematics has these nice functions. So the nice functions here are called resurgent functions. And resurgent functions are very easy. So you say that phi of z is resurgent if the Borel transform admits, let me put it, I'm going to spell it like right now, easy analytic continuations. So you see, we are going to be interested in doing analytic continuations of these functions, this Borel transform, beyond its original radius of convergence. So you see, usually what you find here, and this is, again, something that happens in complex analysis, you have a domain of convergence, and then you have some singularities in this domain which limit the domain of convergence. The question is that we don't want to have too many singularities. We want to be able to go from inside the radius of convergence to outside, maybe deforming our paths so that we avoid the singularities, but we want to be able to go outside of this domain. So the definition is that any line which goes from the origin to a point here can actually avoid singularities by a simple deformation procedure. Okay? So for example, if you have a single singularity, it's clear that you can always, if you want to connect this point with this point here, you can always avoid this singularity by a simple deformation of the path. Okay? Now you have like many singularities, so you have this border, and you have many singularities, which is the typical situation. You can have also singularities outside of this. So you can always avoid them by deforming your path in a kind of easy way. So this is essentially what is a resurgent function. And you could say, well, most of the functions are going to be like this. Well, not necessarily, because there are functions which have a dense set of singularities in a closed circle, for example. This is, there is a counterexample to this, which is what we are called lacunary functions in complex analysis. So these functions are very bad because essentially they have a dense set of singularities. So they have a domain of convergence, but in the circle of convergence they have a dense set of singularities. So there are singularities all the way here. So this is like a full border, like a real thick border of singularities. So you cannot really go from inside to outside by deforming the contour. You are going to hit singularities whatever you do. So this is actually a counterexample to the kind of functions that you want to use. Okay? So we don't want to be in this situation. We want to be in a situation in which we can go from inside to outside, okay, following paths. And if there are singularities, we can avoid them by just deforming the path. Okay? So this is not too much to ask, but it's something that you have to ask. Okay? Okay, now in order to make progress and to be concrete, I also want to be concrete about the type of singularities that we will have. Okay? So what type of singularities do we have? Well, you see, in the examples I gave you, we saw that there were poles, branch cuts, and so on. So for expository reasons, I'm going to restrict myself. I'm going to consider mostly singularities which are poles or logarithmic branch cuts. Now, everything I said can be extended to branch cuts, to more general branch cuts. And actually, this is going to be an exercise. Very often, I will state a result where you have these logarithmic singularities, and then I will leave as an exercise the extension to the more general case. This is just in order to have an easy life and also to give you some exercise. Okay, so then once we assume this, okay, now let's do the following. So let psi equal to psi omega be a singularity of the of this Borel transform. Okay. Now we are assuming that the singularities are either poles or logarithmic branch cuts. So this means that if you do a local expansion of this function near this singularity, so we do a local expansion, we zoom around the singularity by putting ourselves near this singularity. So psi here is a small deviation of the singularity. So this is going to be this. You can have a pole here. So this could be something like this. I use these normalizations to make easier some other formulas. You can have a logarithmic singularity. So you could have something like log of psi. And then this logarithmic singularity can multiply in general a series in psi. So this is the most general structure of a logarithmic singularity. And then you will have regular stuff. So regular means things which are non-singular. Okay. So this is the general structure of this function near this singularity. So there is the pole, there is the log, and here I introduce a coefficient s. So what is the meaning of s? Well, let me explain you first. Let me just introduce some notation here. You see here, first of all, you see that here there is another series. And this is what I told you before. I told you that near the singularities of these Borel transforms, suddenly you will see more structure. And this structure, you can see it here. If there is a logarithmic singularity, there can be another full series appearing. And this series is going to be important. I'm going to label. I'm going to write it like phi hat omega psi, which is this series here. And this series is, sorry, let me just change the notation here. This series will have a finite radius of convergence. So this has a finite radius of convergence. And I'm going to actually fix a normalization. Often I will fix the normalization of this series. So, for example, I could actually normalize this series as that c hat 0 is equal to 1. And then since I'm going to fix the normalization, I have to introduce here an additional constant here, s. And this constant s is sometimes called a Stokes constant. But it's very important that the value of this constant depends on my choice of normalization for this series here. Okay? So this is kind of important formula here, and this tells you that once you have this Borel transform, you will find more structure inside. Okay, and this is going to be. I know this is a little bit too mathematical, but keep with me because this is going to be important later on for the physics development that will appear. Okay. Now, in a sense, the most important thing of this is the following. We started with a divergent power series. We did this Borel transform. We got an analytic function, and this function has singularities. And now, by looking at the singularities, suddenly we find more series. Okay, so we started with one series, and now associated to this singularity, we are going to find additional series. And the question is, what are these additional series representing? Are they giving some interesting information or not? And the answer is, of course, they're going to be interesting information, and that's what we're considering here. Okay. Now, of course, you can do this with all the possible singularities. Now, remember that to each singularity, each singularity, we associated this additional series, assuming that you have logarithmic branch cuts. If you have more general branch cast, you also can do something similar. Now, this series is convergent, but I can actually do an inversion of the Borel transform and find another series, this time in the variable z, in which I just take my original series here, and I multiply the coefficients. So Zn are n factorial divided by Zn. So you see, I first obtain a convergent series, but I can obtain another divergent series by just multiplying by n factorial. And now you say, well, but why are you complicating your life so much? Well, you will see that we are going to see that in many calculations we will do, the natural thing to consider is this divergent series and not the original convergent series. But if you take into account everything I said, the final outcome, and this is important here, the final outcome is that I started with a series phi of z, and now, by looking at all these singularities and so on, I got a family of series. I got a family of divergent series associated to the singularities of the Borel transform. So omega here is a label, so I have a label for these functions, and this can be actually an infinite number of functions. I could have an infinite number of singularities. This happens often. So I started with a series which in a sense describes the perturbative sector of my theory, and suddenly I got much more many things, okay? And the question is, what is the physical interpretation of these additional things? But before getting into the physical interpretation, let me give you again some interesting examples where you can see how actually this works, okay? So let me give you examples of this phenomenon. So I'm going to give you two examples. One example is it's actually useful because it's related to the AD function and it's very nice. And another example is the quartic integral that we saw, and this is going to be also very important. So let me give you a kind of very formal example. So the first example is related to the AD function. So for those of you who are not familiar with the AD function, in my lecture notes, I just wrote a small appendix with some additional information and so on. But the AD function appears very often in physics and in mathematics. Well, it's just you can think about it as the solution of this differential equation. So let me just make sure that I get, yeah. So the AD functions are just solutions to this linear differential equation, okay? And very often you are interested in doing asymptotic expansions of the AD function. These appear very often. For example, you have studied the WKB method. Maybe you have had to study the asymptotic expansion of the AD function. Now, I'm not going to speak explicitly about the asymptotics. Yes, you have a question? Yes.
Yeah, here you specify Z, and then you put the xi, which is the difference from the zeta W.
Yes, yes.
And then going back to the Z, but the first, the Z, phi Z is the same as the phi omega Z.
I mean, yeah. Here, yeah. This looks a little bit like black magic because it's not clear why I did that. But you will see that in some calculations. I mean, I will do a calculation which is very important. I don't know if I had to do it today, but I'm going to calculate the discontinuities of Borel resummations, and you will see that actually out of this series, what you actually find at the end of the day are these functions here. So this right now looks like some sort of, it's not really completely justified, but just believe me, this is actually natural. Now, the important thing here is that at this level, these series are for me collections of numbers. So it just happens that, if I look at a singularity, I get a series. Now, you see, this series here is just a collection of numbers. So I'm just using C hat here or Cn here. So these are just ways of encoding these collections of numbers. But what is important, and at the formal level I want to insist in this, is that if I give you a perturbative series, there is a lot of structure in it. And this lot of structure has to do, in a very mathematical, precise sense, with the singularities of this Borel transform. Okay? And I know this might be very mathematical for some of you, but I will make the connection with physics as soon as possible. Okay? Just let me give you an example. In the AD function, when you compute asymptotics of the AD function, you get a formal power series, which looks a little bit complicated. let me just copy it for you here. 3, 4 to the n. And then you have some gamma here, gamma n plus n plus 5, 6, gamma n plus 1, 6, and I divide by n factorial. Oops. And this is multiplied by z. Oops. Sorry. This is multiplied by z to the n. I cannot write it here, sorry. So let me try to, can I get this? No. No, anyway. So let me write it again here. So f1 of z, actually I'm going to define two series here, 1 and 2. So it's 1 over 2 pi. So they only differ in the sign that I use here. And then we have n phi 6, n plus 1, 6, and then n factorial, and this multiplied by z to the n. This is a formal power series, looks complicated, but this is what you get when you work with 80 functions. And the coefficients here grow like n factorial. You have two gammas here, so this grows like n factorial, this grows like n factorial, divided by n factorial, you have a single growth of n factorial. Now this series is actually very nice if you take phi 1, because its Borel transform can be computed in closed form, and it's an exercise that you can do. And actually, it turns out to be a hypergeometric function with index. The index are determined by the index appearing here. So it's 1 minus 3 psi over 4. And this is a very beautiful example of the theory, because if you look at the analytic structure of this function, you will see that this is a hypergeometric function. So we know everything about the analytic structure of hypergeometric functions. It's going to have a singularity here at z equal to minus 4 over 3. So this is a single singularity, and is of the logarithmic type. The singularity is of the logarithmic type. Of the log type. So this is one of these functions, of the functions of the type that we are considering. Let me actually mention that the resorgent functions for which the singularities are of log type are called simple resorgent functions. So this is an example of a simple resorgent function. So now you could say, aha, what is the series that is hidden in this singularity? Remember that in every singularity there is another series hiding. Okay. So what is the analysis here? So this is actually very easy. You can do it by using properties of the hypergeometric functions. So remember that I wrote this series here. So what is the series associated to, let me label the series by the singularity. So let me call the series hiding in this singularity, let me call it minus 4 of z. It turns out that this series is phi 2 of z. So it's the same series that I wrote before, but with a minus sign. So in this case, you see this function, you do the Borel transform, there is a singularity, and this singularity is another series, and this series is the series that I did before, but with a minus sign. And then you should say, well, what is the meaning of this? Well, it's actually very interesting, the meaning of this. Why? Because you see, the 80 function is a second-order differential equation. If you want to find solutions to this equation, you will find two independent solutions. So it turns out that phi 1 gives you the asymptotic expansion of one of the solutions. But you are missing another one. So where is the other solution of the 80 equation? And it turns out that this function that I found here, hidden in the singularity, this formal power series, is the formal power series that you need to do to reconstruct the other solution of the 80 function. So here is, again, already a very simple example of this phenomenon that the singularities of these Borel transforms are telling you about other sectors of the theory, because two different solutions of this 80 function, you can think about them as two different sectors of the 80 theory, okay? And this is actually at the basis of the physics that we're going to find in here. Okay. So so this is again one example of this, and let me do another example, which is the second example is this quartic integral. So this is actually a very beautiful example where the connection to physics, I think, is going to be even clearer. Also, this is in principle a math exercise. Yes. Phi 2 will give you the asymptotic expansion of the other set of solutions of the area equation.
Yeah, yeah. So is that just an observation, or should that be the case? I mean, is there a reason for why?
Yeah. Of course, there is a reason for this. Yeah. Of course, there is a reason. So this is a generic story, and I'm going to mention it here in the example of the quartic integral. The reason is that, as we will see, let me just advance myself. When you write the area functions, the solutions to the area equation, you can write them as integrals. Okay, and actually these are integrals where this asymptotic expansion can be obtained as a saddle point expansion. Okay, now it turns out that these solutions that appear in the singularities, these series that appear in the singularities, are related to the other saddle points of the integral you are looking at. So let me give you first this example, and then I will explain you why is this the case. So in the quartic integral, remember that I had this series with these coefficients where ak was growing like -4 to the k factorial. Okay. Now, as an exercise, you can actually calculate the Borel transform of this series, and it turns out that in this case you can also write this in closed form. Can be written in closed form, and actually it's very, you can write it in terms of a Bessel function of an elliptic integral and so on. But what is interesting is that when you do this, well, you already see what is going to happen. You see, you are going to find a singularity here at zeta equal to -1/4. Okay, so there is a single singularity here, which is also of logarithmic type. So this is also a simple resorgent function. You will have a branch cut, and now you can actually calculate the series hidden in this singularity. So let me actually write it again. So this series, actually you can see that is going to be given by -1/k, a to the k divided by k factorial, psi to the k. So you see, ak are the coefficients that appear here, and the singularity is going to have another series, which is the original series divided by k factorial. So when you do this undoing of the factorial that I was mentioning, you are going to get another series, which is the original series, but with an alternating sign. So this is very similar to what happened in the area equation. But now you have to ask the following question. This series that appear in the quartic integral appear as a saddle point expansion of this function here, right? So we were actually expanding this integral around the trivial saddle point. So remember that set of g was 1/√2 pi, this integral here. So if you think about this integral here, you see this integral here, if you think about a saddle point integral, you have a function s of z, and this function has actually 3 critical points. One of them is z equals 0, and actually phi of g was obtained by doing the expansion of this integral. So if you expand, if you do a Gaussian, is the saddle point expansion of zg around the trivial critical point. so which is z equals 0. So this is the trivial critical point of this function of this integral, and you look at this saddle point, you expand around this trivial saddle point, and you get this series. And this is what is perturbation theory. Perturbation theory is usually doing an expansion around a trivial critical point. Now, there are other two critical points, and you know, when you solve this equation, you get z equals 0, but you also get these other two critical points. Let me make sure that I get the right normalization. So which are, sorry, this is the equation for the critical points. So there are actually two critical points at z squared minus 1 over g. So these are two additional critical points, right? And now, what is in a sense surprising is that if you expand now, and this is an exercise that I propose to you, it's very easy to do. If you expand z of g around these critical points, any of these critical points, they are symmetric. They are going to give you the same contribution. You obtain you obtain phi of minus 1/4 of z. So let me recap, and then I will finish. So in this exercise, we do, you know, there is this general story. Given any divergent series, I can get an analytic function, and then the singularities of this analytic function are going to tell me something, okay? And I did this exercise for the quartic integral. So what did I find? I found an interesting series, and this is very similar to the Airy function. It's the same series that I had before, but with an alternating sign, okay? Now, I know that my original series has an interpretation as expanding an integral around a trivial saddle point. But now what I find is that this series hidden in this singularity can be actually interpreted as the expansion of this integral around a non-trivial saddle point. And expanding around non-trivial saddle point in quantum theory is supposed to give me new sectors of the theory. Perturbation theory is expanding around a trivial saddle point typically, but if you expand your path integral around non-trivial critical points, you obtain new sectors of the theory. And what I'm telling you is that these sectors that you obtain by expanding around these non-trivial saddle points, you could have found them, you could have guessed them by looking at the trivial sector, at the perturbative series, and looking at these singularities. So the singularities of the Borel transform of the perturbative sector tell me about other expansions of the same integral around other saddles. And this actually, I gave you here as an example, but there is a theory behind it that was actually developed by Michael Berry and Chris Holes, where they actually apply the theory of resurgence to these examples, and they show that indeed this series hidden in the singularities of the perturbative series are telling me about other saddle points of the integral. So this is really a perturbative window into the non-perturbative sectors of the theory by using, and that's why all this idea of looking at singularities of the Borel transform, it's useful because it's going to tell me about things that are not manifest when I just look at perturbation theory, you know, on the face of it, okay? So I think I'm going to stop here. I already introduced many interesting tools, and then tomorrow I will continue the discussion, okay? And I will try to make contact with physics as soon as possible. I'm trying now to make contact with physics, but I also want to give you the technology that you need in complex analysis to actually do this type of calculations. Okay, thank you very much. let's see. So this is what I wrote as the most general expansion here, right? So and assuming that there is a pole, then there is something multiplying the log singularity, and there is something regular. So what is that you propose to do exactly here?
So rewrite this as minus a over 2 pi design times the series expansion of design. So combine regular part and
Yeah. But if I do this, the thing is that the regular part actually does not really tell me much, because you know, if you combine the pole with the regular part, most of these series are going to be regular terms. So the regular terms, in a sense, you know, the theory is not going to be sensitive to these regular terms for reasons that you will see. For example, when you know, the interesting thing about the singularity is that when you do integrals, when you know, this is something you know from the Cauchy theorem. The nice thing about poles, for example, is that when you do an integral around a pole, you keep the singular part, you keep the residue of the pole. And if you do an integral around a branch cut, what you're actually computing is the discontinuity around this branch cut. So these are the parts of this expansion that are going to be, to which the theory is going to be sensitive. The regular part, really, you know, the theory doesn't really tell you much about it. Okay, you don't really use it. And as we see, one of the main quantities I'm going to calculate are discontinuities, and discontinuities are not, by definition, sensitive to this regular part. You could also say that because I'm neglecting the regular part, I'm losing information. Okay, that's also true. It's true that two functions that have the same regular part, different regular parts, but the same singularity structure, are going to give me the same type of series. Okay, so in that sense, it's true that, you know, and throwing away some information. So it's not clear that throwing away this information will allow me to reconstruct the full theory at the end. Okay, but the theory in itself is only sensitive to this singular behavior. So the way I'm constructing this thing is only sensitive to this behavior for reasons that will be, I think, clearer tomorrow. Yeah. Sorry? The truncated one, yeah. For the moment being, the thing is that I only define half of the theory. Now, with this Borel transform, I'm going to do a resummation, the Borel resummation. The Borel resummation is going to be much better than the optimal truncation, but I still have to introduce the Borel resummation. So this I will introduce tomorrow, okay? So the Borel transform has two good things. The first thing is that the singularities have information, and this is the information I explain how to extract today. The other use of the Borel transform is as an intermediate step to do Borel resummation. And with the Borel resummation, we will be able to improve, in some cases, on the optimal truncation. Okay? But this will be finished tomorrow. Okay? Yes?
So the singularities that lie along some dense closed cycle, which you seem to be ignoring in your lecture, can they also arise from some physical quantum theory conservative equations?
Yes. So these are I'm ignoring these type of functions because these functions have a lot of singularities, and then I'm gonna. But yeah, actually, this situation happens very often in physics, and one example is, I mean, maybe in physics. I mean, let me put it this way: in examples in quantum field theory, in which you look at perturbative series, you don't see this kind of behavior. Now, in string theory and in other situations, you find this type of things. And one example, it comes to my mind of this type of behavior is what is called the quantum dilogarithm. I don't know if you are familiar with this function. It appears very often in string theory, in complex Simons theory. What is called the compact quantum dilogarithm has this sort of singularity structure on the border, okay? As a function of its coupling constant. So it has a dense set of singularities. And another example that appears in topological string theory, sometimes you compute the expansions of in the string coupling constant. And one thing that you can actually realize is that this topological string free energy, for example, has dense sets of singularities in some sets, so that, for example, in some exponentiation variables of the string coupling constant, this is actually the dense set of singularities on the unit circle. So exactly like I was mentioning here.
But what we are going to learn from your lecture?
Sorry?
What we are going to learn from your lecture can also apply to those cases, or is
well, no, you cannot do it in this way. You have to be very careful because yeah, I mean, in these cases you have to work a little bit harder. Yeah, of course. But the good news is that in many quantum field theories, the structure of singularities is quite simple in the sense that you have, for example, lines of singularities where the singularities are spaced. For example, you have a typical situation in quantum mechanics. You have singularities in one axis, in one semi-axis, and they are spaced. So you have, for example, singularities at the integer numbers, one at the positive integer, 1, 2, 3, and so on. So I don't know any case in kind of conventional quantum field theory in which you have this situation of dense set of singularities. In standard, even in QCD, there is not much known about the perturbative series in QCD, but you don't have this dense accumulation of singularities. So this is good news. You can, in principle, use this technique. Okay. Yes.
You get a new function phi hat, and I assume you can also apply the same procedures to finding the singularities of phi hat.
Absolutely, very good observation.
Does it give new informations, or is it already considered if you consider all the singularity of the original functions? And the set of the phi omega, does it have some group structures or other structures?
Yeah. These are really fantastic questions. And the first question is that absolutely. Now we got this function, we got this series, right? We got this series, and now you can repeat the procedure, okay? And then you will get more singularities, and then you get more functions, and then you keep going. At some point, you get the total collection, and this actually is going to something I'm going to mention tomorrow. This is actually what I wanted to do for the start of my next lecture. But yes, you can do it, and then all this collection, in principle, at some point you end up with a possibly infinite set of functions. Now, in some cases, it might happen that in these new functions you go back to singularities that you had before, and this is actually what happens in the example of the 80 function, right? Remember here, I got phi 1. I look at the singularity of phi 1, and I got this phi 2. Now, you look at the singularity of phi 2. Phi 2 is going to have one singularity. And if you look at phi 2, you are going to look at the singularity of phi 2. You are going to recover phi 1. So here, the structure just has two functions. You have phi 1 and phi 2. Phi 1 takes you to phi 2, and phi 2 takes you to phi 1. So you are done. But in many cases, phi 1 takes you to phi 2, phi 2 takes you to phi 3, and you can go on like this. And then typically you have an infinite set. Now, the second question is there a structure on the labeling of singularities? And this is a very good question. In many cases, for example, in quantum mechanics or in even more sophisticated cases, we know that the location of the singularities is non-trivial. It's actually a subset of a lattice. So you have a lattice on the complex plane, and then the singularities are given by points in a lattice. So there is some sort of integrality structure, but not all points of the lattice necessarily appear as singularities. Okay? So sometimes only few of them, and so on. But in many cases, there is some sort of integrality structure behind. That's actually also a very important thing, which is not completely understood and not completely developed. Okay? But in many cases, you find experimentally that these singularities typically form some sort of lattice in the complex plane. So, for example, you have instanton type of singularities, as we will see. Instantons come in families of multi-instantons. So you have, you have one instanton, two instanton, three instantons. So you have some integrality structure, right? You don't have 1.5 instanton, right? So this structure, integrality structure of instantons, will reappear as some integrality structure for the singularities.
All right. One more question. It's okay. It's final question.
Is it reasonable to say that resurgence is less powerful in supersymmetric theory, where there is some non-renormalization theorems. Like
yeah, that's true. In a sense, in supersymmetric theories, what happens is that you have fine-tuned your parameters in such a way that, for example, many of these perturbative series collapse to one or two terms. So in that sense, you don't see the coefficients. But this is, in a sense, from the point of view of resurgence, what happens is that supersymmetric theories are very non-generic. So the perturbation theory is hidden. So some people, for example, have studied what happens when you have a supersymmetric theory and you introduce a small supersymmetry breaking parameter, and then just with a small supersymmetry breaking parameter, the series, the perturbative series that was 0 because of supersymmetric cancellation, suddenly comes to life, and then you can analyze it. But it's true that you cannot really sometimes you don't even have a factorial divergent series to start with. Okay.
So maybe reversing the logic, is there any difference? Like, is there any like signal we can detect from the like some semi-classical like configuration and computation to detect some non-renormalization theorem in this way? Because I don't know. I'm wondering if is there any.
Oh, I see. Mm-hmm.
Okay.
Well,
so, yeah. If you look at just SUSY, say you don't know the non-renormalization theorem, and you say you can still find the solution of equation of motion, something non-privative. I'm wondering if there's any some difference between SUSY and
right. Yeah. Yeah, sometimes people have tried to combine this in the sense that there have been some attempts to, for example, combine the structure of singularities here with non-renormalization theorems in supersymmetric theories. For example, some people claim that, for example, you have a supersymmetric Yang-Mills theory, some of these singularities will not appear because the theory is supersymmetric and so on, right? So, but in a sense, I think it's fair to say that for supersymmetric theories, in a sense, resurgence is too much, in the sense that, one of the good things about supersymmetry is that, perturbative series are often trivial, and then all these techniques do not apply. But it's also the case in supersymmetric theories that many of these series are also convergent. So you see, it's in a sense, resurgence is better the more generic is the theory. In a sense, that's true.
I see. Thanks.
All right. So now let's take a break, and we'll reconvene at 3:50. And let's thank Marinho once again for a great talk.
Thank you. Tomorrow I can use my.
Okay, good.
네, 이걸 좀 치워버리겠습니다.
컴퓨터도 쓴다고 그러잖아요. 아, 쓰나요? 쓸 가능성이 근데 반 정도는 쓰고.
아, 그럼 뭐 요걸 자기가 밀어서 하라 그래야겠네. 그렇죠?
이렇게 하면 되나? 이렇게 하면 되나?
닫아야 되겠네. 학원 호모가 있을 텐데.
핀 마이크는 있어. 아, 요거구나. 요 핀 마이크. 이거 엄청 잘 보이는데?
잘 보이나요?
저기다가 스크린에 보니까 엄청 잘 보이는데? switch.
The other way around seems natural.
You know which way this goes?
Yeah, I think. Then it's too small for adult's head, I think. Maybe we can do it the other way around. Have this go to the back front.
Ah, yeah.
That sounds.
Yeah.
Then it's.
Something like this.
No, it's for the neck or something like this. Yeah. You mean like
Oh, but this looks like it goes to the.
It's too low then.
Like.
Maybe that's the. Yeah, maybe that's the.
Oh yeah, you don't need a speaker, right?
Huh?
Here, it's not the earphone, right? It's just a mic.
Yeah, but
You don't have to put on your ear.
No.
So somewhere.
Yes, but
Uncomfortable or really?
it's okay. Like this.
Can you share the screen directly
To what?
to Zoom? Did you get the Zoom link from the
No.
from the secretary, Jungwon Yoon?
You mean for the Zoom?
Yes, Zoom. Well, can I connect here?
Yes. Yeah, I didn't do this before. What?
Can you? Did you get any email about this from the AP kiosk secretary?
Yeah, maybe. But actually, in the first lecture, I didn't do that. Was there a problem or?
Because previously we share the screen. It's not share the screen, but because through the camera, this shows.
Yes, then I have to turn on the Wi-Fi. Huh?
It should be more closer.
How does it go? Like this? Oh, I see. Mixed. Oh, okay. That's how I see. No, he says it should be like this. Like. Actually, this seems. Yeah, I think this is yeah. We'll see. Yes. Sorry, what was the name of the email? Yeah, but this is. There was one before. Yeah. In the end of this one? Oh yeah, this is. Sorry, this doesn't have a. Oh, okay. Well, I give it back to you, no? Yeah. But. Mhm. Oh, no, not this one. Do you know what happens when I? Yeah, but it shows now, but when I play, it goes away. Yes. Sure.
So please, yeah.
Okay, so please take seats, and Daniel will give his second lecture.
Okay, yeah, thanks a lot. Yeah, let's continue. Yeah, I'm gonna try and make this fully multimedia, this lecture. I'm gonna finish off the first lecture with another 20 minutes, half an hour with slides, and then I've decided to try out how these blackboards work, okay? All right, so just this is a reminder of what we did last time. I discussed kind of the meaning of cosmological correlations, how we can measure them at different moments in time in the history of the universe, learn about both how the universe is expanding, what type of phases it went through, and what the universe, the composition of the universe, and so on and so forth. And it described in a bit of detail this transfer of information from primordial initial conditions to the CMB power spectrum. So far we have just worked with the free theory of these fluctuations. So we have studied the quadratic Lagrangian, which was a collection of simple harmonic oscillators with time-dependent masses. And then we calculated the quantum variance of those collection of harmonic oscillators, and that gave us the initial power spectrum for these fluctuations. Something I didn't highlight, but which is natural because we so far have only studied the free theory, is that these fluctuations are purely Gaussian at this level of approximation. So they're drawn from a Gaussian probability distribution that I've shown you here, with a variance, which is the one that we just calculated, okay? And in fact, you can put observational bounds on how closely this primordial distribution from which we're drawing the fluctuations, how closely that is approximated by a Gaussian. And so one measure of the type of deformation, the skewness away from this Gaussian shape, is to take a putative 3-point function of these fluctuations and divide it by appropriate powers of the 2-point function, okay? To have equal number of powers of zeta upstairs and downstairs. That's a number that you can calculate in principle. It's momentum dependence because it depends on which triangle configuration for this 3-point function you look at. So we will talk more about this, but just if you pick one specific reference 3-point shape and ask what's the amplitude of that 3-point configuration relative to the 2-point function, then you can measure that deviation, and we call it this parameter FNL. And so this parameter FNL is found to be less than 10 to the minus 3. FNL of 1 would correspond to a completely non-perturbative theory where this expansion into a power spectrum and a small correction, the 3-point, 4-point, and so on, doesn't make any sense. So that's where the theory completely breaks down, the perturbative description. So we know that we're already way into the weakly coupled regime, okay? And in fact, it's fair to say that the universe is more Gaussian than it's flat. So you've often heard about the flatness of the universe. The flatness of the universe is only established at the percent level, while this is measured at or constrained at the sub-percent level. So the universe is more Gaussian, more weakly coupled than it is flat, okay? Okay, however, it's also a little bit disappointing because it's hard to learn about physics if you have only measured 2-point functions. Yeah, this would be like in particle physics if we tried to reconstruct the standard model from just measuring propagators. Okay, so large propagators tell us like which stable particles there exist in the world. There's an electron sitting here and it travels from one point to another in space-time. That's described by the propagator for the electron. So we learn certain things about the electron, like its mass, but everything else is dictated by Lorentz symmetry. So there's not very much we learn about the dynamical content of the standard model if all we had access to was propagators. But this is analog, yeah? We only have the 2-point function. We have learned some things. We have learned kind of a scale, a size of that 2-point function, and some slight scale dependence, which is an indication of time-dependent dynamics before the hot Big Bang. So it's not nothing. We have learned certain things. But if you really want to zoom in into the kind of the microscopic origin of what created these fluctuations, we're kind of limited at the moment to just 2 numbers, an amplitude and a tilt of that spectrum. And so that motivates kind of looking beyond the 2-point function and try to measure at a, possibly a small level these higher point correlations. Okay? And so for the entire rest of this course, I will talk in a lot of detail about how to compute, how to analyze, what type of insights we can get by measuring these higher point correlations. Okay? So I will first give you a sketch now, kind of qualitatively, and then for the rest of the lecture on the board, I will actually introduce to you a technique for calculating these higher point correlations very explicitly, called the wave function of the universe. All right? So first of all, let me just make this slightly more formal. So the main diagnostic that we have for the so-called primordial non-Gaussianity is the bispectrum. That's the 3-point function in Fourier space. Yeah, it's called bispectrum because there are 3 points. Okay, and the 4-point function is called the trispectrum. I don't know where these terms came from, but it's just if you calculate a 3-point function in Fourier space by translation invariance, there's always an overall momentum conserving delta function up front. Okay, that means that this 3-point function has to be a function of a triangle shape, where the side lengths of each of these triangles correspond to these Fourier vectors, and they have to form a closed triangle because of this delta function. Okay, so the signal only has support on these closed triangles, but the triangle shape is arbitrary. You can have arbitrary shapes of these triangles, and the amplitude associated with each of these shapes is a function, and it's in general actually a function of 6 variables, and often by symmetry, by scale invariance, and so on, you can reduce the number of variables to like 2 or 3. And so there's a functional dependence that characterizes the shapes of these non-Gaussian signals. Okay, so you can already see that while the power spectrum was just 2 numbers, a nearly scale invariant spectrum with a small tilt. So there was an amplitude and an NS value, 2 numbers. Now there's a whole function worth of possibilities. And so in principle, by studying that function, we can learn much more about the microscopic features. Just like in particle physics, when we scatter particles, we measure cross sections and we measure, ingoing and outgoing S-matrix elements. This is the analog of the S-matrix process in particle physics. I already introduced this kind of schematically, but now I can do it more formally. So this amplitude of non-Gaussianity is just the size of this bispectrum in the equilateral configuration. So imagine you take an equilateral triangle, and the signal will have a certain size in that triangle, and then I'm just dividing it by 3 powers of the square root of the dimensionless power spectrum. Okay, roughly speaking, just the amplitude of the fluctuations, 3 powers thereof. That gives you this value f and l. And then for scale invariant fluctuations, in fact, the dependence on k cancels upstairs and downstairs, and you just get a number that doesn't depend on k anymore. Because scale invariance means that the signal just changes in a specific way dictated by scaling symmetry as I'm rescaling the equilateral triangle. Okay, so this will just be a number independent of k in a theory that's perfectly scale invariant. Now then, most of the information about non-Gaussianity or the microscopic physics during inflation is encoded in this shape of non-Gaussianity, namely how the signal changes as I'm deforming the triangle. So in particular, if most of the signal is in the so-called equilateral configuration, so that you have a large signal when the triangle is equilateral, and then when I change it away from equilateral, the signal gets smaller. That's a signal that's typically associated with higher derivative interactions. Because interactions mean that signals get suppressed when I'm getting far outside of the horizon. So I only get large signals when all the wavelengths are roughly equal, namely the horizon size corresponding to each of these different waves. Okay, so that's one type of signals that you can get if there's additional, not just potential interactions, but derivative interactions of the field. You get equilateral non-Gaussianity. If you have an extra massive field during inflation, and these extra massive fields are easily generated because the energy scale during inflation was so high. So there can be spontaneous particle production during inflation. And this mass can be as high as 10 to the 14 GeV. So if the energy scale during inflation is 10 to the 14 GeV, I can produce 10 to the 14 GeV scale particles. But then massive particles also during inflation are very short-lived, and they will decay into lighter particles like the inflaton. And that then produces non-Gaussianity in the decay products. And so a signal of that type typically is maximized in the so-called squeezed limit, where one of the momenta is very short. This corresponds to a very long wavelength fluctuation in the sky. And the 2 remaining fluctuations are long. They have large k number and so short wavelength fluctuations. Okay? So basically what happens there is that there's a massive field that decays, produces these 2 states, and then that produces a background wave. And that background wave modulates the interaction between 2 other waves. Okay, so that's how 3 waves can interact when they have different wavelengths. So those are the 2 main types of non-Gaussianity. There can be a third one, which is the so-called folded non-Gaussianity, when 2 of the wave numbers become collinear. Yeah, just point in the same direction, which means that you're folding the triangle onto one of its side lengths. So here 2 of these momenta become collinear and you're folding up the triangle. This can only happen if you're not in the Bunch-Davies vacuum. So in the Bunch-Davies, actually I just learned that Bunch-Davies vacuum should be called something else, but I forgot the names. Yeah, so in the Euclidean vacuum, as Marcos told me, in that vacuum, you should not have that singularity because you have only positive frequency modes in the initial conditions. And it's a negative frequency component that leads to this folded non-Gaussianity. Okay. Any questions about this? Okay, so let me talk a little bit more about equilateral non-Gaussianity because that's the type of non-Gaussianity that you get in this effective theory of the Goldstone boson that I described earlier. Yeah. So notice when we were writing down this effective theory for the pi field, it had only derivative interactions. And that's a consequence of the fact that this is a Goldstone mode of broken time translations. There's no mass term for pi. There's no polynomial interactions for pi. All the interactions are either time derivatives or spatial derivatives, as you can see here. Okay. So we then also saw that this can change the sound speed of the fluctuations because it breaks the symmetry between time and space to having a rolling background. But now, if the sound speed is small, this then also necessarily induces a large three-point interaction by symmetry. So you're just not free to have a small sound speed independent of a large three-point interaction. So that these two are tied to each other. And in fact, this FNL parameter that you're generating from this interaction here scales as 1 over the sound speed squared. Yeah, so for a small sound speed, this becomes large. And as I said before, for equilateral non-Gaussianity, these correlations are larger when the fluctuations have comparable wavelength. And you can, in fact, calculate this bispectrum, and it has this form. So it scales as factors of K1, K2, K3. These are just the magnitudes of the side lengths of the triangle. Sometimes I will call these energies. It's just the magnitude of each of the wave vectors. And then very importantly, this has a pole when the sum of all the 3 Ks goes to 0 of a certain order. And in fact, we will see later that this singularity here is very important. It's a signature of having just contact interactions in the bulk spacetime. But we will discuss the singularity structure of these correlators a bit more. But you can already see this happening here. But let me spend a few minutes discussing actually what you would learn by measuring such an equilateral non-Gaussianity. Okay, I should of course make clear that we haven't so far measured any of these non-Gaussian signals. But if you were to measure them in the future, what could you possibly learn? And in particular, is there some threshold value for this FNL? At the moment, FNL was just a number, and it would be nice to normalize this number relative to something. Yeah, to learn, is there a specific threshold value of FNL where the theory transitions from, one very specific corner of parameter space to another corner, or is this all just continuously connected and arbitrary? Okay, and so I will actually show you that there's a unitarity bound that puts a very specific value of FNL, namely 10 to the minus 5, to a preferred scale. Okay, so to do this, let me go back to this effective theory of the Goldstone and actually describe the relevant energy scales of that theory. And this will come back to some of the questions that we already had in the first lecture, namely what's the symmetry breaking scale and so forth. So minimal models of inflation, like the ones I've just described in terms of this effective theory, are characterized by just 3 energy scales. All right. So first of all, there's the Hubble scale and the Planck scale. So the Hubble scale is dividing modes into wavelengths that are larger than the Hubble radius, which are superhorizon, and modes that are shorter than the Hubble radius, which are the subhorizon modes. And we already discussed that when a mode goes from subhorizon to superhorizon, it freezes and becomes an initial condition for the classical universe later on. But the frequency scale at which this happens is precisely set by the Hubble scale. Okay. And so a given model of inflation will have just some certain value of h, okay, and we have no freedom to tune the value of h. And so that's why what we're observing in the sky in this analogy with particle physics is basically like a fixed energy collider. So we're observing kind of these collision processes in the early universe, corresponding to these higher point interactions, but we don't have the freedom to increase the energy and kind of see higher order things like we have in particle physics if we're lucky. But instead, of course, this scale is just set for us, And all we can do is to make precision measurements and try to measure kind of small corrections by measuring things more accurately rather than at higher luminosity. Sorry, with higher luminosity, but rather than at higher energies. Okay. Now, the second energy scale is the Planck scale. Okay. And of course, that's also just a fundamental constant that's fixed for us. And the hierarchy between the Hubble scale and the Planck scale is a free parameter in an inflationary model that sets the amplitude of tensor fluctuations or gravitational wave fluctuations. So if in the future we were to measure gravitational waves, it would instantly tell us how far separated the Planck scale and the Hubble scale are from each other. At the moment, we just have an upper bound, which I've indicated here. This is the power spectrum of tensor fluctuations. Notice it's exactly the same as what we calculated in the first lecture, which is this h over m Planck squared factor without the 1 over epsilon. The 1 over epsilon just came because I went from a canonically normalized field to the Goldstone field. There was an extra factor. The graviton field itself is already canonically normalized, and so it just receives de Sitter fluctuations of order h over m Planck squared. Okay? So it's exactly the same calculation that we did this morning, except it's easier because, first of all, there's no gauge issues, and then also there's no conversion from the canonically normalized field to the physical field. So we can calculate the power spectrum, we can compare it. There's ways of constraining the amplitude of these tensor fluctuations. And so this power spectrum is constrained to be less than 10 to the minus 10. Okay? So it's basically constrained to be an order of magnitude smaller than the amplitude of the scalar fluctuations. Okay? And that puts a bound on the hierarchy between the Hubble scale and the Planck scale. It basically tells us that the Planck scale has to be a factor of 10 to the 5 times larger than the Hubble scale. Okay? And so that's where this number of 10 to the 14 came from. So the maximum value that the expansion rate could have had during inflation was 10 to the 14 GeV. If it was larger than that, it would produce too much gravitational waves. Right? Okay, and then finally the last scale, which is the scale that makes the whole theory dynamical, is this f pi, the symmetry breaking scale, which arises because the background is not exactly the Hubble scale. So in slow roll inflation, this f pi scale to the 4th power is just the speed of the inflaton field squared. More generally, if we had a sound speed, this is just m Planck squared times h dot squared times the speed of sound. Okay? And in fact, this scale, so actually this is not something I showed, but if you take the power spectrum that we calculated earlier, that power spectrum can be written purely in terms of a ratio of h over f pi to the 4th power. So this epsilon factor that we had that appeared in the power spectrum for the scalar fluctuations precisely gets absorbed into the definition of this symmetry breaking scale. Okay? So while the tensor fluctuations are characterized by the ratio of h over m Planck, the scalar fluctuations are characterized by ratio of h over f pi. Okay? And since we have measured the scalar fluctuations very precisely, we know that their amplitude is 2.2 times 10 to the minus 9. Okay? We actually know what that ratio is. Yeah? We don't know what each of them individually is, how large it is, but we know exactly what their hierarchy is. In fact, it's 58. You can calculate, yeah? So this symmetry breaking scale is a factor of 58 times bigger than the Hubble scale. And then the Planck scale is another factor of 10 to the 50 times bigger than the Hubble scale. Okay? So, just to summarize, there's 3 important scales that characterizes the minimal model of inflation, which are these 3 scales. And we know the hierarchy between 2 of them, and not the 3rd one. Everything is normalized to the Planck scale, but we don't know the overall normalization. Okay, finally, so this is all in the absence of any non-Gaussianity. This is just in the free theory we have these 3 scales. Now, if there were higher point interactions in my Lagrangian, like this small sound speed thing demands for me, then there would possibly be an additional scale at which the theory becomes strongly coupled. Yeah? So the coupling of the theory will depend on frequency, and as I go to higher and higher frequencies, it becomes more and more strongly coupled. This strong coupling scale depends on the sound speed, and so for small sound speed, the theory can become strongly coupled close to the Hubble scale and at a scale that's smaller than f pi. Or, for example, in slow roll inflation, the theory only becomes strongly coupled at the Planck scale, and this lambda scale would be all the way up to the Planck scale. And so we would like to decide which is which. Yeah? Is the theory closer to slow roll, where this lambda scale is larger than f pi? Or is it very different from slow roll and it arises actually from some strongly coupled background like QCD, and the fluctuations are like pions of QCD? Yeah. So you can think of, maybe the question is inflation more like the Higgs mechanism, where the theory of W bosons gets gets UV completed by the Higgs, or is it more like Technicolor, where the theory of the W bosons is UV completed by strongly coupled physics? Of course, in the standard model, we know how this question was decided, but inflation actually we haven't yet decided that type of binary question. But this FNL parameter precisely depends on the ratio of h to this new scale lambda. So again, everything is just fixed by a dimensionless ratio of these energy scales. And so this FNL for equilateral non-Gaussianity just depends on h over lambda squared. So if we were to measure an FNL, it would tell us this ratio h over lambda. And so then we could translate this into a hierarchy, and we could answer the question whether this lambda appears closer to h or further from than f pi, or further from it than f pi. Okay. So it turns out that if you convert this into a value for CS, slow roll inflation corresponds to CS exactly 1, and then perturbative corrections to slow roll are values that don't deviate from 1 too much. It turns out that the transition point where it's not reasonably called slow roll anymore is at a CS of 0.31. Okay? And the reason you can be so precise about this is because you can actually calculate kind of a unitarity bound from just 2 to 2 scatterings of these pi's, and with all factors of pi, and actually infer this value. Okay. And then there's a lower bound here, 0.02, which is actually observationally the limit of what's allowed. So if CS was smaller than 0.02, this is already ruled out by observations. Okay. So at the moment we're living here, there's still this window in which it could be non-slow roll. If we further constrain and not see non-Gaussianity of this type up to this level, we would have ruled out that it's not slow roll, and we could start calling it slow roll inflation with small corrections. Yeah. Unfortunately, observationally, it's hard to get there. This is like it doesn't look like much, this factor of 10, but this factor of 10 will cost us a few decades of lifetime. Okay. Okay, maybe let me skip this. This is what I just mentioned before for folded non-Gaussianity. Instead of this pole that I saw for equilateral, you need to have this pole with a minus sign. This can only arise if there was negative frequency modes and initial conditions. So if you were to see something like this, like a singularity or at least an enhanced signal in this folded configuration, it tells you that you're not in Bunch-Davis to start with. And then we already discussed Swiss non-Gaussianity. Maybe we come back to it in the final lecture. Okay, sorry, any questions about this part? There was something in the chat, but is it, or was this just you chatting? You. All right. Okay, so a final slide before I move to the blackboard. So I've so far focused mostly on practical motivations. Yeah, the things that cosmologists care about, why they care about measuring cosmological correlations in the first place, and there's various physical interests. Of course, the grandest of all is just the origin of structure in the universe and everything you see around us. That's pretty good. Yeah. Sorry, is it? Oh no. Yes. Sorry. Yes, actually, sorry, this scale lambda has nothing to do with the cosmological constant whatsoever. In fact, this scale h is more closely tied to the cosmological constant. So by the Friedmann equation, the cosmological constant during inflation is related to h by Friedmann, yeah? And so there's a formula that says h squared equals the other lambda for the cosmological constant, or let me call it rho lambda for energy density, divided by m Planck squared, okay? That relates the effective cosmological constant during inflation to the expansion rate during inflation. This unfortunate scale, this scale that I called lambda here, is just a scale that arises if I were to take my Goldstone Lagrangian. Notice that the Goldstone Lagrangian has a not canonically normalized pi. If I had canonically normalized my field pi, so maybe this is actually worth saying. Yeah, sorry. So if you look at this, notice that this kinetic term, here, is not canonically normalized. So I need to do two things, and also it's not actually Lorentz invariant. So let me do two things. Let me first rescale my spatial coordinates to absorb factors of CS, to kind of reintroduce a fake Lorentz symmetry to make time and space equivalent again, just by a change of units, basically. So I can do that. So that will absorb this factor of CS, but then there will also be an integral measure that has 3 powers of CS from just d cubed x. Yeah. So if I'm changing my x units, I also have to change the measure of my integration. So that's not seen here because I'm just rounding a Lagrangian density. But if I look at the action, there should be also an integral over d3x. That will produce 3 powers of CS. That gives me then a prefactor that's m Planck squared h dot times CS. Notice that that's what I called f pi to the 4th, with one positive power of CS. That's how this arises. Okay. And then if I now take this and canonically normalize the quadratic action, basically by absorbing this prefactor into pi, then these higher order terms now really become irrelevant operators in the usual sense. They all have mass dimension 1, and I then divide them by mass dimensions. And for CS, that mass dimension is what I called lambda. So then this would really become a dimension 6 operator. Yeah, it's 3 powers of pi and 3 powers of derivatives. So this would then be dimension 6, has to be divided by a mass scale squared. That mass scale squared is what I called lambda. Okay. Okay. Sorry, one too much. Okay. Yeah, so as I said, I mostly discussed practical issues. So then for the rest of these lectures, we were going to get a little bit more conceptual. What I will first do is introduce you to 3 different ways to compute these correlation functions, these higher point correlation functions, and mostly 3-point functions and also 4-point functions. And the 3 ways of computing are the so-called in-in formalism, or Schwinger-Keldysh formalism. In fact, we will not have time for this. So actually, I will immediately skip the in-in formalism. You can read about it in the lecture notes that I put online. And instead, I will focus on 2 alternatives. One is called the wave function approach. Okay. And this is not so often taught, so I think it might be a good way of showing you how this works. The wave function is kind of it's complementary to the in-in formalism. Of course, in the end, all of these approaches give the same answer. But we will see that the wave function has slightly nicer analytical properties. And also in terms of the bootstrapping, it's the fundamental object from which the bootstrapping starts. And then this bootstrap approach is just new. And so otherwise, these approaches would be kind of a few decades old. And so, yeah. So I will focus on these last 2. And as we will see, this will then lead us actually to questions of kind of more conceptual nature about how quantum fields behave in an expanding space-time and so on. All right. Okay, so maybe I switch to the blackboard now. Or should I leave it here? Leave it here? Okay. Is this good enough to read on the camera? Yeah. Yeah. If I get too small, then let me know. Okay. So the first thing to discuss is this wave function approach for calculating fluctuation. And so I will introduce an object called the wave function of the universe. And so the idea is that so when we are calculating inflationary fluctuations, we always calculate them in a quasi-de Sitter space-time. So there's a quasi-de Sitter. And de Sitter spacetime has a future boundary at eta star equals 0. And sorry, I think in my slides I called this tau star, like conformal time tau. Now from now on I'm going to use eta. Okay, don't ask me why, but just because my notes actually have tau, I don't know why my slides were using. Sorry, my lecture notes have eta, and the slides were using tau for no reason. Except that tau looks more like time, so in introductory slides this is somewhat easier. Anyway, this is the same as what I previously called tau. It's conformal time. Conformal time during inflation runs from -infinity to 0, so there's a future boundary of the de Sitter spacetime that lives here. And there's spatial fluctuations. So this axis here is space, and time runs upwards. Okay. So there's two sets of fields that I want to distinguish. So first of all, there's a field capital phi. There's a function of eta and x that lives in the bulk. So this is a bulk field. But then that bulk field also, of course, has a boundary value, which I'm going to call little phi of x. Yeah. So that's just the asymptotic value of this bulk field when conformal time goes to 0, or sometimes we will keep this eta star finite. Okay. It's sometimes a little bit tricky to take this limit as eta star goes to 0 because there can be II divergences. And so then I will have to keep eta star finite as a regulator and think of the connection to the late universe at the finite value of eta star. Okay? But in any case, this boundary value is just the bulk field evaluated at eta star. Okay? And so then the wave function of the universe is defined as a wave, and actually more correctly, it's a functional. It's a functional of this field profile phi of x. And when this becomes a quantum field, there's kind of eigenstates of this field operator. And so those eigenstates can have an overlap with the initial vacuum that I'm going to call omega. Yeah? So this is the vacuum state. When I evolve it forward from -infinity to this boundary, and I'm calculating the overlap of this vacuum state with some arbitrary field configuration that could possibly exist at late times, and that gives us a wave functional. Okay? All right? And so then from this wave function, I can calculate boundary correlators. So in particular, I can calculate phi 1 to phi n. This is going to be a shorthand notation for the value. So phi a, for example, is the value of the field phi evaluated at xa. Okay? So if I calculate an endpoint function, I just want to calculate the expectation value of this field at n different points in space. And that's defined as a path integral over all possible field configurations, phi 1 to phi n, weighted by the square of this wave function. Okay? So that's just the ordinary Born rule of quantum mechanics, that if I have a wave functional, I can square that wave function and I can calculate correlations in that state, yeah, namely the forward evolved vacuum state, via this path integral. Okay? Okay? So I'm writing a bit big, so I'll switch here. I hope it's okay. Okay, so then in perturbation theory, we then expand this wave function in powers of the fluctuations. Yeah. So yeah. Okay, so here I've actually done two things. I've taken each field phi of x and I've written it in terms of its Fourier components, and I've then expanded out as an infinite series of fluctuations of this field phi. Okay, and so then what you generate here is so-called wave function coefficients. Which are the coefficients that arise in this expansion here, okay? And those are theory dependent. In fact, what we eventually want to calculate in perturbation theory are these wave function coefficients. Yeah. So there's in particular going to be a coefficient for the 2-point function, for the 3-point function, and so forth. Okay. Oh yeah, and I should have said this notation here where I'm putting an underbar under the k just means that this is a function of all the different k's. Oh yeah, this is bad on the board. Ha. Yeah. Actually, in the lecture notes, so in the lecture notes, my vectors are bold-faced. Okay. And then I put an underbar under the vector to denote the collection of all n vectors associated with each Fourier mode. I'm realizing on the board there's now two different underbars. So yeah, I could put a vector as in this notation, and then this would be an underbarred vector. But I'm surely going to not keep this consistent. Okay, so from the context, we will just mean, and it's not going to be very important to know which is which. Okay. Okay. So now, by translation invariance, this wave function coefficient always has a momentum conserving delta function. Like this, and then a function. Yeah, and we already saw this when we talked when I showed you the bispectrum. This was a 3-point function in momentum space. There was a delta function up front, and then there was this extra bispectrum function. This is the analogous, but the higher point generalization of that bispectrum, but just for the wave function. Okay, and this is not an assumption, but this is what you always have to find. Unless you broke spatial translations as a symmetry, you will always find this delta function, okay, and this remainder here. And so since we will always find this, we can always focus on this remainder function, okay? And what people then also often do is they write this remainder function as a correlation function itself of an additional so-called dual operator. Okay. Yeah. So since this depends on the n different vectors, you know, you can actually just formally express this as a correlation function of an operator. Okay. Here I've put a prime on the expectation value to indicate that I've stripped this delta function. So this is the same as the ordinary correlation function of a set of dual operators, except that you should not expect, you know, you should have removed the delta function because it's already taken account here. Okay. And so, for example, when we had this bulk field phi, there will be not a scalar operator O living on the boundary. And if you have the graviton fluctuation gamma ij, there's the stress tensor of the theory Tij that appears as a dual operator. Okay. So in ADS-CFT, of course, this language has kind of deeper meaning. And there's an actual conformal field theory living on the boundary where these operators have a life of its own and so on. We so far haven't actually discovered this deeper meaning of these operators. At the moment, this is just notation. I didn't have to do this. It's just for convenience because later it allows me to label different fields in a convenient way in terms of this notation here, rather than just writing this little phi of n as a function. Okay. But at the moment, we haven't done anything. We had this wave function. We expanded it in fluctuation. There will be coefficient functions or kernels that we call the wave function coefficients. Okay. And we want to study these objects. Okay. So at the moment, there's not yet deeper physics behind all of this. Sorry? Yeah, so in DS-CFT, the hope would be that these have some more intrinsic meaning, that there's a conformal field theory that you could study on your own, right? And that theory would actually define non-perturbatively what this conformal field theory in DS looks like. We're very far from something like that, okay? So far, we've only discovered trouble. Yeah, that CFT is kind of unconventional, you know, notions of unitarity are kind of harder to define in this Euclidean spatial slice and so on. We can talk about this more when we come to the conformal bootstrap, cosmological bootstrap, because it's kind of a baby step of something that's closer to DSCFT than what we currently have. But indeed, exactly. So at the moment, I'm just calling this notation. The aspiration of DSCFT would be have something that's closer to ADS-CFT, where these are operators with an intrinsic physical meaning that we can understand better. Yeah. Sorry? Yeah. Eventually will be a CFT because the boundary symmetry in de Sitter space is a Euclidean conformal field theory. Yeah. So in fact, we will discuss tomorrow and the day after a lot how these correlation functions or wave function coefficients are constrained by this underlying isometry of de Sitter space, the fact that it's living in de Sitter space and not some arbitrary background spacetime. That will lead to constraints because the entire evolution is de Sitter symmetric, and the fluctuations at the late time boundary must inherit some of that symmetry, which is a conformal symmetry. Yeah. So I hit quasi de Sitter. Actually, for most of actually you can. We can talk about this. It's always going to be a small breaking of de Sitter that we can treat perturbatively, and so most of my discussion actually will be valid. Will be for perfect de Sitter because it's easier as a kind of toy, and then we can talk about yeah. In fact, there's two different sources of breaking of de Sitter symmetry. One is just the background geometry, and that breaking we already know cannot be far from de Sitter, so it's always going to be a weak breaking. And then there can be bulk interactions like this sound speed theory that had higher derivative interactions in the bulk that can also break the symmetry. And we would have to treat those two separately. So whether the final boundary theory is conformally invariant will depend on both things. Whether the interactions in the bulk spacetime are approximately de Sitter invariant, and whether the evolution of fluctuations in the bulk is approximately de Sitter invariant. Okay. The second one is guaranteed to be the case, but the first one is not. Actually, okay. So last minute, I decided to change an order of presentation in my lecture notes, and I now discovered that this was a bad idea. And actually, this is why I was pausing on the board and so on, and I was, because I realized there was trouble, and I couldn't pinpoint where it was. Now I understood. Okay, let me actually, there should have been a line before this one. And let me add it, and we will demystify. Notice also that I didn't say anything about where this exponential here came from. Yeah. And so this was, okay, apologies. So there's something that I should have said before. So this wave functional as a function of phi can also be written as a path integral over the bulk field weighted by e to the I s of phi. Okay? And this is basically the same formula as also Marcos, I think, was showing in his lecture earlier. He was just showing the Euclidean version with a minus sign here instead of the I. Okay? So you can define this wave functional as a path integral over e to the I action. Okay? With boundary conditions set at early and at late times. So you need to impose that at late times, this bulk field, so at eta star, it becomes the prescribed boundary value phi. And at early times, so eta going to minus infinity, and here I'm defining minus infinity with a minus I epsilon, the bulk field should vanish. Okay? This is a fancy way of describing the Bonch-Davies initial condition, that it has only positive frequency solutions. Yeah, there's an I epsilon prescription that projects out for me all the negative frequency solutions, and the only normalizable modes here are the ones that have positive frequency. And so sometimes one uses the shorthand where one doesn't show this I epsilon, and just says that the negative infinity value of the field vanishes, where it's always understood, when suitably rotated into the complex plane, the time integration. Okay. So those are my two boundary conditions. At late times, the bulk field has to approach the boundary value that I just prescribed, and at early times, it has to start in this e to the I k eta. Sorry, big. Oh, no, this is not. This is not meant to be a 0. This is like an O. Yeah, my bad. But yeah, this is an O. Yeah, it's an operator, scalar operator O. Has nothing to do with the scalar number 0. Okay. All right. And then actually we always will. So in this course we will only be working at tree level. And at tree level, it turns out you can approximate this path integral here just by its saddle point, which is e to the is, the classical value of the field, the on-shell action evaluated for the classical solution. Okay? That's what defines the classical solution, in fact, that the action is minimized. And so this path integral also has a saddle point approximation here at this value. And it's this function here that I'm expanding out, and that's why this exponential was also appearing naturally. Yeah, I've naturally expanded out things in exponentials because there was an e to the is that appears in my definition of the wave function. Okay? Is that clearer? Sorry if this caused confusion. Yeah. Yeah. Yes. It's a sphere. It's a sphere. Yes. Yes. Yeah. So people like doing these calculations on the sphere. Yeah. In our case, actually, I will do very explicit calculations, extremely explicit calculations in a moment, in fact. And we will always be relying on, since we're using the saddle point approximation, the calculation really reduces just to finding the classical solution with the right boundary condition. Yeah. So there's no real quantum. Yeah. So quantum mechanics is yeah. The only problem will be that this theory here can be nonlinear. Okay. So in fact, if I have time in a moment, I want to show you actually how to compute in this formalism the harmonic oscillator, and in fact the anharmonic oscillator, which I was very happy to see in your lecture. So we're going to calculate the anharmonic oscillator from this wave function of the universe. And so the whole issue then just is that the anharmonic oscillator doesn't have an explicit solution for arbitrary coupling, yeah, and there's bigger issues that you discussed. And so you have to then solve perturbatively the equation, classical equation of motion for an anharmonic oscillator iteratively. So you first solve the free theory, use that as a source with a Green's function, and we will see all of that happening. And that generates for you a Feynman diagram expansion of the theory of the anharmonic oscillator. Okay, but it's still just solving a classical equation of motion and then feeding it into the action. So it's not so hard, and I don't think going to the sphere would help us. But maybe if you want to calculate loops and such things where you can't rely on the saddle point approximation, then maybe going to the sphere has some benefits. Yeah. Yeah, they will have to. I mean, yeah, consistent things have to agree if you do it consistently, and so, yeah, they should agree. Okay. All right. So far I've just defined a few things, and so in particular I've defined these fundamental objects, which are the wave function coefficients, and I've written them two different ways, either as these functions here, or as correlation functions of dual operators. Okay. And so that's now an infinite expansion. So there's a 2-point function, 3-point function of these operators O that multiplies the fields. Okay? And then I can go back to the definition of the boundary correlation function over here, and I can just perturbatively evaluate this integral. Okay? So at lowest order, this is just a Gaussian integral. And so when I perform the Gaussian integral, I will find that the 2-point function of two fields phi is just 1 over twice the real part of the 2-point wave function coefficient, OO. Okay? maybe as an exercise you can try to reproduce this. If I take the formula over there, I plug it into here and square it and expand out, then the first integral is just Gaussian, and I will just pick up the variance of that Gaussian, and that variance will just be the inverse of the wave function coefficient. Okay? So there's a one-to-one mapping between the two-point function of the field on the boundary and the two-point function of the dual operators on the boundary. Okay? For the three-point function, this is all in momentum space. Yeah. And it's all with delta functions extracted. Of course, you know, it would be hard to interpret this formula with an inverse if there was still a delta function downstairs. No. This is all cases where, so from now on I'm not going to put these primes anymore, but all correlation functions will always have these trivial delta functions subtracted. So then the three-point function you will find as twice the real part of the three-point function of O divided by the product of all possible two-point functions, and also their real parts with a factor of 2. Okay? So this is the two-point function of the operator O1, the two-point function of the operator O2, and the two-point function of the operator O3. Sorry, and I should have said this is 1, 2. This could be 1. Sorry. Well, let me not. Yeah. Well, let me for the moment. Let me assume that all the fields are the same, so we don't have to distinguish them. And then finally, so the first more non-trivial case is kind of the four-point function, where you would get that these are related to the four-point function, again also with a real part of the dual operators divided by the 4 powers of a two-point function, plus so here now you can have a connected and a disconnected piece, yeah, because the wave function coefficients are an expansion in kind of a two-point function, a three-point function, 4-point function, and now the 4-point function for the boundary correlator has a connected piece, and can also has kind of a disconnected piece, which is kind of in diagrammatic language. Well, sorry, maybe if this is the boundary, I can have something like this, but I can also have 2 3-point functions that create by an exchange a 4-point function. Okay. Sorry. Sorry, squared. Yes, of course. Yeah. Can the 4-point function of O be? You mean if you can do some kind of OPE expansion? And let's get back to this actually, but in principle not, because you could have like a really just an honest-to-God 4-point bulk interaction, and there's no way of expanding that further. It just exists as a coupling, and yeah. Sorry, and yeah, and so by X I just denoted the case where there could be a 3-point coupling where an additional field mediates an interaction between this. It could also be sum over X. Yeah, this is very schematic. Yeah, if at the moment actually, yeah, I could have just called this O and not introduce X, because right now actually we just have the theory of the field phi. Maybe let me just call it O and not, because and then this would be 5th power. Yeah. If we just had a single scale and the bulk, then this X wouldn't exist, and we would only have O's. Okay. Okay. All right. So to make this less abstract, let me actually show you how to do a calculation with this in quantum mechanics. Yeah, namely the anharmonic oscillator, and especially because that calculation will already illustrate kind of all the features that we need in quantum field theory. So the extension from quantum mechanics to quantum field theory is rather doesn't have many more subtleties in it. And so we learn everything we need to learn, in fact, from this quantum mechanics example. Okay. Yeah. Yeah. Yes. Yes. Yeah, this is essentially, I think, what's done in informalism. Yeah. So in informalism, you calculate this boundary wave function directly by taking a field, the vacuum state in the past, evolve it forward to a boundary, calculate the overlap with the fields on the boundary, and then evolve it back. And that's why it's also a closed time contour. It's also sometimes called closed time formalism. And because you have to calculate things in two in states, and that's why it's called in. Okay. So I think that's closer to what you're asking. So the what? Yeah. Indeed, indeed, indeed. So when one calculates, for example, an exchange diagram like this one, yeah, in the informalism, actually this corresponds to 4 diagrams, because these 2 vertices here can be ordered in 4 different ways on the in contour, which is there's an ingoing contour and a outgoing contour. I can put these 2 vertices on the same side, both on the ingoing, that's one way, both on the outgoing, or 2 different inverse orderings. Yeah, and so there's 4 diagrams, in fact, that I have to calculate for the informalism. Okay, while for the wave function there's only 1 diagram, and the reason these 2 things give the same answer is actually subtle. It's because of this formula that I just erased, that the correlator is not just one wave function coefficient. The correlator is a sum of the 4-point wave function coefficients plus the 3-point wave function coefficient squared. And actually there's 2 different ways of squaring with complex conjugation, so there's actually 3 terms. Yeah. And when you put everything together, it's kind of subtle to get the same answer. And that's why in our lecture notes, actually, we spend a long time trying to get everything right. And it's a very instructive exercise to calculate this 4-point function, for example, in the informalism, where you have to worry about all these time orderings, yeah, and it's a bit complicated. The wave function is nicer. You just calculate the 4-point function of O. You also have to calculate the 3-point function of O, and you have to assemble the pieces such that it gives you the 4-point function of phi. But then we will find that the correlation functions of O have nicer analytic properties than phi itself. So it's nicer to think as an underlying object about correlations of O rather than correlations of phi. Yeah. And so unfortunately I don't have time to do all of it. Yeah. But so in the lecture notes we therefore do all 3 things to show that these are the same. But indeed, when we calculate the boundary correlation functions phi, that should be the answer of the informalism. And it will always be if you do things correctly. But it has to, sometimes it's assembled in terms of wave function correlations in a non-trivial way. Yeah. Okay, so let's start with this example in quantum mechanics. So I'm gonna work with the following action. So I'm gonna call the amplitude of the oscillator phi, just so that we have a correspondence between these things. And so this is a 1-dimensional time integral of 1/2 phi dot squared minus 1/2 omega squared phi squared. Okay. And actually, before having the anharmonic oscillator, let's just really do basic. Let's do the harmonic oscillator to make sure that the wave function approach gives us the right answer that we already know. Yeah. Yeah. Yes. I think maybe this person was asking before I clarified it. Because remember, I was just writing this exponential without explaining it. The motivation is that the wave function itself in the saddle point approximation is an exponential of the action. And so what I'm doing inside here is I'm just expanding the action in powers of the field. And so the exponential is naturally there because it's e to the I action. It was totally insane for me not to explain this. I don't know what it was. Yeah. it is very important that we start with e to the I action for the wave function. Then we expand the action in powers of the field fluctuations. And that expansion is what I'm writing up here. Okay. All right, yeah, so my apologies for messing that up. Okay, so this is the harmonic oscillator. So the whole challenge is just boils down to finding the classical solution, feeding it into the e to the I action to get the wave function, squaring the wave function, and calculating all possible correlation functions. So what's the classical solution of the harmonic oscillator? The classical solution of the harmonic oscillator is e to the I phi e to the I omega t. Yeah? And it has to be the classical solution with the right boundary conditions. Namely, that it's purely positive frequency, so there's no minus I omega t. With this I epsilon prescription that I gave over there, this is the one that vanishes at early times. The other one would blow up at early times. And then the field value at t going to 0 is just phi. Okay? So that's a unique solution of the second order equation for the harmonic oscillator that satisfies the two boundary conditions that I prescribed. Okay? So very simple. And so from that, we can then calculate the on-shell action. So S of phi. Okay? So we integrate this from Ti to T star. You're going to see in a moment why I'm explicit about the integration limits. So actually, before we evaluate this, let me also tell you that you can actually, you can rewrite this action for the harmonic oscillator as follows, namely as a pure boundary term, a total derivative minus 1/2 phi classical times the equation of motion okay, just by integration by parts. Okay, so by integration by parts, so if I take this kinetic term here and I integrate by parts, I get a phi double dot and a phi with a minus sign, and then I'm just combining it with with this frequency term. Okay, so this is just taking the kinetic term, integrating by parts. And the reason integrating things by parts is nice, it creates one term that's proportional to the equation of motion, which on shell for the classical solution will vanish. Okay, and then it leaves me with a boundary term. Okay. So and this boundary term then becomes 1/2 phi dot classical phi classical evaluated at t equals t star. Okay. Of course, strictly speaking, I should be evaluating these boundary terms at both values. Why don't I include the boundary value at ti at the initial time? Exactly, it vanishes by the boundary condition. Okay, and so at early times this boundary term has to vanish, but at late time it doesn't have to vanish. Okay, and therefore we're picking up as this classical action is just given by this pure boundary term. Okay, and then now if I'm evaluating this action here, what I will get is I omega over 2 phi. Okay. So the classical action is just the boundary value of the field times I omega. Sorry, squared, boundary value of the field squared. All right. Okay, from this I can then calculate the wave function. So the wave function is, remember, e to the I s phi classical. So this then just becomes an exponential of minus omega over 2 phi squared. Okay? So it's just the Gaussian wave function of this field. Yeah, which means that the wave function coefficient is just omega, and the variance, phi squared, is just 1 over twice omega. Yeah? Okay? All right. So that's of course just the standard result of a 0-point fluctuation of the harmonic oscillator scale as 1 over the frequency. Okay, and so also it's what we calculated in canonical quantization this morning. So in quantum field theory, in fact, the same result applies for each individual Fourier mode. So we can also write phi k, phi minus k as 1 over twice omega, which can now be a function of k, where omega k is defined as k squared plus m squared. So in flat space quantum field theory, for example, if you calculate these 2-point fluctuations for each Fourier mode, they would of course just be multiple copies of this quantum mechanics problem, okay? And so that will be useful for us in a moment, because we will be immediately able to apply things from quantum mechanics to inflation by doing this translation in Fourier space. Okay. All right. Okay, so let's make this slightly more interesting. Let me see. Let me do this here. So we're gonna study this harmonic oscillator now 2 more times. One, I'm gonna keep it harmonic, so just quadratic, but I'm gonna make the frequency time dependence. And so that's in fact exactly the case that we had to deal with in inflation. And so we just want to reproduce the calculation that we did this morning. And then we're going to add interactions and study the anharmonic oscillator. So let's first do a general time-dependent oscillator, S phi. So I'm going to introduce an arbitrary function a of t in front of the kinetic term, and a second arbitrary function b of t in front of this quadratic potential term. Okay. So then the classical solution for the field has a boundary value phi, and it has a well, sometimes we call this the propagator. It has a free field solution k of t, where k at 0 is just 1, and k at minus infinity is e to the I omega t. Okay, and the precise solution, of course, for k of t will depend on my functions a of t on b and t. Yeah, so I couldn't tell you this now because I haven't specified enough. Okay, so you could write down the equation of motion that involve factors of a of t and b of t, and the solution k of t will depend on a and b. Okay. But let's keep things just general, that I have introduced these 3 free functions, and we just want to see what the variance of the harmonic oscillator depends on with these 3 functions. Okay. So now the on-shell action when we do exactly the same calculation as before, so we first integrate this action by parts, so we get total derivative of a phi dot classical, phi classical, minus 1/2 phi times something that's just the equation of motion. So it vanishes on shell. Okay. So notice that this function b of t does not appear in the on-shell action. On-shell action only depends on a, because that's the part that I was integrating by parts. The function b will implicitly, of course, appear in k of t. So it's not that the answer will never depend on b of t. It will depend on b of t implicitly through this function k of t. And again, I integrated, so now I pick up the boundary term from this total derivative, and so I will get 1/2 a phi dot classical, phi classical, evaluated at t equals t star. Which becomes 1/2 a little phi squared dt log of k at t equals t star. Okay? Okay, now if I calculate the wave function squared for this solution, I will get exponential of minus imaginary part of a dt log k at t star of phi squared. Okay, so it's again Gaussian. And of course it's still Gaussian because we're still studying just the quadratic theory. But now there's a more general variance or 2-point wave function coefficient that appears. And so now the expectation value of phi squared is 1 over twice the imaginary part of a dt log of k, evaluated at t star. Okay? All right? Yep. How did I get logarithm? Exactly. Exactly. Well, but on the boundary that oh, good. Well, I think the log was by choice because I'm evaluating it at t star, and at t star k is 1. So yeah, very good. Naturally, there wouldn't be a log here, yeah. But I'm just putting the log in. Actually, for later convenience, actually, it will be nicer to have a log there. But I could divide by any powers of k. It's 1 at the yeah. Okay. Yeah, at this point we didn't have to do this, but we will see in a moment that taking a log, k itself will be an exponential function, and then taking a log will be nicer. Okay, but you don't have to do it. Okay. Okay, so let's actually use this result, and maybe I can just erase a few things and hopefully try to adapt this to what this calculation that we did earlier for inflation and see that we get exactly the same. So when I take a massless field in the zeta space and I expand it in Fourier modes, I will get an answer like this, where there's an extra d3k 2 pi cubed. This function a here will become 1 over h eta squared phi prime k phi prime minus, so phi minus k prime minus k squared over h eta squared. Okay, so if I just take a massless field in the zeta space and I expand it in Fourier modes, yeah, so a massless field will just have an action that's like phi dot squared and then grad phi squared. In Fourier space, the grad phi squared will just become a k squared. Okay, and so that's why this is just the action of a free field in the zeta space with extra factors of time because of just the time-dependent scale factor that I get from the measure of this integral. Okay. But you see that it takes exactly the same structure where this function here is a and this function here is b. Okay. So then in the zeta space also we know that the classical solution is phi times k of eta, where k of eta is now 1 minus I k eta e to the I k eta. Okay. That's just the solution that we found earlier. So now if I take a log of k, I will get that this is log of the prefactor 1 minus I k eta plus I k eta. Okay. And so I could now just take this log here and this A and feed it into my variance over there. Okay? Those are the only two functions that appeared in this answer over here. So, and actually, yeah. So the imaginary part of A d eta log of k at eta equals eta star is 1 over h eta star squared. That's just my function capital A evaluated at eta star times the imaginary part of 1 minus 1 over k eta star minus ik plus ik. Okay? So this is just the derivative of the log that I have over there, and this is derivative of the ik eta, yeah, all evaluated at eta star. And so that's why there's a dependency on eta star. So let's see, I can write all of this as 1 plus k squared eta star squared k squared eta star plus I k cubed eta star squared. Okay? So if you just take these two terms and you combine, you write them in terms of a single fraction here, you could check that it becomes this. Okay? And so there's one just interesting point that I want to make is that there's a piece here that's IR divergence. Yeah, because it just comes with a single power of eta star. Yeah. So notice that this piece here, if it survived, if there wasn't the imaginary part operation here, then this first term here would just have 1 power of eta star, while there's 2 powers of eta star here, which is IR divergent. Okay. So luckily, this does not survive. This is just a phase in the wave function, and it disappears when I take the square of the wave function. But the wave function of the universe has an IR divergent phase. Okay? But the physical answer, the correlation functions will not know about this IR divergent phase, because you have to take absolute value, and it drops out here. And the only thing that survives is this term. And this term, this eta star squared, will cancel exactly against the eta star squared over there. And this one I'm taking to 0, so it doesn't, only the 1 here survives. Okay? So in the end, if I'm taking the limit eta star going to 0, what I'm left with is k cubed over h squared. Okay? So sorry, in my notes this is written out a bit more neatly, and then you should try and reconstruct this for yourself. But so the 2-point wave function coefficient for a free field in the zeta space is k cubed over h squared. Okay? And so of course the correlation function on the boundary is just the inverse of that, which is h squared over k cubed, which is precisely what we calculated this morning. Okay? So the 1 over k cubed was the scale invariant spectrum. Here the wave function coefficient is exactly the inverse of that answer that we got this morning. Okay? Okay. So any questions about this? Sorry, in principle we should stop now. Is that right? Is that the okay. Yeah, so then I will complete the anharmonic oscillator. So we're just in free field theory at the moment. I will complete the anharmonic oscillator tomorrow, and I will show you how basically exactly the same ideas that we just discussed now will apply there. And then we will see how all of this manifests itself in the interacting theories. Okay, I'll stop here. Thanks.
Okay, more questions to Daniel? Okay, perhaps we had enough questions during your talk, so let's thank Daniel once more.
So yeah, another announcement about meal. So for the dinner, so now it's like 5:10, right? The dinner, unfortunately, only starts at 5:30. And again, we have this entrance rule. So why don't we start around 5:25 together here? And I heard that for the dinner, all of us can enter the building together. So, I mean, not many people are actually having dinner in the cafeteria, so we can all have dinner at a time. And for the dinner, Mio over there will be leading the group, so you can follow her. So enjoy your dinner.
Sorry, not the full, yeah, well, the half of it. It goes behind that. Sorry? It's the whole, it goes behind that. So it goes, sorry, say that again. That's like each point is a circle. Sure. Each point is a sphere.
Actually, he lived mathematics, but actually I don't know what he asked. So. He is here for me now. He also asked several times.
No, I'm doing the path integral here. Oh, sorry, what do you mean? To generate the wave function, you do a path integral on where you're shaded. Yeah, sure. Yeah, but then step also, like fluctuations originating from the complementary patch, which would inevitably enter this patch. How do you account for that? Because in flat space this is legit, I understand, because that's the whole flat space. Yes. How do you account for this? Because it's something I never understand when we go to flat space coordinates and do this wave function calculation. I thought the Indian formalism was used because this kind of issue is there. But now since we you said like it's accelerated to wave functions. Well, it's definitely a fact. In our notes we show very explicitly that it's just equivalent. So all the Indian calculations that you can do will be reproduced by this wave function.